Welcome. So in this course, we're going to be learning about computer architecture. And this course is an adaptation of a course which I teach at Princeton University called ELE, or for Electrical Engineering 475. And I'm David Wensloff. I'm a professor here at Princeton. And my background is mostly looking at how to build many-core and multi-core microprocessors. And in the past, I've actually built two of the world's fastest many-core microprocessors in industry. And before that, I've worked in academia building many-core microprocessors. So about 15 years of processor design experience. In today's lecture, we're going to be talking about an introduction or some opening to what is computer architecture, why do you want to learn computer architecture, how it's different than previous courses that you might have taken, so something like a computer organization class or a logic design course. And then we'll talk about some content today, which is looking at instruction set architectures and how a instruction set architecture or big A architecture is different than implementation or microarchitecture, and why it's a good idea to split out these two ideas. So let's take a step back and look at the course administration of this class and how this class is going to be organized. So as I said, I'm David Wensloff. This class is roughly going to be the equivalent of 2 80-minute lectures a week. So this is the same format that's used at Princeton University for this course. And we're going to try to segment into shorter segments to sort of give you bite-sized nuggets with questions and answers intermixed to check your understanding as the video goes on. Two books that I wanted to talk about. This is the Computer Architecture, A Quantitative Approach by John Hennessy and David Patterson. This is a very, very good book. If you are going to be doing computer architecture, I highly recommend it. And it's a heavily suggested book for this course. I did want to point out that there's a lot of different versions of this book floating around. We're going to be using the 5th edition, and you should go get the 5th edition. The 5th edition is very different than the 4th edition. It's updated as of 2012, so it's very fresh. And then a auxiliary text, which is useful for a portion of this class. I'll mention it as the Shen-Leposti book, because of the two authors. Modern Processor Design and Fundamentals of Superscalar Processors. The reason we're going to use this book, or a reason that we're going to, I'll recommend some readings out of this book, is that it has a lot deeper coverage of superscalar processors than the computer architecture book. So this is a great book to begin with, but it doesn't cover how to build superscalar processors in great depth. This book goes on to do that, and that's something we're going to be talking a lot about in this course. A lot of the content of computer organization, or a traditional computer organization class, I'm going to repeat in the first 3 lectures of this course, or the first 3.5 lectures of this course. And the reason for this is because I teach everything from first principles and want to get everyone on the same page, but we're going to go very, very fast through that material. So if you've not had a computer organization class, it may be possible to take this class, but I highly recommend taking a computer organization class before this class, because this is the second class in sort of a computer architecture series where you'd have computer organization and computer architecture, and we really do rely on the prereqs. But if you are watching the first 3 lectures and you say, I know all this, yes, that is correct. You should know all this. If you don't know all this, then you should probably go back and retake computer organization or take a computer organization class. But don't drop the class if you take the first 3 lectures and say, oh, I know all this, and just leave at that point. Because we're just going to breeze through that content very fast as building from first principles. So what is computer architecture? Computer architecture, we're trying to take an application or something that a human wants to do. So for instance, calculate a spreadsheet, play a video game, play some sort of music. And we want to figure out how to map it down to physics. So what do I mean by physics here? Well, physics is we have in the world, we have particles, and they bounce around, they interact. We have photons bouncing around in the world. And we need to somehow translate what humans want to do into what the physics can do. And one of the problems with this is a really big gap. So how do you go from application directly to physics? You have physics bouncing around the world. You have mechanical systems. And without some level of abstraction, it's very hard to go from the application directly to the physics. Now, in the broadest sense, what computer architecture is trying to do is it's trying to come up with the abstraction and the implementation layers that are needed to be able to bridge this gap. So we're going to put a bunch of different layers in here. And by making smaller abstraction layers and smaller layers, we're going to be able to solve subsets of these problems and not have to change everything here in the middle. Just one, let's say the physics changes or the application changes a little bit, we'll be able to reuse a lot of the work that we've done along the way. And computer architecture is the study of these layers and figuring out how to take the physics and turn it into applications that humans want. Now, I wanted to point out that in the natural world, it's pretty challenging to directly jump from application to physics. But there's a few examples. So one example I wanted to bring up, actually, is the compass. The compass is a nifty little device that directly takes physics and gets pushed up into an application. But there's very few other examples. I think a book is an OK example of this. But otherwise, people build lots of abstraction layers in between here. And one other thing I wanted to point out here is that we're trying to efficiently use manufacturing technologies. So what I mean by that is when physics changes or we move to smaller transistors or we move from, let's say, silicon to gallium arsenide or some other implementation technology, that changes the bottom layer here. But we want to still be able to reuse a lot of the other work that we've done over the years. So let's take a look at the abstractions in modern-day computing systems. We start off here with physics. We have fundamental physical laws of how particles interact. And we move up to devices. So what do we mean by devices? We have transistors, and we can build different types of transistors, MOSFETs, BJTs. We can build other types of FETs. And then we start to build circuits, bigger circuits out of this. And out of those, we go and build gates. And from gates, we can go to RTL, or register transfer language here, which is sort of our Verilog coding. And then we start to get into where this course is about, which is different types of architecture. So there's microarchitecture, which is how do you go and actually build a specific implementation of a chip. And then above that, we have instruction set architecture, which gives us some portability on top of that. And then we get into operating systems and virtual machines, programming languages, and algorithms. And then finally, we get to the application programmer sitting on top. So in this course, in computer architecture, we're going to be focusing on these three middle layers here: instruction set architecture, or what I will sometimes refer to as big A computer architecture; microarchitecture, or sometimes what people call organization of computing systems; and register transfer language. And we'll also overlap a little bit into the abstraction layers above and below here. So we'll talk a little bit about some operating system concerns and virtual machine concerns. And we'll talk a little bit about how the technology in the gates influences the computing system. So one important point here about computer architecture is it's constantly changing because different constraints and different applications are changing. So people have new applications they come up with. They come up with ways, or people come up with different applications. I now want to have a smartphone. Well, that didn't exist 20 years ago. And this pushes down different requirements. And these different requirements actually suggest how to change the architecture. If you, for instance, want to do a lot of video processing, that actually can influence your computer architecture, so you add specialized instructions to do video processing. Likewise, the technology constraints push up. So as we go to smaller and smaller transistors, we'll say, Those smaller and smaller transistors, let's say, go faster, but the wires go slower. Well, that's going to influence your computer architecture. And a lot of times, new technologies make new architecture possible. So what do I mean by that? Well, let's say all of a sudden you get a big bump in transistors. You get twice as many transistors. Well, now architectures and microarchitectures that didn't used to make sense start making sense. Because you can, for instance, fit a lot more computation on one chip. And what's the interesting thing here is that computer architecture is not done in a vacuum. So computer architecture actually provides feedback up and down this abstraction layer stack. So it'll give feedback, and it'll actually influence the research directions that technology looks at, and it'll influence research directions and influence different applications that are possible. So this is not all done in a vacuum. The computer architect actually sits in a very key location in this abstraction layer stack here, because you can push up and push down, and you're not just forced to work with what you're given, if you will, from the technology perspective. But that might take a few years. So let's talk a little bit more about what this class is about, but we'll do it by way of a little bit of history. And to put a little bit of a Princeton connection in here, we're going to talk about computers back in the late 40s, early 50s, 1940s, 1950s. So here's actually a picture of the IAS, or the Institute for Advanced Study machine, which was built in the Institute of Advanced Study, which is maybe about 1.5 miles away from this classroom. And it was designed by John von Neumann. And to give a little bit of insight here, it was first booted in Princeton in 1952. It was actually started in the late 40s and took them a couple years to get working. And one of the interesting things here is that this machine is actually built out of vacuum tubes. So everyone thinks about transistors today. Well, before we had transistors, we had little glass tubes that actually looked like light bulbs. And inside of those, they were switches that could be switched. So a very similar idea to what a transistor can do. But instead, you had a evacuated glass tube, and you had a little transmitter. It was a cathode ray tube. And then you had a gate that could open and close inside of this. So people were building computers long before transistors, and people were thinking about computer architecture long before transistors. And people were even thinking about computer architecture and these sorts of technologies even before vacuum tubes. So there was electromechanical systems. A good example of this actually was originally in phone systems. They had these cool electromechanical switches. So when you take your old rotary phone and you sort of turn it, and then it goes tick, 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 tick. What it's actually doing is it's sending pulses, which are turning a little mechanical arm inside of a relay system. And people built computers out of those electromechanical relays. So you can have switches that change switches, similar sorts of ideas to transistors. And even before that, people had looked at building mechanical systems. So there was mechanical adding machines, for instance. And nowadays, we, of course, have transistors. So that was computing then, in the 50s. And if we fast forward to today, we have computers look very different. In this figure here, this thing was the size of a room. Pretty big room. To give you scale, sort of a person is maybe yay tall in this figure. This thing fits in a sort of normal-sized room, but still sort of room-sized. But today, we have lots of different applications, and computing looks very different. So we have computing, let's say, in small systems. We have little sensor networks and little sensor nodes distributed. We have fancy cameras. We have smartphones. We have mobile audio players and iPods. We have laptops, like my laptop here. We have self-driving cars. We have big servers. We have Xboxes. And there's a lot of variety now in what computing systems look like. So the influence of this technology in computer architecture has been very, very broad. And we even go on to seeing things like routers, flying unmanned autonomous vehicles. We have GPSs, which are little computers that can basically fit on your wrist these days and tell you exactly where you are. e-books, tablets, set-top boxes, and the list goes on and on and on. And what I wanted to get across here is that computer architecture has a very rich history, and this history is continuing and it's very relevant today. So we're not studying something which no one cares about anymore. People are sitting there sort of ready to get the next generation computer architecture. People, and it used to be, you want your faster desktop computer, and that may not be as important today, but what is important is people want their faster smartphone, they want to enable voice recognition on the go, they want to be able to, in scientific applications, they want to be able to model some health system that's really complex that you weren't able to do before. So it continues on and on, and it is very relevant today, and it has a very rich history. In this course, we're going to talk a little bit about the history, but mostly focus on the technology. Sometimes when people teach computer architecture classes, they have much more emphasis on the history. This class, we're going to touch on history a little bit, but more focus on the technology considerations. So here's a chart that's from Hennessy and Patterson's computer architecture, or a quantitative approach. And what this graph's trying to show is something very fundamental to computer architecture. And it's what's been driving our industry. So what we see here is we see different processor designs plotted on a log plot. So this is 10, 100, 1,000. So this is a log plot, and this is performance versus years. So if you look at this plot, you'll see that, well, this roughly looks like a straight line. And a straight line on a log plot is an exponential increase in performance. So we've seen computing going up exponentially faster. And this is really fundamental to driving what's been going on in our industry and why computer architecture is so important. And I do want to say that this exponential increase comes from two things. It's not all computer architects. I'd love to be able to stand here and say, we did all this. Well, no. A fair amount of this is from getting better technology. What I mean that is the lower down layers and the implementation technology, like the transistor technologies. And some of it is from having better and better computer architecture. And what is really important here to note is that even if you have better and better transistors, a lot of times what happens if you look at this graph is what's happening is you're getting more transistors, but those transistors are not necessarily exponentially faster. So what computer architects have to do is we need to figure out how to take buckets and buckets of more transistors and turn them into more performance. And that's what this is many times called Moore's Law. If you've heard that term before, what it is we're trying, Gordon Moore said that every 18 months to 2 years, you're going to get twice as many transistors, which you can have for the same amount of dollars. That was what was originally said. People have sort of transformed that now into meaning your computers can get twice as fast every year. That's not what Gordon Moore originally actually said. He said you can get twice as many transistors for a certain amount of dollars. And people have also sometimes taken this to mean that you get twice as many transistors on a chip every year. Not quite what he said, but close enough approximation. And I don't quite have the graph here, but if you look at computing in general across, this is all across transistor-based technologies. But if you go farther back into the past, you can actually plot other technologies like vacuum tube technologies and relay-based technologies. And it also fits on this graph relatively well. So sort of if you continue down here, you're going to see vacuum tubes show up, and it's sort of still on this exponentially increasing curve. OK, so let's look at, there's two inflection points in this graph that we want to look at. First one's right here. You can see the slope changes a little bit. Well, what happened here? This was the introduction of reduced instruction set computers, or RISC computers. So we got a little bit of a crink up there when people came out with the first RISC. And another thing you notice is this graph keels over a little bit here. And we're going to be talking a lot about this in this course, is what happens, or why did this happen? So what happened here? Well, sequential performance, so this is the performance of a single program, was getting faster exponentially. But then, I don't know, depending on who you ask, I like to use 2005 as the number, but somewhere between 2003 and 2007, sequential processor performance started to really have a problem. But overall performance of your processor still continues to go up today. And what happened is we had a move to multi-core processors, or multiple cores on a single chip. And hopefully, the hope is that this graph will continue on here with multiple cores if we can figure out how to effectively parallelize our programs versus our sequential performance tapering off. Because it'd be very harmful to computer architecture and the computing industry if all of a sudden our computers stopped getting faster. No one would be buying new computer chips. So course structure. There's going to be recommended readings. There's going to be in-video or in-lecture questions that will pop up. There's going to be several problem sets during the term. And these are going to be very useful for review for exam preparation. So I'll give you guys a hint right now that if you do the problem sets and actually master the problem sets, the exams are going to be relatively easy after that. We'll probably use peer evaluation for grading the problem sets because a lot of them are more open-ended problems. And we're going to have a midterm and a final exam. One other thing I wanted to point out is collaboration in this class is encouraged, but I want everyone to make their own problem sets and midterms and final exams. So you can discuss the overall generalities of the ideas and the concepts going on, but I don't want people discussing the actual exam questions in particular. So for instance, you can discuss the concept if you have some caching question and you want to understand how caches really work. Discuss the concepts and collaborate on that, but don't discuss and collaborate on the actual problem itself on the respective problem sets, midterms, and final exams. OK, so let's talk about the content of this course. So we give a very high-level motivation, and now we're going to talk about what's inside of this course. And I'm going to start off by contrasting it with what you should have already learned. So in a computer organization class, something like ELE 475 at Princeton, you're going to have learned how to build a basic processor. So something like we see here. This is actually the RISC-1 processor from Berkeley. Depending on who you ask, either the RISC-1 or the first MIPS chip was sort of the first academic RISC. The IBM 801 probably used a lot of those ideas, but didn't call it RISC before then. But you learned how to design stuff which had about 50,000 transistors. So this entire design here, this is a two-stage pipelined processor. But things that you should have learned is basic cache ideas, pipelining. So how do you pipeline a processor? A little bit about memory systems. And you should also know sort of how logic works, or digital logic works. And then in this class, to contrast, instead of learning how to build a very simplistic processor, we're going to learn how to build cutting-edge, modern-day microprocessors. That's right. We're going to learn how to build things like this, or at least design things like this. So this is a Core i7 from Intel. I guess this is the original Core i7. We're now in the third generation of Core i7s, standing in 2012 now. So this is pretty recent. And to give you an idea, to contrast in that previous picture, which was 50,000 transistors, this design is about 700 million transistors. So the complexity has gone up here a lot. And that other processor, or the processors that you learned about in your computer organization class, fit this little tiny box up here and have performance that's sort of equivalent to the size of the little tiny box relative to this big processor. So we're going to learn how to, instead of just building little tiny processors or toy processors, we're going to learn about how to build big processors and high performance processors. So before I go down this list, I wanted to talk briefly about the course content of ELE 475 and the two main techniques to make processors go fast. So how do we go about making processors go fast? Because people like their computing systems to run fast. Well, one is to exploit parallelism. So we're going to figure out how to exploit lots of concurrent transistors or concurrent parallelism in your program. And as you add more transistors and more parallelism, hopefully it'll make your computing system go faster. And there's different techniques on how to go after parallelism. And they're not all explicit parallelism. So a lot of them are implicit parallelism. So for instance, instruction level parallelism is a completely implicit concept. The programmer doesn't have to do anything. And then the other main technique we can think about is just to do less work. So if you're trying to do something and you look at, let's say, an assembly line of someone building cars, well, you can either pipeline and try to get pipeline parallelism in your assembly system, or you can try to have multiple people building different cars at the same time. So that's all falls into the parallelism category. Well, something else you can do if you want to make a car faster is you just take out steps or you take out components. So you do less work. And one way to do less work is to have fancier software systems. So we can have better compilers and runtime systems. And a lot of times they can remove work. So this is like the optimization pass in your compiler. If you turn on -03 or the optimization for GCC, it's going to try to remove instructions from your program, which are either redundant or not doing any useful work. Another great example of this, which people don't really think about as doing less work, but actually is something like a cache in your microprocessor. So in your cache, it puts memory closer to the processor than main memory. Well, this is equivalent to if you had an assembly system or a production line of cars, and let's say for every part you had to get, you would walk down the street 3 blocks away, get the part, and bring it close. Well, that's pretty slow. That's doing a lot of work for each part that you need to go fetch. But in a cache, you can actually put the data very close, and by doing that, or put the parts very close, similar sorts of ideas here in car assembly, is you can put a bin, if you will, of all of the parts you need to build the car, and then just grab out of that bin, and you're going to do less work, do less walking. Similar sorts of things with caches. So these are the two primary techniques that we're going to apply. So now let's dive into the actual technical content of what we're going to learn in computer architecture, in this computer architecture class. And we'll categorize them as either doing less work or parallelism. So the first thing we're going to start off in this class talking about is we're going to talk about instruction level parallelism. So we're going to look at superscalar processors, which can execute multiple instructions at the same time. And it's done implicitly from sequential code. And we're also going to study very long instruction word processors, or what's called VLIW processors. We're going to hint a little bit about pipeline parallelism and look at how to build longish pipeline processors. We'll talk about advanced memory and cache systems. So this has no parallelism in the word here, in the title here. So what this is going to be is this is going to be looking at doing less work. And we're going to look at how you build memory systems that either bring the data closer or have higher bandwidth, and a lot of the implementation issues in building these advanced memory systems. Then, as the term goes on, we're going to be talking about data level parallelism. So this is more explicit levels of parallelism. So these are things like vector computers and graphics processor units or general purpose graphics processor units, GPGPUs. And at the end of the course, we're going to talk about explicit threaded parallelism and be talking about multi-threading. How do you build multi-processor systems? So this is multiple chip multiprocessor systems, multi-core and many core systems, and how do you interconnect all these different processors? Roughly, the first third of the course is going to be talking about instruction level parallelism. There's going to be sort of a middle third, which is going to talk about caches and a little bit about data level parallelism. And then the last third is going to talk about more threaded levels of parallelism. But that's a very coarse cut of this class. OK, so now we're going to change topics and start talking about our first technical subject of this course. And as an introduction to computer architecture, we're going to be talking about what is architecture versus microarchitecture. And I wanted to just briefly say that as you take this class, the first 3 lectures or so should be review. So if you're sitting in the class and you're saying, oh, I've seen all of this before, don't get up. Wait to the 4th or 5th lecture, and then the content will become new. And this is because I want to teach everything from first principles and get everyone up to speed. But those first 3 lectures are going to go very fast. So if you're lost in the first 3 lectures, which should be review, then that's probably a bad indicator. So we'll start off by talking about architecture versus microarchitecture. And I wanted to say briefly what I mean by architecture. And I have in this slide here a very large A for what I'll sometimes call big A architecture. So your Patterson-Hennessy calls this instruction set architecture. And I want to contrast this with microarchitecture, or what Patterson-Hennessy calls organization. So big A architecture is an abstraction layer provided to software, or instruction set architectures are abstraction layer provided to software, which is designed to not change very much. And it doesn't say, it says how a theoretical fundamental sort of machine executes programs. It does not say exactly the size of different structures, how fast those things will run, the exact implementation issues. That falls into organization. And one of the things I wanted to emphasize is that computer architecture is all about trade-offs. So when I say it's all about trade-offs, you can make different design decisions up here in the big A architecture or the instruction set architecture, and that'll influence the application, it'll influence the microarchitecture. But also, you can make different design decisions down here and make a lot of different trade-offs on how to go about implementing a particular instruction set architecture. And largely, when you go to look at computer architecture and computer architecture implementation, the design space is relatively flat. There's sort of an optimum point where you want to be, but the other points around it are many times not horribly, horribly bad. Though there are, at the extremes, probably horribly bad design decisions. But a lot of different design points are equally good or close to optimal. And the job of a computer architect is to make the very subtle design decisions around how do you move around this point to make it both easier to program, lives on for many years, is low power, and sort of other a little bit of aesthetic characteristics mixed together with just making your computer processor go fast, we'll say. And these trade-offs, I will reiterate this over and over again in this class, that because there's multiple different metrics, so for instance, speed, energy, cost, and they trade off against each other, many times, and there is no necessarily optimal point. It depends on, if are you more cost-driven or energy-driven or speed-driven. And within that point, there's sort of sometimes Pareto optimal curves where all the points are equally good if you're trying to trade off these different things for different cost models. OK, so let's talk about what is a instruction set architecture and what is a microarchitecture. So a instruction set architecture, or big A architecture, is trying to provide the programmer some abstract machine model. And many times, what it really boils down to is it's all the programmer visible state. So for instance, how does the machine have memory? Does it have registers? So that's the programmer visible state. It also encompasses the fundamental operations that the computer can run. So these are called instructions. And it defines the instructions and how they operate. So for instance, add. Add might be a fundamental instruction or a fundamental operation in your instruction set architecture. And it says the exact semantics on how to take one word in a register and add it to another word in a register and where it ends up. Then there's more complicated execution semantics. So what do I mean by execution semantics? Well, if you just say adds take two numbers and add them together and put them in another register, that many times does not encompass all of the instruction set architecture. You'll have other things going on. For instance, I/O, interrupts, and you have to define in your instruction set architecture or your big A computer architecture what is the exact semantics of an interrupt or a instruction or a piece of data coming in on an I/O. How does that interact with the rest of the processor? So many times the instruction execution semantics is only half of it, and what we have to worry about is the rest of the machine execution semantics. Big A architecture has to define how the inputs and the outputs work. And finally, we have to define the data types and the sizes of the fundamental data words that you operate on. So for instance, do you operate on a byte at a time, 4 bytes at a time, 2 bytes at a time? How big is a byte? Do you actually have bytes? So this gets into sizes. And then data types here might mean that you have other types of fundamental data. So for instance, the most basic one is you have just some bits sitting in a register in your processor. But it could be much more complex. So you could have, for instance, something like floating point numbers, where it's not just a bunch of bits. It's bits formatted in a particular way and has very specific meaning. It's a floating point number that can range over, let's say, most of the real numbers. OK, so in today's lecture, we're going to step through all these different characteristics and requirements of building an instruction set architecture. And I wanted to, and we'll talk about how it's different than microarchitecture or organization. So let's think about some examples of microarchitecture and organization. So what microarchitecture and organization is really thinking about here is the trade-offs as you're going to implement a fixed instruction set architecture. So for instance, something like Intel's x86 is an instruction set architecture. And there's many different microarchitectures or implementations. There's the AMD versions of the chips, and then there's the Intel versions of the chips, and even inside of, let's say, the Intel versions of the chips, they have their high-performance version for their laptop, which looks one way, or high-performance version for, let's say, a server or a high-end laptop, which looks one way. And then there's another chip for tablets. Intel's trying to make chips for tablets these days, and they have their Atom processors. And internally, they look very different, because they have very different speed, energy, cost trade-offs. But they will all execute the same code, and they all implement the same instruction set architecture. So let's look at some examples of things that you might trade off in a microarchitecture. So you might have different pipeline depth, numbers of pipelines. So you might have one processor pipeline, or you might have 6, like something like the Core i7s today. Cache sizes, how big the chip is, the silicon area, what's your peak power, execution ordering. Well, does the code run in order, or can you execute the code out of order? That's right. It is possible to take a sequential program and actually execute later portions of the program before earlier portions of the program. That's kind of mind-boggling, but it's a way to go about getting parallelism. And if you keep your ordering correct, things work out. Bus widths, ALU widths. If you have, say, a 64-bit machine, you can actually go and implement that as a bunch of 1-bit adders, for instance. And people have done things like that in the microarchitecture. And this allows you to build more expensive or less expensive versions of the same processor. So let's talk about the history of why we came up with these two differentiations between architecture and microarchitecture. And it came about because software sort of pushed it on us and ended up being a nice abstraction layer. So back in the early 50s, late 40s, you had software that people mostly programmed either in assembly language or machine code language. So you had to write ones and zeros, or you had to write assembly code. And sometime in the mid-50s, we started to see libraries show up. So these are sort of floating point operations were made easier. We had transcendentals, those are the sine, cosine libraries. You had some matrix and equation solvers. And you started to see some libraries that people could call, but people were not necessarily writing code by themselves or writing large bodies of code in assembly programming because it was pretty painful. And then at some point, there was the invention of higher level languages. So a good example of this was Fortran. Came out in 1956. And a lot of things came along with this. We had assemblers, loaders, linkers, compilers, a bunch of other software to track how your software is being used even. And because we started to see these higher level languages, this started to give some portability to programming. It wasn't that you had to write your program and have it only map to one processor ever. And back in the 50s, even 60s timeframe here, machines required experienced operators who could write the programs. And you got these machines, and they had to be sold with a lot of software along with them. So you had to basically run only the software that was given, because you had to be a master programmer or someone who worked for the company that built the machine to even be able to program these machines back in the day. And the idea of instruction set architectures and these breaking the microarchitecture from the architecture didn't really exist back then. And back in the early 60s, IBM had 4 different product lines. And they were all incompatible. So you couldn't run code that you ran on one on the other. So to give you an example here, the IBM 701 was for scientific computing. The 1401 was mostly for business computation. I think they even had a second one that was sort of for business, but different types of business computation. And people sort of bought into a line, and then as the line matured and developed, they had to either rewrite their code or they had to stick into one line. But IBM had some crazy insights here, is that they didn't want to have to, when they went to the next generation of processor, they wouldn't want to propagate these 4 lines. They wanted to try to unify the 4 lines. But one of the problems was these different lines had very different implementations and different cost points. So the thing you were building for scientific computing wasn't necessarily the thing you want to build for business computing. And the one that you built for business computing, let's say, you wanted to not have it have very good floating point performance. So how do they go about solving this? And their solution was they came up with something called the IBM 360. And the IBM 360 was probably the first true instruction set architecture that was implemented to be an instruction set architecture. And the idea here was they wanted to unify all of these product lines into one platform, but then implement different versions that were specialized for the different market niches. So they could they could unify a lot of their software systems, unify a lot of what they built, but still build different versions. So let's take a look at the IBM 360 instruction set architecture, and then talk about different microarchitectures that have been built of the IBM 360. So the IBM 360 is a general purpose register machine, and we'll talk more about that later in this lecture. But to give you an idea, this is what the programmer saw or what the software system saw. This isn't what was actually built in the hardware, because that would be a microarchitecture constraint. But the processor state had 16 general purpose 32-bit registers. It had 4 floating point registers. It had flags, if you will. It had condition codes and control flags. And it was a 24-bit address machine. And at the time, that was huge. So 2 to the 24 was a very large number. Nowadays, it's not so large, and they've since expanded that on the IBM 360 successors. But they thought it was good for many, many years. And it was good for many, many years. And they defined a bunch of different data formats. So there was 8-bit bytes, 16-bit half words, 32-bit words, 64-bit double words. And these were the fundamental data types that you could work on. And you could name these different fundamental data types. And it was actually the IBM 360 that came up with this idea that bytes should be 8 bits long. And that's lived on for today. Because before that, we had lots of different choices. There was binary coded decimal systems where you actually would encode a number between 0 and 9, and then you had each digits, and this is sometimes good for sort of spreadsheet calculations or business calculations where you want to be very precise on your rounding to the penny. And sometimes bit-based things don't actually round appropriately, or you'll lose pennies off the end. And so you had these binary code decimal systems, and well, in the IBM 360, they unified it all and said, well, no, we're going to throw out certain things and make choices. Now they, of course, because it's the IBM 360 and they did have business applications, they still supported binary coded decimal in a certain way. And let's look at the microarchitecture implementations of this first instruction set architecture. So this is in the same time frame, the same generation here. There was the Model 30 and the Model 70. And this was very, very different performance characteristics. So if we look at the machine, let's start off by looking at the storage. The low-end model here had between 8 and 64 kilobytes. And the high-end model had between 256 and 512 kilobytes. So very, very different sizes. And this is what I'm trying to get across here, is that microarchitecture can actually change quite a bit. Even though the architecture supports 64-bit adds and additions, you can actually implement different sized data paths. So in the low-end machine, they had an 8-bit data path. And if it wanted to do a 64-bit operation, it had to do 8-bit operations to make up a 64-bit operation. And then probably it actually even has to do more than that to handle all the carries correctly. Versus the high-end implementation had a full adder there, and it could actually do a 64-bit add by itself without having to do lots of micro-sequenced operations. And, oh, yes, with minor modifications, it lives on today. So this was designed in the 60s, and even today, we still have System 360 derivative machines. And a piece of code you ran, or you wrote back in 1965 will still run on these machines today, which is pretty amazing, natively. So how does this survive on today? So here's actually the IBM 360 47 years later, as in the Z11 microprocessor. So the IBM 360 has since been renamed to the IBM 370, and then it has been renamed to the IBM 370EX, which was in the 80s. There was never a IBM 380, strangely enough. And then later on, they just changed the name to the Z series. So have a cooler model numbers here. So we had the IBM Z series processors, and this lives on today. So going back to that 8-bit processor, which had a 1 microsecond control store read, which is forever, we now have the Z11, which is running at 5.2 gigahertz, has 1.4 billion transistors. They have updated the addressing, so it's no longer 24-bit addressing, but it still supports the original 360 addressing. It has 4 cores, out-of-order issue, out-of-order memory system, big caches, on-chip 24 megabytes of your L3 cache, and you can even put multiple of these together to build a multi-processor system out of lots and lots of multi-cores. And what I'm trying to get across here is that if you go forward over time and you build your instruction set architecture correct, it can live on, and you have many different microarchitecture implementations and still leverage the same software. And a few more examples just to reinforce this a little bit more. Let's take a look at an example of something where you have the same architecture but different microarchitectures. So here we have the AMD Phenom X4, and here we have the Intel Atom processor, the first Intel Atom processor. And what you'll notice actually is that they have the exact same instruction set architecture. They both run x86 code. And the design implementations, and this is just to point out here, these are the same time frames. So this is roughly modern day processors. This one has 4 cores, 125 watts. Here we have single core, 2 watts. So there's design trade-offs. So you're going to want to build different processors in the same design technology, we'll say, but with very different cost, power, performance trade-offs. This one can decode 3 instructions. This one can decode 2 instructions, so it's a different microarchitecture difference. This one has 64 kilobyte cache, L1. This one has a 32 kilobyte L1 iCache. Very different cache sizes, even though they're implementing the same architecture, or big A architecture. Strangely enough, they have the same L2 size. You know, things happen. This one's out of order versus in order, and clock speeds are very different. And I wanted to contrast this with different architecture, or different big A architecture, and different microarchitecture. So if we think about some different examples of instruction set architectures, there's x86, there's PowerPC, there's IBM 360, there's Alpha, there's ARM. You've probably heard all these different names, and these are different instruction set architectures. So you can't run the same software on those 2 different instruction set architectures. So here we have an example of 2 different instruction set architectures with 2 different microarchitectures. So we have the Phenom X4 here versus the IBM Power 7. And we already talked about the X4 here, but the Power 7 has the power instruction set, which is different than the x86 instruction set. So you can't run one piece of code that's compiled for this over here, and vice versa. And the microarchitectures are different. So here we have 8 core, 200 watts, can decode 6 instructions per cycle. Wow, this is a pretty beefy processor. It's also out of order and has the same clock frequency. Something that can also happen is you can end up with architectures where you have different instruction set architecture or different big A architecture, but almost the same microarchitecture. And this does happen. So you end up with, let's say, 2 processors that are both 3 wide issue, same cache sizes, but let's say one of them implements PowerPC and the other one implements x86. And things like that do happen. That's more of a coincidence, but I'm trying to get across the idea that many times that the microarchitectures can be the same, and those are more trade-off considerations versus the instruction set architecture, which is more of a software programming design constraint. So now we're going to start talking about the fundamental things inside of an instruction set architecture and the things you need to build inside of an instruction set architecture. And we're going to start off by talking about machine models. So I have a question here. Where do operands come from? And where do results go to? So when I say operands, these are the data values that you're going to operate on with a single instruction on a processor. And the results are where they the data that gets calculated, and where does it go. And this is actually an instruction set architecture or a big A architecture concern. Fundamentally, you're going to have some form of arithmetic logic unit or some sort of calculation unit. And you're going to have some type of memory storage. And in a processor, you're probably going to want to take stuff from the storage, move it to the ALU, compute on it, and then put it back into storage somehow. And this is the processor here that we wrap around the ALU. And the machine model is what is the implementation, what is the semantics, or excuse me, not the implementation, what is the organization of the registers, how do you go to access memory, what sort of instructions and operations are allowed. And we're going to talk a little bit about where do the operands come from and where do the results go, and different machine models that people have built. So this is different instruction set architectures, and even more than instruction set architectures, because instruction set architectures talk about how do you encode instructions even. This is even a little bit more fundamental of how do you go about reasoning about how to move data from memory to the ALU and back, and how do you go and store the data close to the ALU. So let's start off with a very simplistic example here, a very simplistic processor that people have actually built. Believe it or not, you don't have to have registers in your processor, or you don't have to have named registers in your instruction set architecture. Instead, you can have a stack. A stack is just a storage element where you put things onto the stack, and then they come off in the order that was the last one that was put on that gets taken off first. Instead, in a very basic sense, we just take the top two things on the stack, we fetch both of them, operate on them, and put them on what would be the top of the stack. Building up from there, we can think about something like a accumulator architecture. So typically in an accumulator architecture, if you have one accumulator, so there's only one register, one of the operands for every operation you do is always implicit. It has to come from the accumulator. The other one, let's say, can come from memory. So you have to name one of the operands in an architecture like that. Building up from there, we can start thinking about maybe register to memory operations, where you'll name, let's say, the operand that is the source, let's say coming from memory, and you'll name, let's say, an operand coming from your register file. And optionally, you may even name the destination. So these are all options, and we'll call this a register memory architecture. Finally, we have something like a register architecture. So everyone wager guess here, how many named operands do we have here? 3. OK, yeah. And so in this picture here, we're going to take something from a register, something from another register, and we have to name where to go put it. So I wanted to point out here, actually, the number of explicitly named operands for some of these is a little bit more questionable than others. So as you can see here, we have 0. We have a little more complicated something where we have 1, 2, or 3. Now, why do I say 2 or 3 here? So some of these architectures or architectural models don't necessarily name the resultant or the result location. Some of them will implicitly name the result. So something like x86, for instance, the first source operand is always the destination. So it only has to name 2 things. Something like MIPS, or most RISC architectures, will actually name all 3. And you can think about that happening with both memory and a register-register architecture. So a good example of a 3-operand memory, which I don't have drawn here. I just have register memory drawn here, but memory, which basically says all of your operands come from memory and all your destinations are in memory, is something like the VAX architecture, which was popular in the 70s. You could actually have all of your operands come from memory, do some operation on them, and store it back into memory. So one interesting trade-off here is as you start to have more operands that are explicitly named, you need more encoding space for that. And this is one of the important trade-offs. OK, so let's go into a little bit of depth about a stack-based architecture. So some examples of this are actually the Burroughs 5000. The Symbolics machines were stack-based. And these are sort of machines from the past. There's a few modern or more modern examples of this. For instance, the Java virtual machine is actually a stack architecture. And then also Intel's old floating point system, x87, they've since sort of deprecated this, but it's still relatively modern. It was a stack-based instruction set architecture. Let's take a stack-based instruction set architecture and look at how you can go about evaluating an expression. So here we have an expression, a plus b times c, all in parentheses, that whole quantity divided by a plus d times c minus e. So it's some complex math instruction or math operation that we need to do. Here we actually break down this into a parse tree of this. So you can see this is preserving orders of operations. Well, we have a plus this subquantity here of b times c. And you take all of this and divide it by this sub-expression here. And a little bit of a throwback here. This is a way that we're going to take the operations, and if we do these operations on a stack machine model, we're going to get the right result. So what this means is put A on the stack, put B on the stack, put C on the stack, and then multiply B times C, and then add the result times A. And you can see that we're going to build this expression on a stack. So it's sort of a different way to sort of rethink about problems. And we'll walk through an example here. So here we have an evaluation stack. And the top of the stack is going to be whatever's on the top here in this picture. So first thing we're going to do is we're going to say push A. So A shows up on the stack. Then we're going to push B. We're going to push C. And then we're going to do a multiply. So we're going to take the two entries that are on the top of the stack, multiply them, and put them into this entry in the stack. And then we're going to say add, and it's going to add the two top things on the stack here and put the result here. And you can see that if you run something like this, you can actually do full computations on a very small stack. And what's also nice here is you don't have to explicitly name any of the operands. So this machine model allows you to run real programs. And one of the things I wanted to get across here is that the stack is part of the processor state. And it's usually, so that's the big A instruction, or big A architecture, or the instruction set architecture. You have a stack, and many times it's unbounded in the big A architecture, but in real life it needs to be bounded somehow, because you can't have infinitely long physical stacks in your machine. So it's conceptually unbounded, but you probably want to have it overflow to main memory if you put too many things on the stack. And this is an important characteristic, because otherwise there's certain computations you can't do. If, for instance, the parse tree is too long here, or the depth of the tree is too long, your stack might grow too long. OK, so let's say we have a microarchitecture implementation of a instruction set architecture, which is a stack-based architecture. And the top two elements of the stack are kept in registers, and the rest is in main memory, and it spills and fills. Well, each push has a memory reference. So when you put something on the stack, it has a memory reference. And each pop has a memory reference, because you need to put something back into main memory. But more so than that, you might have extra memory references here as the stack spills over into main memory and you might have to pull something back in from main memory. So that's not very good, because you might end up with a push having more than one memory reference. So one optimization from a microarchitecture perspective is you could think about having n elements of your stack in registers very close to the processor, and only have to go access main memory when the register stack overflows and underflows. So instead of having to do a memory reference basically every single time you do an operation or every single time you do a push or a pop, you do it only when the stack depth gets too large that you can't fit everything on your stack. So let's walk through a brief example here. We have the same expression calculation that we were doing before. And you can see we can do push, 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 multiply, add, push, 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 multiply, add, push E, subtract, and then do all the divides at the end. But if we have a stack size of 2, what's going to happen here is at the beginning, we're only going to, when we do a push, we're going to do a load from A, push, we're going to do a load from B. Now we do a push of load of C, but our stack already has 2 things on it. So when we try to push the third thing, we have to overflow the bottom of the stack somewhere. So we're actually going to do a stack save of A out to main memory. Here we do this multiply, and we actually have to do a stack fetch of A and get it back from main memory. So it's a lot of extra memory operations. So you might want to think of a different microarchitecture. And if you sort of walk through this whole example here, we're going to see that we have 4 stores and 4 fetches from main memory, which are all implicit, plus the explicit ones that we're trying to do with the pushes and the pops. Well, that's 8 extra memory operations. Can we think about how to build a microarchitecture which has less, but has the exact same instruction set architecture? Well, let's say we have a machine which has a stack size of 4. Well, if the stack size of 4, at the worst case here, we only ever have to fit 4 things on our stack. So we never have to spill out to main memory our stack. Pushes and pops still have to access memory, but that's what they're trying to do. They're actually trying to access memory. So to sum up here about stack-based machine models, they look pretty cool, but not all things are great at all times. So one of the interesting things here to see is we actually push A, and we push A again. So we're doing redundant work. And we push C, and we push C again. C and A had the same value both times we pushed them. So all of a sudden, we're doing extra work, and maybe we could have done less work if we had an architecture or a machine model, a big A architecture, which allowed you to store multiple things and name different operands. So what I want to get across here is, while a stack-based architecture is very simple, the instructions are very dense, it may not be good for performance because you might end up having to reload values multiple times. Versus if you had an instruction set architecture, something like MIPS, where you actually have 32 general purpose registers, and you can name any register for any instruction, you could have loaded A, B, C, D, and E all into the register space once, and then done all your operations, and never have had to reload. And this is actually an instruction set issue, and not, or a fundamental machine model issue, and not a microarchitecture issue. OK, so to summarize different machine models, we have our stack, accumulator, register and memory, and register, sometimes called load store architecture. If we want to take some expression here like C equals A plus B, we can look at the instructions that would have to be generated on an abstract architecture. So here we're going to have push A, push B, add, pop C. As we add more naming, we actually can potentially have fewer registers, or fewer instructions, excuse me. So we load A, add B. Note here we don't have to name what we're adding with because we're adding with the accumulator. And then store C. Start to get a little bit more compact. If we have register memory, we can load one of the values, add, store. It's pretty simple. If we have a load store architecture, we actually have to do a little bit more work. We have to load, add, store. But which seems inefficient, But if you have to reuse any of these values, A, B, you don't have to go reload them, versus in these two architectures, you have to go reload the value. OK, so now we're going to change off of machine model and talk about other aspects of instruction set architectures. And to talk about what else is in instruction set architectures, well, there's the fundamental machine model. How many registers do you have? What type of register access you have? Do you have stack-based? Do you have an accumulator? Do you have a register-register or a register memory architecture? Also, you need to talk about what the fundamental operations that you have, the fundamental instructions you have. So let's look at classes of instructions. You start off with things like data transfer instructions. So loads, stores, move to control registers. So this is what MIPS has. And in this course, we're going to be relying a lot on MIPS, the MIPS instruction set architecture, a lot for our example cases. But you have load, store, move to, and move from control registers with different control registers. You have arithmetic logic unit instructions, so things like adding, subtracting, anding, oring, multiplication, division. This is an interesting one here, set less than. That's kind of a fun one. It's a comparison operator. So if you want to take two values and compare and see which one's less than the other, you can use set less than. Load upper immediate. This is moving a value into a different location in a register. It's kind of like a shift operation. You can have control flow instructions. So do you have branches, jumps, traps? And one of the points I want to get across here is within or between different instruction set architectures, people make different choices about which instructions to have. Some people have very complex ones, some people have very simple ones, or some of the architectures have very complex ones, and some of the architectures have very simple ones. You can have floating point instructions, adding floating point numbers, multiplying floating point numbers, subtracting floating point numbers. These are actually compare operations. This is a compare operation, floating point numbers. So compare less than for doubles, or double precision floating point. Here we have conversion operations. So it's conversion from a single precision floating point number to an integer number, or integer word number. So this is a convert. This is the MIPS instructions. You can have multimedia instructions, or what's called single instruction multiple data. And we'll be talking about SIMD a bunch in this course later when we get to data parallelism and vector units. And this is actually an example out of x86 I wanted to give of stranger operations that sometimes show up as fundamental operations or fundamental instructions in instruction set architectures. This is an example called rep moves B. That's not two instructions, that's one instruction with a prefix and a space in between it. Yep. This is actually valid Intel assembly code. And what is rep moves B? Well, rep moves B is a string operation where it'll actually copy one string into another string. So if you have some text and you want to copy it to another piece of text, you can do reps move B and set up a number, and it'll actually copy. This is the moral equivalent of something like stir ncopy. So you can do that all in one instruction. So in addition to these complex string operations, things like rep moves B, we can see there was sort of old jokes about adding extra and extra instructions and having really complex instructions. So for instance, in the VAX architecture, they had instructions that could do very complex things. I think there was one that even did a fast Fourier transform in one instruction. That's right, a whole fast Fourier transform or across a huge data set in one instruction. So you can see that there's a lot of different choice between your classes of instructions, and the ISA architect, or the instruction set architecture architect, has to sit down and think about what should be in an instruction set versus being left out of an instruction set. Another characteristic of instruction set architectures that the architect needs to think about is how do you go and access memory. And what are the different addressing modes that can be used? So, or how do you get operands from memory? So looking at one example here, we have a register-based addressing mode. So in a register-based addressing mode, we can only name 2 registers and put them in another register. And this is a 3-operand format here. x86 would only have 2. But you can name register 3, register 2, add them together, and put them into register 4, for instance. And one of the interesting things here is this may not actually access any memory. We call it a memory mode, but it may not actually access memory. If you have enough register space and your implementation or your microarchitecture actually implements all the registers, then it won't go access memory. But it might access memory. So for instance, there are machines out there where you have a register, register, register operation or register, register, register instruction, but the processor has no register file. Everything is out in main memory. So it has to go read the data from main memory to go actually do the operation. And it just sort of caches or keeps the 2 operations that are needed. And it's all at the microarchitecture level. So this is all at the big A architecture level and asking what is the fundamental memory operations that can be done. So that's a register-based addressing mode. We can have immediate-based addressing modes. So here we have something like a constant of 5 being added to a register, put into another register. So here's our assembly code for that. You can have displacement-based addressing. So in displacement, we're going to take a register value, add it to some constant, and then take that and look up in main memory that location, and then do some operation, let's say with another register. But this is displacement-based, and it's called displacement because you can take a register and have some displacement off of it. You can have register indirect, and this is pretty common on something like MIPS, or actually if you go look at the Itanium instruction set, they don't have displacement stuff. They only have register indirect. So this is similar to the displacement, but you can't have a displacement. You can only go and read from a particular memory address that's stored in a register. You can have absolute addressing. This is actually not very common on most modern day architectures, but in the older machines this was common. So you can take memory and take a constant, not out of a register, and go look up in memory and then do some operation with that. You can have memory indirect, and this is kind of interesting way to denote this here. MIPS very much does not have this, but you could do a memory operation of a memory operation of a register. So what you have is in a register, you'd have an address, and then you would take that address, you'd look up in main memory, get the data, and that itself is an address, and then you look up in main memory again with it. So it's sort of a double index based off a register sort of addressing mode. And that gets pretty fancy. So if you look at something like VAX, they definitely had this. You can have PC relative or program counter relative or instruction pointer relative addressing. So you can take the program counter, add some displacement, and then index memory. This is very useful for position independent code or code that you don't know where it's going to be loaded. And if you want to go access some data close to where the code is, you don't know exactly where the code is loaded, but the program counter, because you know what instruction you're executing, you can basically index off that and find memory around where you are or around where you're loaded in main memory. So this is for PIC code. You can also have scaled. This is something that x86 has, where you can actually take a register and add it to another register multiplied by something else. So in x86, this is called SIB, scaled, index, and base mode. So you can actually take a displacement, add it to two registers, and multiply it. And this is very useful if you're trying to index through an array of some size. So if you have an array of 4-byte words, you can just keep ticking up this counter here. So you start off 0, 1, 2, 3, and as this ticks up here, instead of going up by a byte, you'll go up by 4 bytes at a time. And if the data you're trying to load is 4 bytes long, you'll actually be able to just pick up the exact elements in the array you want, versus having to do this multiplication someplace else. Usually these scaled operations or scaled memory addressing modes have very limited sort of multiplication here. You can't multiply by, let's say, 7. Usually it's sort of multiplication by factors of 2 or a small set of factors of 2, because that's easy. That's just a shift operation in base 2. And then you can think about data types and their sizes. So what do I mean by data types? Well, you can have binary integer. You could think about having different types of integer data. You could think about having unary encoded, binary encoded. You can think about having things that are sort of roll in different ways. So for instance, as you probably learned about in your computer organization class, there's 1's complement versus 2's complement arithmetic. And that's different data types there. So you have binary integer data, and saying whether it's 1's complement versus 2's complement is pretty important. You can have binary coded decimal. So this is where each digit is encoded with 4 bits from each decimal digit, if you will, is encoded in sort of the the period, if you will, is also encoded in there between your fraction and the integer portion, or the natural number portion. So your binary coded decimal can have different, very exact calculations for things like spreadsheets and business calculations. You can have floating point types. And there's actually a lot of different floating point types here. You can have, there's a standardization now that's called IEEE 754, which is what's used in most modern computers. And this was different than the Cray floating point on Cray supercomputers. They had a much wider floating point, and they also had different numbers of bits given to the mantissa versus the exponent. And by doing this, their precision could be different in different ways. So for instance, you could have a bigger range of numbers, but the precision smaller, or a smaller range of numbers with bigger precision, and there's different trade-offs there. Also, Intel internally, at least in x87, had this thing that they called Intel Extended Precision, which is 80 bits long. IEEE 754, the biggest thing defined in that is a 64-bit double. But if you want even more precision to your floating point numbers, you might need 80 bits. You can have packed vector data. This is like MMX data, where you're trying to pack the data all together and operate on it at the same time. So typically, things like MMX, you need to bring the data into a packed data type and then operate on that whole data type, so which has different values in it. And some architectures even have a special data type called addresses, which is different than a binary integer. So some older computers actually had address registers. And the address data type was different than the data type, or the binary integer data type. And that was different than the floating point data type. And there was different registers and different register names for that. And what was nice about that is they knew that if you loaded something into the address registers, it was definitely an address. So it had type information. And that's separate from the width. So let's say you have binary integer. Well, people have built machines which have 8 bits, 16 bits, 32 bits, 64 bits, all these different things as sort of the default word size. And then finally, one of the important things you need to do is come up with the encoding of the different instructions. And there's been a lot of debate on this of should you have fixed width versus variable width instructions. So let's look at a couple different ISAs and see where they fall, what camp they fall into. So most RISC architectures are fixed width. So you have MIPS, PowerPC, SPARC, ARM falling into this category. And as an example, MIPS, which we're going to be talking a lot about in this course, is every instruction is exactly 4 bytes long. And what's nice about this is it's easy to decode, but it may not be very compact. On the other side of this question about ISA encoding, you can see variable length instructions, where the width of the instruction can vary widely. So what's nice about this is you can have things that things that are very common take up a very small amount of space. So if you have an instruction which is like 1 byte long and it's always called, you could effectively do a manual Huffman encoding on your instruction sets. So you take the most common things and you put them in the smallest amount of data. But if you have something that's very uncommon, you can have it take a lot of bytes. So an example here, x86, you can have between 1 and 17 bytes for an instruction. I think this has actually been updated now. If you look at x86 64, it can be between 1 and 18 bytes. So, and a couple ideas here. It can be everything in between, 1, 2, 3, 4, all the way up to 18. And some CISC architectures. You have IBM 360 is a good CISC example of a complex instruction set architecture. There's x86, Motorola, 68K, VAX. These are all variable length instruction encoding architectures. And now we start to get into something which is a little bit fuzzier. There's things that sort of start to cross over. People started to look at, started to build mostly fixed or compressed instruction set architectures. So example of this is something like MIPS 16, which is effectively a MIPS instruction set where there is both 32-bit or 4-byte instructions and 16-bit or 2-byte instructions. And Thumb, which is the compressed or the mostly fixed instruction set architecture of ARM. Yep, gotta love the naming there. Also did the similar sort of thing where they had 2 bytes and 4 bytes as the different instructions. This is a little bit different than compressed. So this is like a mostly fixed architecture with sort of 2 different instruction sizes. If you look at something like PowerPC and some VLIWs, they actually have a compressed file, compressed format where they will actually store the instructions compressed and decompress them when it ends up in main memory, or ends up in the caches at least. So you can think of some architectures where the code in main memory is small, but then when you get to the cache, maybe it gets expanded or gets expanded when it comes out to the main processor. And then there's long instruction words where you actually can explicitly name multiple instructions happening at the same time, or even very long instruction words, or what's called VLIWs, which we'll be studying a bunch in this course, where you can put multiple fixed width instructions in multiple instructions in a fixed width bundle. So some good examples here are multi-flow, the LX architecture and also from STMicro. The LX architecture was from HP and STMicro, which shows up in printers today mostly. TI DSPs are actually VLIW architectures, and a couple other good examples. So just to show here something complex of how you can end up with 1 to 18 bytes. Here we have x86's instruction set, and fundamentally you need an opcode, a byte worth of opcode. But some instructions might have between 1 and 3 bytes here. And then there's different addressing modes, special information about different addressing modes, displacements, immediates about the different addressing modes, and those all take up more space. And then you can also have prefixes. So that rep in rep moves B is actually a prefix which says repeat this operation multiple times. You can encode all these things in a variable width instruction format like x86. And to give you an example of something like MIPS, every instruction on MIPS is exactly 4 bytes long, and they have to fit everything into it. So a ISA architect or instruction set architect has to decide the layouts of the bits within the instruction set, and that's usually something that's defined in the instruction set architecture. So to sum up some real-world instruction sets and where they fall with different numbers of operations, number of memory operations, data sizes, and registers, let's walk through a couple different instruction set architectures. And you've probably heard these in passing, but you may not have actually used any of these machines. But that's because some of them are embedded or some of them aren't commonly used anymore. But they're good to know about. So let's start off with Alpha. Alpha was built by Digital Equipment Corporation, and it's a register-register architecture with 3 named operands. There's no explicit memory operands in the instruction set. It's got 64 bits as the default data type. And when actually Alpha originally came out, you could only do 64-bit operations with it. That was sort of later changed as they figured out that might not have been the best idea. 64-bit addressing, and it was mostly designed for workstations, so big addresses, fast computers. Then you can see something like ARM. ARM is used in my cell phone. It's a architecture that there's a lot of different implementations of, and they've licensed it to lots of different people, but it's also register, 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 3 operands. There's a 32, and then now there's a 64-bit data size that has just come out. 16 registers, and the addressing, as I said, a 64-bit version came out, but it's mostly 32. And it shows up in cell phones and embedded applications. MIPS, which is an outgrowth of the Stanford MIPS project, and later was commercialized. Register, register, register. We're going to be focusing on this mostly in this class. Sort of similar. Workstation embedded. Spark is another instruction set. This is what Sun originally used or used to use. It was an outgrowth of the RISC-1 and RISC-2 sort of architectures. It has, well, this one's interesting, between 24 and 32 registers, depending on how you look at it. They have this interesting idea where as you load more data in, or as you do function calls, data gets spilled out into main memory and gets pulled back in from main memory, kind of like a stack. So it's sort of a mixture between a stack and a register architecture, mostly used for workstations. You can see the TI C6000 is more for DSPs. But then we can start to see some more interesting stuff down here. Let's take a look at VAX. So VAX is a memory-memory architecture where it has 3 named operands, or could have up to 3 named operands, and all 3 of those can come from main memory. Has a relatively small number of registers. We can see something like the Motorola 6800. This is not to be confused with the Motorola 68000 or the 68K. This is the 6800. Is an accumulator-based register, or accumulator-based architecture, where you can have 1 named operand that comes from memory. It's an 8-bit data path, and this is mostly used in a microcontroller. So why all the diversity in these instruction set architectures? Well, instruction set architecture is actually influenced by technology, or influenced by transistor technology. So we see that if storage is limited, we might want tight encoding. And on the flip side is if you have very small number of transistors, you might want to try to fit the entire chip on there. And this was the actually fundamental idea behind RISC. If you have lots and lots of transistors, you might not have to worry about having to shove everything onto a very small amount of area. You can think about adding multi-core and many-core, start putting multiple processors on there and build an instruction set architecture specifically designed for multi-cores and many-cores. And then also instruction sets are many times influenced by their applications. So a good example of this is if you're building a signal processing architecture or a digital signal processor, a DSP, you might want to add DSP instructions. And then finally, I want to talk about how technology from software has influenced instruction set architecture over time. So if we look at something like the Spark architecture, it has what's called a register window. So in the register window, what happens is whenever you do a function call, it'll actually take 8 registers and put them into memory, and then you get 8 new registers. When you do a return, it takes 8 registers from memory and puts it back into your register file and sort of swaps out the ones that were there before. And what this was at the time that Spark was made, compilers didn't know how to do register allocation. It was like an open problem. Since that time, register allocation, figuring out how to take a fixed number of registers and move data in from a stack in main memory and vice versa can be orchestrated very effectively and very efficiently by the compiler. But at the time, compilers were very simple, so people didn't know how to do that, so they needed hardware help to do that. So the instruction set architecture has that baked into it. But now that we have effective register allocation, we've not seen any other register windowed architectures come along after that. And if you talk to anyone who's actually went and implemented a Spark instruction set architecture, microarchitecture, they basically hate register windows. It's like the bane of this architecture. But at the time, compiler technology was not good enough. So applications influence it. Compiler technology influences your instruction set architecture. Technology influences your ISA. And ISAs have evolved over time, even though, as we said originally, a lot of times people want to build ISAs that don't change, so you can keep running software and have binary compatibility. But at some point, it might make sense to actually break that compatibility and re-optimize your instruction set architecture. So to recap, this is ELE 475, or a computer architecture class. We're going to be focusing on abstraction layers and talking about instruction set architecture, microarchitecture, register transfer language, and a little bit into operating systems and a little bit down into gates. But we're really trying to harness technology and bring it to applications, or bring it into what humans want to accomplish. Today we talked about ISA, or instruction set architecture, versus microarchitecture, or big A architecture versus microarchitecture. And we talked about some ISA characteristics, including machine models, encoding, data types, what sort of instructions you can have, addressing modes, and encoding. Next lecture, we're going to start off by talking about microcode, and then move into our first review lecture, which is review on how to build pipeline processors, or review on pipelining. So I'm going to end here and thank you all for listening. OK, so today we're going to start our third installment of ELE 475 computer architecture. And this is going to be more review, and we're going to finish up talking about hazards. And today we're going to be talking about control hazards. And then a little bit later, we're going to start talking about caches and why we have caches. So let's start off by looking at control hazards. And just to recap, the the three different types of hazards we've talked about in this class so far. We were talking about structural hazards, data hazards, and now we're going to talk about control hazards. OK, so what exact information do we need to calculate the next program counter? Well, is it the same thing for every instruction? When we go to execute an arithmetic logic instruction, an add instruction, do we need the same information to calculate the next program counter? You might say, well, isn't there some piece of magical hardware which just calculates the next program counter? Well, yes, but we need to talk about what that magical piece of hardware is. So as you might guess, it's actually different for branches and jumps than it is for sort of more traditional instructions or arithmetic logic instructions or everything else. So let's start off by looking at jumps. So if we look at a jump, you need to look at the opcode to make sure that it's actually a jump. You also need to look at the offset within the instruction. And you need to look at the current program counter. And you take that all together, and you're like, oh, it's a jump. The decoder says it's a jump. The decode pipe stage of your processor says, OK, it's a jump. And then you can take the program counter, add it to the offset. And you probably need to do that either in the ALU or if you need a special adder to do it. And the pipelines we've drawn so far on our 5-stage pipe, we had a special adder just for that. And you do that offset calculation. And then you want to go and vector your machine so that the next instruction you go to execute is at the target of the jump. Now, this gets a little more complicated when you start to look at jump register. So jump register you don't know where you're going until you go decode the instruction, fetch the information from the register file. Conveniently, at least you don't need to do some conditional calculation, but you will down here. But we're just going to have to look at the opcode to know that it's a jump register. We don't need to look at any offset because we are jumping directly to a register value in something like MIPS. In other instruction sets, you might need to look at other sorts of information. So you might have, for instance, a register indirect jump register type of instruction, or even a memory indirect jump sort of instruction. Conditional branches, now things start to get a little more complicated. We need to look at the opcode. We need to look at the current program counter. We need to go look at the register, which is going to give us the condition. So we're branching based on whether some value is, let's say, greater than or less than 0. OK, so we need to go look at that. But we don't really know that until quite a bit farther down the pipe. And we also need to take the offset and add it to the program counter when we do a PC relative conditional branch. That's how it's defined in MIPS. In other instruction sets, you can have different types of conditional branches, either a absolute addressing scheme or something where it might be register, register, indirect, or some other thing like that. But for MIPS, we're just going to take program counter, add it to our offset, and branch that if the register is the register or the condition is what we're looking for. If not, you want to just fall through and go to PC plus 4, or the next instruction, if your instruction is 4 bytes long. OK, everything else. Believe it or not, we do need to actually think about this case. It's not some magical piece of hardware. We're going to discuss this magical piece of hardware today. You need to take the opcode, and you need to take the PC, and you need to add some constant to it to compute that you want to fall through to the next instruction. So, when we're looking at this, we might have to look at the program counter, but we also have to look at information which comes at different stages in the pipeline. The opcode doesn't get decoded probably until something like the decode stage. Registers don't get fetched, let's say, until the instruction register fetch or decode stage. And for condition, you may even need to do some comparison with 0 or comparison with another register. So you need to do some math or run it through your ALU in your execution stage. Something like jump register is similar there. You're not going to know the destination until maybe once you've gotten to the either execute stage or possibly way, way at the end of the decode stage. So let's take a look at a basic control hazard. And the basic control hazard is we want to execute an instruction, and we want to fall through to the next instruction, which sounds pretty basic, but you would say, why is there any structural hazard there? We're not changing the control flow. So let's draw the pipeline diagram. Assuming that we have no branch delay slots in our architecture, we'll talk more about branch delay slots in a second. Let's draw a pipeline diagram here. So we're going to plot time, and then we're going to step through a basic instruction sequence here. And this basic instruction sequence, actually, let's start here. We're going to have instruction 1 and instruction 2. Instruction 1 is taking some register and adding it to something else. We talked about there being data dependencies or data hazards. In this case, there is no data dependence and no data hazard here. You'll see that this is writing to register R1, and this is reading from register R2. So there's no data hazards here. We just want to look at the control hazard. The first instruction just goes down the pipe, fetch, decode, execute, memory, write back on our 5-stage MIPS pipe. The second instruction starts going down the pipe, and it first goes into the fetch stage. But the problem here is we actually need to stall the fetch stage, or we need to, because we don't know that the second instruction is the second instruction yet. For instance, we don't know that this first instruction is not a branch or a jump. So we don't know the address of the next instruction. That's kind of odd. Now, why do we not know this? So going back to this example here, one thing that's common through all of these different cases is they all need to decode the opcode. Well, where do we do the decoding of the opcode? We don't do that until the decode stage of the pipe. So we don't do that until here. And we're not able to use that information until the end of this cycle, which would be sort of here. And we would need that information to determine what's going on here. So if we had a branch, for instance, here, where it's not able to get around and change the program counter and change what is being indexed into the instruction memory on this cycle. So what we're going to have to do is we're going to have to insert a decode bubble here for this structural hazard. Now, if we sort of play this forward for more instructions, what you're going to realize is this is not very efficient. Every instruction that goes down the pipe is going to hit a control hazard. And every instruction that goes down the pipe, you're basically going to hit this decoding hazard. And every instruction now takes 2 cycles. So your clock per instruction for this is not going to be very good. Let's analyze that now. So we can draw this in the other pipeline diagram axes and see that what's happening here is let's take the execute stage. We're executing instruction I1, then we're no-opping instruction I2, no-op, I3, no-op. And you compute this all out, you end up with a CPI of 2. So your machine is running at strictly half the performance that you want it to run at. Well, that's not very good. So let's start to talk about some techniques to mitigate the effect of control hazards. And we're going to actually have a whole lecture later in the course about branch prediction, which is one of the main techniques in order to mitigate control hazards. But let's move forward here and take a look at one of these techniques. And this technique is speculation. So what's the solution to this? So the most basic solution is we actually speculate that the next address is going to not be a branch. Or the current instruction is not going to be a branch. The next address is going to be the PC plus 4. So what does this look like in a pipe? Well, there's this nice adder here. We're going to take the PC. And if nothing else is happening sort of later down in the pipe, we're just going to be selecting PC plus 4 on this control path here. So we're just going to be sort of walking down here. We're going to be executing 96, 100, 104. And we're not actually going to even look at the instruction until, let's say, something else more interesting happens. So we can just speculate that the next address is PC plus 4. So that's great, but that adds some wriggles. What happens when we have like a jump here? So this jump, if we speculated PC plus 4, we went and fetched instruction 3 here, which is at address 104. But the jumps says we're supposed to go to 304. So this instruction is not even supposed to execute. So we need some mechanism to kill instructions in the pipeline, kill live instructions in the pipe. So how do we go about doing this? So let's look at a brief example here. So we need some way to kill an instruction. And what we're going to do is we're going to add a multiplexer here, which will multiplex in a no-op. And if we have a jump that gets to the decode stage of the pipe, we're going to wire back in and say, oh, that instruction that we just executed, or that instruction we just fetched, this one here, it's not actually supposed to go down the pipe. We should kill it. So we're going to swing this mux, and right at the end of the cycle, we're going to say, no, it's actually a no-op. We're going to insert into the pipe, and we're going to redirect this multiplexer here to the actual jump location. And this is what I was talking about before about the extra adder here. Here's our extra adder, which is computing our destination. And sometimes people try to sort of put these two things together, but we're going to take part of the instruction, and we're going to take the current PC and add to that, and that's going to compute our new destination of the jump. Yeah, sorry. So here's the control on this mux. We just have to look to see if it's a jump or jump and link, and then we insert a no-op. Otherwise, we actually take the thing coming out of the instruction memory. So let's look at this sort of as things flowing down the pipe. If we have instruction 1, the add at the beginning of the execute stage, instruction 2 here now in the decode stage, and we just fetched 104 out of the PC. As we go forward one cycle, we're going to actually take what we took out of the instruction memory that was 104, and we're going to kill it and put a no-op in its place. The jump is now entering the execute stage. The add is entering the memory stage. And we've redirected the front of the pipe here, and we're actually fetching now the destination of the jump, or the instruction at 304. So important question pops up here on the screen. What happens if we have a stall and a jump in the decode stage at the same time? Are there interactions here that we should be worrying about? That's a tricky one. Well, the first question is, what is a jump? What are reasons that a jump would actually stall in the decode stage? It's not a whole lot. In a basic pipe, probably a jump would not actually stall in the decode stage. In more complex pipes, there are sometimes just stall signals that say there's some big structural conflict later in the pipe. Just stall the whole rest of the pipe. So it is possible for things to stall. One important thing is that in a very simple pipe like this, if you have a stall, let's say there actually is some reason this jump is stalling, and you have a jump in that stage, what happens? Sort of, do we kill the instruction? Do we let it go forward? Both of them are actually possible to do. More complex pipes might even think about actually allowing the jump to happen and sort of squishing out any no-ops that get inserted later on in the pipe. And let's look at that from a pipeline diagram perspective, because that might shed a little light on this. And instead of drawing this instruction as continuing down the pipe, we're just going to put no-ops here, or dashes there. So the first instruction goes on the pipe. The jump goes on the pipe, doesn't stall on anything. Because we have the PC plus 4 speculation, there's no stall here. This add gets fetched, but doesn't ever make it into the next stage of the pipe, because it gets killed. Then we have the next add, or the target of the jump, showing up, and we go and execute that. And if we look for the resource utilization, we can plot it the other direction. You'll see the no-op moving forward in pipe stages over time. Let's look at a little bit more complicated case. We talked about control hazards due to jumps. Let's put the control hazard one cycle later. And a good example of that is something like a conditional branch. So here we have a piece of code, add branch, and it's branching to 200 bytes into the future. If you take 100, branches on MIPS are relative to the subsequent instruction, so it's PC plus 4 plus the offset, so we're going to end up at 304. And let's walk through this case here. We have I1 is our first add. We have the branch sitting at the decode stage. And we have some decode logic, which is saying, is this a branch? OK. The next question, though, is how do we compute whether this is a branch is being taken or not? Can we do this in the decode stage? Unfortunately, we need to do a comparison here. And this comparison, the hardware we want to use to do the comparison is in the ALU. It's a subtract operation. or a comparison operation. So this fits well within our arithmetic logic unit. And we have the 0 wire coming out. So what this is going to do is instead of having one cycle of latency or one cycle of kills being inserted, we might have to insert 2 cycles. Because now we have to wait for the branch to get to here. And if we are predicting PC plus 4, we're speculating PC plus 4, we will actually have fetched more data. So let's walk through this. So the branch moves forward 1 cycle forward here. And what you'll see here is we're actually fetching 108. So we're fetching the next instruction. But these two are both potentially dead. We want to kill both of these. But we don't know whether to kill them until we get this 0 wire here. OK. So at that point, we can redirect the front of the pipe, and we can insert a no-op. So that's going to change the logic that connects to here. We're also going to have to insert a no-op here because we fetched 104 at that time into this point of the pipe. So if a branch is taken, we need to kill the next 2 instructions. And the instruction at the decode stage is effectively invalid. So we need to swing this mux here. So we're going to have to add an extra control line onto this multiplexer. And now, stalling and killing makes a lot more difference. So the stall signal has to effectively be killed or nullified at this point. And why is this important? Well, let's say we're stalling the front of the pipe and stall were to take priority. That would stop this register from moving and stop this register from moving as this red lines come in. So if the stall were to take priority, you could have an instruction here, which is, let's say, dependent on some stall condition or dependent on some data hazard or dependent on some random hazard. And you have a branch which is branching to someplace else. So let's take this instruction here, 104, which is an add, is dependent on something that's stalling the front of the pipe. But at the same time, you want to kill, because you took the branch, you want to kill that instruction. If you were to put the stall at the higher priority, you would actually end up with a deadlock, because you'd be stalling, but you would have no way of killing the previous instructions to clear the stall. So this is why it's really important that the instruction at the decode stage is now invalid. So unlike the jump case where, well, you might be able to do either way with the priority of the stall and the kill wires, here the kill has to take precedence, or the redirect has to take precedence. And that's going to redirect the front of the pipe and basically clear out everything here. And if you were to stall it, you would not be clearing it out. So instead, you need to kill, sort of turn these all into no-ops, and redirect the front of the pipe to go fetch the actual target of your branch, of your conditional branch. Yeah, sorry. This is just drawing now that this branch information has to go into this multiplexer and go into this multiplexer. The other thing that's important here for branches is we need to figure out the address that we're actually branching to. And we'll talk about this more when we get to branch prediction later in the course. But what you're going to have to do is you have to take the PC plus 4 and add it to the branch offset. Because on something like MIPS, there's PC relative branching. And the other thing is we can't reuse this ALU necessarily to do that. You could potentially reuse this ALU if you were microcoding your design. But unfortunately, we need this ALU to do the branch comparison. So we need to add another adder here to come up with the target of our branch. Now, some people get smart on the way they build this. And you can actually see some things where people will try to reuse the main processor pipeline ALU to do the branch offset calculation, and maybe try to do this comparison, because if you have simple enough branches, you can do the comparison with less hardware than a full adder. That's another option. Let's hold off talking about that until a little bit later. OK, so now we get to talk about the stall signal in detail. So we start off in blue here at the top, the stall signal we had from before. So you need to check the data dependencies and check for data hazards between the registers of the source operands. These are the R, S, and RT in the decode stage against the other stages in the pipe, the execute stage, the memory stage, and the write back stage, and make sure that you're both reading the registers and you check the write enables to make sure that the respective instructions in the different pipeline stages are actually writing to the different locations. But now we add another term. We add a branch term. So we need to know whether there's a branch going on here, because we need to unstall the processor if the branch is taken. So we're going to add not. And this is effectively, it is a branch 0 and 0. Likewise, it's a branch not 0, and the value is not 0. So these two terms are basically saying a branch is happening, it's in the execute stage, and we'll say that the branch is being taken. So if it's a 0 branch and the result is 0, it's taken, or if it's a not equal 0 branch, it's not taken. And why don't we stall if the branch is taken? So it's the same question we had on the previous slide. You have a branch, it's happening. If we stall the front of the pipe, the instruction of the decode stage has to be unstalled to get that out and to clear it out. So the instruction of the decode stage is now invalid, so we don't want to pay attention to any of the stall information. It's just like a red herring, or it's a piece of information you shouldn't be paying attention to. So you want to have the instruction of the decode stage be turned into an invalid instruction. OK, so now we get to talk about the control equations for the program counter and the instruction register multiplexers. So let's start off by talking about PC source. And so I want to remember what that is. That's way up here. It's the input to this multiplexer. And that's going to select where we're branching to, or excuse me, not necessarily where we're branching to, but the program counter of the next instruction we're going to fetch on the next cycle. And it's on the next cycle because this is a flip-flop. So a little bit of control equations here. Just I wanted to point sort of two basic things out in this these equations, is that the older instruction, or the thing that's farther down the pipe, is going to get precedence over younger instructions, and for the control signals going down the pipe. So if we look at this PC mux select, it actually has things coming out of different stages of the pipe. We have something which is redirecting for a jump out of the decode stage. And then we have these signals here, which are coming out of the execute stage, which is strictly farther down the pipe. And this needs to take precedence over that. So if you have a branch which is directly followed by a jump, the jump's going to be sitting there trying to sort of swing the control on the PC select mux, or the next program counter mux. And you can't let that happen. You have to let the branch that's actually executing take precedence over that. And that's really what we wanted to get across from this. And you'll see that similarly here, the branch takes precedence over the jump and link for the other control signals. Let's look at this from a branch pipelining perspective. So we'll draw the pipeline diagram for a branch executing for our example. And what you're going to notice real fast here is if you take a branch and you actually execute the branch and take the branch, you're going to be adding 2 extra instructions here, in this case 104 and 108, and they get killed as they go down the pipe. And this is going to impact our CPI in a negative way. And what's happening is this execute, the branch which is in the execute stage, is going to reach back and kill these instructions inserting the no-ops. And we can plot this in the other dimension also, but you'll see. So now we need to think hard. Is this a good thing? Well, we speculated that the instruction was, or the next instruction was going to be PC plus 4. Or the address of the next instruction was going to be PC plus 4. So we took something where the CPI was, let's say, 2. A machine with a CPI is 2. And we cut it down a little bit in the common case. But jumps, the CPI still goes back up to 2. And here, the CPI is 3. Now, in our speculation case, or our no speculation case, if we had a branch, we would probably have to stall for 3 cycles anyway to know the destination of that branch. So this didn't really hurt us in that case. The CPI in that case was also 3 for a branch instruction. OK, well, but this still isn't good. I don't want every single branch I take to have a CPI of 3. So let's talk about some ways to mitigate this cost. Or how do we reduce the branch penalty? Well, one way to do it is we can actually add a comparator 1 stage earlier and have it resolve in the same timeline as something like the jump. So how do we do that? Well, here we have our register file. This is in the decode stage of the pipe. This is the fetch stage. What do we really need to do for a branch? Well, we need to know that it's a branch. So we do some decode. And we need to know whether it's a branch 0 or a branch not 0, for instance, if those are the only 2 branches in our architecture. And we need to know that, let's say, register 1 is 0 or not 0. So some people came up with this smart idea that we can add a 0 detector onto the register file output. And by adding the 0 detector into the register file output, we'll know which way the branch goes. So this 0 detector, one of the interesting things is this is actually a little bit easier than doing a full comparison with 0. Because to do a 0 detect, you can basically build a optimized OR tree and then either take the negation of it. And sometimes people even do this with sort of wired ORs or more analog-y circuits. But this is effectively a big OR gate where you OR in all 32 bits if you have a 32-bit processor, and then take the NOT or take the bit itself. And this is easy for 0 detect. This can get harder for different types of branches. If you have something like a branch equals or BEQ instruction, you can't use 0 detector. What you have to do instead is somehow actually do a full comparison between 2 of the source operands. And that usually takes more time. So the nice thing about this is that it'll take all your branches and take them from a CPI of 3 when they mispredict or when you misspeculate to 2 cycles with the same timeline that you had with a jump. So you end up with the exact same pipeline that we had for jumps now. The downside is that this is going to elongate your cycle time, because you have this wire coming out, and the wire needs to go into the logic which computes PC source, and this can become a critical path. And it's a critical path because you have to go through the decode. That's usually done in parallel, but you have to access the register file then go through a zero detect, and then go into the control logic, which computes this, and then come around and latch the information or flip-flop the information. So you can really negatively impact your clock period. And as we talked about the iron law of processor performance, you can either get performance by lowering your clocks per instruction, or you can get it by lowering your clock frequency. Or excuse me, increasing your clock frequency or lowering your clock period. So these two things trade off. So you can elongate your cycle time, which will negatively impact your CPU, negatively impact your performance or time per program in our iron law of processor performance. But on the flip side, you will have branches resolve faster. So your clocks per instruction or your aggregate clocks per instruction, especially for branches, will go down. So this is only one approach. Another approach is you can expose it to software. So we can change the instruction set architecture. And what's really cool here is the instruction set architect can actually have an impact on what's going on here. This is not all microarchitecture issues. It's not all fancy branch predictors, as we'll be talking about later in this course. But instead, you can expose this problem or this challenge of the time it takes to resolve a branch to the software. So what we're going to do, well, I'll define a branch delay slot. And a branch delay slot is a architectural, when I say architectural, I mean big A architectural or instruction set architectural change, which allows or forces some number of instructions after a branch to always execute. So it could be, let's say, 1, 2, 3, or 4, some number architecturally defined. And in this delay slot, that instruction is executed irregardless of the direction of the branch. And what people try to do with this is they'll try to take work that was above the branch and move it below the branch. Because if you know the work's going to be done anyway, you can just put it below the branch and everything's OK. But the problem with that is the branch has to not be dependent on that work that you're moving below the branch. So typically, for very short loops, where there's not much work inside the loop, this becomes very problematic, because there's not enough work that the branch is not dependent on to move below the branch to have the loop run effectively. And what we're trying to do here is the compiler has a hand in what's going on, or the program writer really has a hand in what's going on, because that's what's doing the reordering of the information from above here to below here. So let's take a look at an example here where we have a branch and we have one delay slot. Some architectures have 2 or more, but right now we'll assume one delay slot. And let's also assume that we have this reduction of branch penalty optimization. So now branches only have one dead cycle when we're going to execute them. So what we can do is we can say, OK, the branch is at address 100. And this add here at address 104 in the delay slot executes irregardless of whether the branch gets taken or falls through. So then we don't actually have to kill the next instruction after the branch. We don't have to have all this fancy extra hardware there. We can just have this always execute. The tricky thing is many times, as I said, it's hard to fill this branch delay slot. It'd be great if you could have many, many branch delay slots. So if you go look at something like a Pentium 4, I think they have a 20-odd cycle mispredict penalty. They could have added 20 delay slots to their architecture. That would have been really, really cool, but at the same time, the compiler would have to go find 20 instructions for every branch to stick after the branch. And there's usually just not that much work to be put after the branch, which the branch is not dependent on. So we have a really hard time filling these branch delay slots. And roughly, if you go look on something like MIPS across sort of old spec ints, to give you some example here of how often the compiler can actually fill branch delay slots, I think the rough rule of thumb is if you have one branch delay slot, you can usually fill it maybe about 70% of the time on something like spec int. Spec int is a common benchmark suite that's used throughout the computer architecture industry or the computing industry. to measure performance. And if you have 2 branch delay slots, that second branch delay slot only gets filled less than like half the time. So if you're only filling these slots relatively infrequently, you might be better served by coming up with other prediction mechanisms. And we're going to talk later in class about, not this class, but in a different lecture, branch prediction, which is a technique to cover branch latency and to make a branch decision early, where we can predict whether the branch is being taken or not taken. And this can be used to dramatically reduce the branch penalty. So let's draw the pipeline diagram here of a branch delay slot. Or architecture has 1 branch delay slot. So we have the add flowing down the pipe, we have a branch flowing down the pipe, and now we're going to have this next add, and architecturally we've defined that always executes whether the branch is being taken or not taken. So this code sequence, or excuse me, this pipeline diagram sequence here is the same for whether the branch is taken or whether the branch is not taken. In this case, we're going to say that the branch is taken, and we go to execute this next add here. But you see that there's no bubbles. There's no no-ops being inserted. So we've actually improved the performance here. This is assuming, though, that this add is doing useful work. Now, this is really important to say, because the compiler or the program writer has to put something here. And if they can't put anything useful, they're going to have to put no-op. And that's not useful work. Doing a no operation, you might as well just have had the hardware insert the no-ops for you and save some instruction coding space. So there's tough trade-offs here between how often you fill the branch delay slot versus having a branch delay slot. But for right now, we'll say branch delay slots are one good technique to put useful instructions after a branch and not have branches stall a lot. OK, so we're almost to the end here of control hazards. Let's talk about why an instruction may not be dispatched every cycle. Well, let's think about forwarding and full bypassing. This is sometimes really expensive to add. If you're trying to bypass out of every location in your pipe, that may be expensive. So we may still want to stall in certain cases. A good example of this is if you go look at a modern day, something like your Core i7 machine. They actually don't bypass between all the different functional units from all the different locations, because they can execute about 6 instructions per cycle, and they have many stages in the depth of their pipe, so they'd have to basically be bypassing out of 100 different places for every new source operand. So what you typically will do is you'll figure out what are the common bypasses that are needed, or the common forwarding paths that are needed, and you'll have those. And then some of the infrequently used ones, you just won't build. This will help with your cycle time, but hurt with your CPI. Loads can have or typically have a 2-cycle latency. So we talked about this when we were talking about load to use. And the instruction after the load cannot necessarily use the result, or definitely cannot use the result, because in our 5-stage MIPS pipeline, the result is not computed until the memory stage. So if you're in the execute stage, you would not have been able to get that, even if you had bypassing out of the end of the load. End of the load pipe, or excuse me, end of the memory stage. And one interesting thing is that the MIPS 1 architecture actually defines load delay slots, very similar to what we have in what we had discussed with branch delay slots. So MIPS1 had load delay slots, which were software visible slots that you had to fill and could solve basically this pipelining hazard. And the compiler would have to schedule some non-dependent instruction. So it was an instruction which was not dependent on the load into that spot. This was ultimately removed out of the ISA, and stalling was put back in, because as you went to sort of different pipeline lengths and different microarchitectures, this started to be onerous. And this is really one of the big problems with both load delay slots and branch delay slots, is it's not very microarchitecture independent. So as you change to different microarchitectures, if you had, let's say, a pipeline length of 5 and it went to 4, all of a sudden maybe you didn't need that branch delay slot or something like that. And I wanted to sort of point out here is this idea here really is encapsulated in the name MIPS. It stands for microprocessor without interlocked pipeline stages. So they really did not want to have interlocking here on something like the load to use of that. And later in MIPS2, that was removed and pipeline interlocks were reintroduced. So we could all find mistakes that we have done and have changed it. But in the original MIPS1 ISA, they had load delay slots. Another good reason why CPI might be greater than 1 is we have conditional branches, which can cause bubbles. So this was all the control hazards we've been talking about up to this point. And you have to kill the instructions if you don't have some sort of delay slots. Now, I wanted to point out here when we talk about CPI, and this is this note at the bottom of the slide, is that you really want to think about CPI from the perspective of a usable CPI instead of how many instructions are executing. So if you are adding no-ops to your program and the no-ops are not doing anything useful, that should not go into your useful CPI calculation. Your machine might count that as valid instructions going down the pipe because it was software visible instructions, but that's not a good solution. When you should be computing CPI, you should always be thinking about useful CPI or CPI that's actually towards the end goal of the program. A couple other control hazards that we need to talk about in this course are other things that can change your control flow of your program. And those largely can fall into two different cases here. Exceptions and interrupts, and they're both related. And let's talk about what an exception is. So an exception is something where you have an instruction, and the instruction does some operation which is invalid or against what the intended use of the machine is. So a good example of this, there's a couple good examples, is you divide by 0. You take some value, divide it by 0. Well, on most computer architectures, this is ill-defined or undefined. So you'll actually get an exception, which is a divide by 0 error. And you can go try this out. If you go log into your computers and go write a little C program, take some number, divide it by 0, you're going to get a div by 0 error if you're running on Linux, and get something similar if you're running on Windows. And another good example of exceptions is things like a memory fault. You're trying to access memory you're not allowed to go access. There's some underflow and overflow exceptions in certain architectures if like number precision goes out of whack. If you have a floating point number which becomes too large or too small, and the floating point arithmetic can't handle the precision, you'll sometimes get underflow and overflow exceptions. And then interrupts are external things happening. And what's so something like a timer tick going off or an I/O device trying to wake up your processor or do something to your processor. And why these are important, why these are control hazards, is these are unexpected things sort of coming into the instruction stream. And it's going to change the subsequent instructions that are executing. So there is really a control hazard. It's changing the program control flow. And we're going to be talking a lot more about exceptions and interrupts later in this course, but I just wanted to get this idea across in this review so far that exceptions and interrupts are different types of control flow hazards. Let's start off our third topic so far in our review of computer architecture. So this is still review at this point. As I said at the beginning of this class, if you know everything up to this point in the class, that's a requisite or a prerequisite for this course. We're just trying to blow through everything you should know in order to start the much more detailed content later in this course, where we talk about real processors you're going to be building. So things like out-of-order, multi-issue, multi-core microprocessors versus simple little processors you should have built in previous classes. So this is ELE 475 at Princeton University. We're talking about computer architecture. And today we are going to be reviewing caches. And this is the last topic, cache review, as I said before we move on to new material. And the new material we're going to be moving on to very soon is superscalars, or processors which can execute multiple instructions per cycle. So let's take a look at the agenda for the cache review lecture. We're going to start off by talking about memory technology and motivate the different so we're going to start off by talking about memory technology and use that as a motivation for caches. So we're going to look at different types of technology, DRAM versus SRAM, what the transistor technologies are behind them versus, or why we have these different memory technologies. Why don't we just have one? Why are there different ways to store information? Why do we just not use register files for everything or simple flip-flops for everything? Then we're going to motivate cache design, or why we have caches. So let's define what a cache is. A cache is a little piece of memory that you stick next to something which does not have all of the information that you're trying to store. Instead, it has a subset of that information, and hopefully it has a useful subset of that information. We're then going to talk about classification of these different caches. So we'll put names and labels on sort of different cache architectures. So we're going to talk about associativity of caches. We're going to talk about size of caches. We're going to talk about whether the cache has multiple things that could fit in one set or not. And we'll talk a bunch more about that. And then we'll have a very, very brief introduction to cache performance, or some of the things you should know about why caches give you good performance right now. Later in this course, we're going to actually have 2 more lectures about advanced caches. In advanced caches, we're going to talk about more sophisticated topics with how do you build and implement actual caches for very high performance processors. So let's start talking about memory technology. OK, so let's look at a memory, or something that can store multiple values and give us back some data. So here we have a very naive flip-flop-based register file. You'd probably never actually build this in a modern microprocessor. But let's look at the sort of conceptual idea here of what a memory really is. Here we have 4 entries that are flip-flops. Maybe it's multi-bit wide. So it's maybe, I don't know, let's say each of these registers are 32 bits wide, and each of these buses here is 32 bits wide. And we're going to sort of select, based on a read address, some value. So we can choose, this is 2 bits here. We can choose out of one of 4 places. We have write data that comes in, and we just sort of broadcast that to all of the registers. And we write depending on the write address here and the clock. And if the decoder tells us to light this up and the clock clocks the actual element, it'll load in the value. You may even have a write enable on something like this, where that would also feed, let's say, into the AND gates here So it'll say, if a write's not occurring, don't actually load anything into these registers. OK, so that's really, really naive. Let's look at something a little more complex and how these things sort of start to actually look. OK, so now we're going to transition from talking about this naive register file and see what people actually build. And the first thing you should realize is, if you go to build something that's a naive register file, you have lots and lots of bits as you add more and more bits here. Here we only have 4. But if we go to a 1,000-bit register file, this multiplexer grows really big. And if you stack these all up, 1,000 long, your aspect ratio, your x versus y, or the size when you go to lay it down on a piece of silicon, is very long and very narrow. So you'll end up, let's say, with 1,000 bits, 1 bit tall. And that does not lay out very well, and it's not necessarily good for speed or from an area perspective. So why is it not good for speed? Well, it's not good for speed because wires have costs and take time to propagate. So if you have to propagate from 1,000 bits away or 1,000 bit cells away all the way over to the multiplexer, your cycle time is not going to be very fast. Versus if you were to somehow make it more square or more rectangular, the distances actually are minimized. So this is how we end up with arrays, or memory arrays. And we're going to look at a memory array for a register file first. Let's look at a register file array and how you could possibly actually go build this, because it's a little bit different. We're not going to use fully complementary logic here for everything. Instead, we're going to start to transition to something where we will have more of analog circuits connecting our bits to respective buses. And we're also going to change how we do the decode. We're not going to have a full multiplexer here or a full decoder here. We're going to split that into different portions. So here we have an example array. It's a square. And each of these little boxes is a single storage element bit cell. And the address comes in here. And that goes up into a row decoder, which will turn on one of these wires at a time. And these are called word lines. And we'll have both read word lines and write word lines. And this is still just for a register file. But we're actually going to split out some of the bits here of our address and send it over to here, which is the column decoder. And that's going to choose, this column decoder is just a multiplexer very similar to this multiplexer, but it's going to only have a subset of the bits. Instead of having all of the bits that are together here going through this multiplexer and having n-bit address coming into it, it instead has a subset of that. So in this diagram here, we have a 4-bit wide readout or write. And we're going to have 1, 2, 3, 4, 5, 6, 7, 8 bits in bits across here. So we're going to need a 2-to-1 column decode. So this is a 1-bit decode here. But this is just a toy example. As we go to build sort of 1,000-bit arrays or megabyte arrays or gigabyte arrays or gigabit arrays, we're going to have lots of bits coming here and lots of bits there. But the idea I want to get across is you split off a portion of the address to the word line creation and a portion of the address to your column decode here. And in this register file, I wanted to just sort of walk through what this diagram over here, the circuit level diagram is. Here we have 2 cross-coupled inverters. And as you'll see, we don't have full complementary logic connecting these two things. But this is a stable storage cell. If you give this power, it'll store data. If we want to do a read, we need to connect the output of this to read bit lines. And these read bit lines are these vertical wires running here. And we're going to do this with effectively a pass gate here. When we energize the read word line, it connects the output of this gate, or output of, it's going to be this inverter here to the read bit line. And if we want to do a write, we're going to turn on not the read word line, RWL here, but we're turning on the write word line, WWL. And what that's going to do is it's going to connect both the Q and Q bar to the write bit line. And now we get into sort of some analog magic here. But in order to have this work, what we're going to do is we're going to we're going to energize or ground the write bit line such that it's stronger than what's going on of these two, or stronger than what either of these inverters can drive. So we overpower the inverter, and we can flip it, let's say, from a 0 to a 1 or a 1 to a 0. So this is not traditional sort of complementary logic, but this is how we typically build register files, small little arrays that are close, let's say, into a processor. Now let's move to something a little bit larger. We're going to look at memory arrays. So these are things like SRAMs. So we go from register files, something that we'd hold our general purpose registers for a processor in, and we're going to move out a little bit and talk about small arrays, something like caches, maybe a kilobyte of data. And these are typically built out of SRAMs. Same structure. We're going to change the cell a little bit here. The main difference is the cell, we're going to have two sets of bit lines. We're going to have bit and bit bar. And then we're going to have two pass gates here, and these are cross-coupled inverters in the middle. And by doing this, we also have this word line running the other direction, which connects this cross-coupled inverter to the bit lines. By having these SRAM arrays, typically what happens is because you have bit and bit bar, you can have these be even weaker than normal. And when you go to build something like an SRAM, down here, in addition to the column decode, you're also going to have what are called sense amps. And these are basically operational amplifiers where you hook the bit and the bit bar to them, and it can sense a very small difference between bit and bit bar. And by doing this, you can effectively have a very low difference between bit and bit bar and be able to sense it at the other side. And one of the differentiations I wanted to make between a register file and this SRAM here is that the register files many times are designed to be sort of multi-ported. But in this diagram here, these bit lines get reused. They're both read and write bit lines. So we've effectively built a single-ported SRAM. Having said that, people do build multi-ported SRAMs and single-ported register files, but conventionally, you build a register file when you need speed, and you need lots of ports, and you build an SRAM when you want to be more dense in your storage. OK, so now let's move to a piece of technology that is in all of your computers, or rather register files and SRAMs are all in your computers. But this is something that you can actually see, because usually the SRAMs and the register files are all integrated onto your centralized microprocessor. You don't actually get to go see it. But here we have a stick of DRAM. So let's see what this is. This is PC100 DRAM, and this is old stuff. This is 128 megabytes of RAM. Nowadays, your computer has, at least this laptop here, has 4 gigabytes of DRAM. And different people have different amounts. But DRAM, I want to contrast with SRAM. You still go and build an array out of it. But the actual storage looks very different. The bit cell storage, instead of being some form of cross-coupled inverters, instead, you're going to have one transistor which hooks a capacitor into your bit line. Now, you may ask yourself, how do you build a capacitor? Capacitor, typically you need 2 plates or 2 pieces of metal with some dielectric in the middle, where you can store charge. Well, what's inside of that RAM looks very odd. It is a capacitor, but it's a very oddly shaped capacitor. Typically, what will happen is you build these very, very deep trenches, very long and skinny trenches. They're skinny because you want to put them very close together, because if you want gigabytes and gigabytes of RAM, the smaller you make it, the more you can shove on a single piece of silicon. But you have these really long and narrow trenches here, and you have 2 plates of metal and then a dielectric in the middle. So in this case here, we have, I think there's 2 metal sort of plates here, and then there's some dielectric sort of shoved in between there, but you can't really see it on this picture. And then all the actual logic is up here. So in this diagram here, this is the transistor, N doped, N doped, and here's the depletion region, and here's our word line. But basically, that's this transistor here. So we're going to be connecting the capacitor, which has a very funny aspect ratio, it's very tall, to this bit line. And to give you some idea, this is a slice through the silicon wafer. This is not a plan view or top view. Top view, you would just see what looks like a transistor and then some poly plug here running vertically. It would look really small. But this is a slice. And the reason we do this is because we want to see that the actual capacitor is very long, very deep into this. And one thing I wanted to point out is this is typically really hard to go build on your standard CMOS process. So this is hard to go build on something like a logic process. You have to go build this, let's say, in a special DRAM-only manufacturing process. So you want to, it's sometimes hard to mix that. There are some technologies which allow you to mix them, but when you do that, people haven't really designed ways to make them as small, the DRAM cells as small. OK, so what are the advantages of DRAM? Why are we even talking about DRAM? Well, it's a lot easier in DRAM to have large amounts of storage. You can have big amounts of storage in the same area, because instead of having, I don't know, in SRAM, 6 or 8 transistors for each cell, instead, we now have 1 transistor and 1 capacitor. So it's actually less. Now, how does this circuit work? Well, logically, what we're going to do is we're going to store data or store charge in the capacitor. So we're going to connect the capacitor to the bit line. We're going to either put a 1 or a 0 on the bit line, and then we're going to disconnect it, and it'll hopefully store the charge. And at some point in the future, we're going to connect it, and we're going to discharge it into the capacitor into the bit line and read out the value. And we still need something at the bottom here, which is very sensitive, to be able to read out this bit. And the reason is because the capacitance that you can store in one of these little capacitors is a very small amount, so there's not a whole lot of charge in the circuit. OK, so what is the cell? What's the problems with this? Well, first, one of the major problems with this is you're going to end up having this capacitor discharged and charged. And capacitors, as you may recall, don't always store their charge that well. They might slowly lose that charge over time. And what this turns out to be is you're actually going to have to refresh the DRAM. So you might have heard of DRAM refresh, but typically, in a modern day computer, your DRAM will only hold the data for maybe a few seconds. It used to be that it only held it for a few milliseconds. Most RAM's actually decent now, and you've probably seen some attacks that people have built around this. Like there's some encryption attacks where people will effectively turn off a computer and then pull the RAM out and stick it in a different computer. And the DRAM will still hold the charge, still hold the information, even after you remove the electricity or remove the power from it, because this is a bunch of little capacitors that will store that charge. That's a funny little case where this DRAM ends up being a negative, but we're really doing this to have more space to store data, because each of these bit cells is a lot smaller. OK, so I like this diagram. And this is one of the more key diagrams in today's lecture here, is showing the relative sizes of SRAM versus DRAM and different types of SRAM versus DRAM. So let's start off here with an SRAM cell built out of logic on a logic process or logic CMOS technology. So that's this one here. This looks to be 6 transistors, so sort of optimized SRAM on a logic process. And it's pretty big. Let's contrast that, though, with this one over here. We have DRAM on a memory-specific process. And it's tiny. So it's not only 1 transistor versus 6 transistors. It's actually more than 6 times smaller because they can optimize it because they can go into the Z dimension here, go into and out of the board, because that trench capacitor goes down into the substrate. And some other interesting things on this diagram here, we have a DRAM on an ASIC process or DRAM on a traditional ASIC process, which is here. Here we have 6 transistor cell with local interconnect. It's a little bit smaller, so what that means by local interconnect is you can use the poly layer of your process or the polysilicon layer to do interconnection, so you don't have to use wires for everything. So it gets a little bit denser, so the layout gets a little bit denser. And I really like this bottom one here. Yep, that bottom one labeled A is not 4 different things. Instead, what that is this is a fully complementary logic cell, a storage cell built out of gates. So there's some number of gates put together here. So this is what this is trying to get across here is that the addition of custom logic cells, either this one or this one, storage cells in your library is really important, because otherwise your RAM is going to be a lot larger, or you won't be able to fit as much memory on your machine. OK, so to wrap this memory technology section up, I want to talk about some of the trade-offs. And computer architecture is all about the trade-offs. And why would we use one type of technology versus another type of technology? So what are our trade-offs here? Well, we can go from fast, close, small things, so things like latches and registers, and we sort of put them together into bigger, we put them together into bigger things like something like a register file and an SRAM, and have different technologies even. And as we sort of get to bigger and bigger memories, we get a lot more capacity, but it takes longer to access them, kind of by definition. And typically we have less bandwidth. But if we have small things, we have low capacity, low latency, and very high bandwidth. So it's sort of a trade-off of capacity versus the other positive aspects. And depending on where you put it in your memory system, you might want to trade these off differently. So now that we've talked about these different memory technologies, let's move on and talking about an introduction to caches and why we have caches and where this really comes from sort of first principles perspective. And to start off motivating caches, let's draw the most basic memory system we can draw. So in our abstract computer model, we have a processor, and it connects to somewhere to store our data and our instructions, or our main memory. And the time it takes to actually access something like our main memory can many times be much larger than our cycle time, or the latency can be much larger. So that DRAM I passed around, to get a byte out of, or to get like the first byte out of something like a modern day's DRAM, it's going to be thousands of instructions. Or probably around it's probably right around 1,000 actually in a modern day computer. It's gotten a little bit better, as we'll see on the next graph, for a funny reason. But and the bandwidth we're going to define as the sort of number of accesses per unit time. So as I said, for the close-in arrays, you can usually access them much faster and have more bandwidth through them, sort of by definition. But for things far away, you have to have less bandwidth, kind of by definition, because you have to probably go through some pins or some buses that have to go very far away. And then we're going to define the bandwidth delay product as the amount of data that can be in flight at the same time. And as you have sort of things farther away and more bandwidth, this bandwidth delay product gets bigger because you're multiplying sort of the amount of stuff, the amount of bandwidth you have times where everything can be in the pipe. And you basically have a big pipeline with sort of thousands of values in flight. So this is what I was alluding to about the gap happening between DRAM bandwidth and processor performance. So memory technology has been sort of slowly getting faster, and processor technology got a lot faster. The one thing that's at least not so bad anymore for single scale or for single processor performance, we've sort of flattened out at this point. So now RAM is getting faster. Unfortunately, this is still keep going exponentially here if you sort of look at multi-core. If you have multiple cores in the same chip, the amount of aggregate processor performance is going up relative to the memory performance, and things get worse. So here we have a 4-issue, 2 gigahertz superscalar, accessing 100 nanosecond memory. DRAM, can execute 800 instructions during the time to access that one memory reference. And we have things faster than 2 gigahertz now, and we also have slower memories than depending on what memory system you put in, it can somewhere roughly about 1,000 instructions. Okay, so what's the important first order effect when we're looking at memory systems? Well, size does matter. As you have larger and larger memory systems, it just takes a longer time. There's more capacitance you have to drive, and you have to go physically farther. And you can't fundamentally fight the speed of light. It's going to take you a certain amount of time to go a certain distance, and if that distance is farther, it's going to take you longer. So you also have sort of more fan out if you have bigger memory systems. So our physical size is important here when we're thinking about memory systems. Okay, so let's now introduce a cache, or an idea of why a cache is good. So let's look at a notion of memory hierarchy. Unlike this picture where we had a processor connected to all of memory in the system, we're now going to put some intermediary levels. So we have a processor, and we're going to put small, fast memories here. And we're hopefully going to try to access these small and fast memories instead of accessing this big, slow DRAM. Let's look at the capacity here. The registers, so your general purpose registers or registers that hold, let's say, your program counter, specialized registers in your processor, has very small capacity. SRAM has more capacity. DRAM has even more capacity. And it's sort of double less thans there to accentuate that you can fit a lot more in the same space. Though the latency follows that same hierarchy there. And important other thing to think about when you're building memory hierarchies is that on-chip memory bandwidth is typically a lot higher than off-chip memory bandwidth. If you're on-chip, you can run wires there, but the second you have to go off-chip, you have to go out the pins of the chip, you're going to be limited. And what this really boils down to is the pins or balls or solder columns. So modern day chips, we don't actually have pins on them anymore. Instead, we have ball grid array, what is little tiny solder balls. The size of those, the pitch of those, is still much larger than the wire on chip. A wire on chip is so much smaller than the solder ball, or in modern day, actually, like something like your x86 Core i5 or something like that, or Intel Core i5, actually has what's called land grid array, where you have a little array of little they're pads, little metal pads on the bottom of the chip. And then there's these little pins that are actually located in the socket on little, they call them pogo sticks, but they're basically little pieces of metal on springs. And you put the chip in, and then the little pogo stick hits the piece of metal, and that's the contact. On older chips, you actually had the pins on there, on the chip itself, and you sort of put it into a big socket. And in the middle is ball grid array. But anyway, all those things the connection technology to get off the chip is much larger. So you can fit fewer of them in the same area than if you were to wire on chip. And that's really this insight here that on-chip bandwidth is a lot larger than off-chip bandwidth. And because of this, you're going to want to think about putting small, fast memories close by on chip, where you can store data. OK, so what happens in this memory hierarchy? When we go to access data, if the data is in our fast memory here, we're going to go here, hit in our low latency SRAM will say, and come back. If the data is not in the fast memory, we have to go all the way out to our DRAM and come back. And memory hierarchies work only if you're going to find useful data here. So if you go build a small, fast memory close by, but you never find any information in there that you need, why did you build this structure? You're just sort of doing extra work and burning extra power. And this is one of the key insights of why we have caches, or what a cache is that when we go to build a memory hierarchy like this and we introduce something like a cache, by finding the data nearby that's going to be faster to access, we need to find the data there with high probability. Otherwise, we should have just not built it and just gone out to main memory all the time. We were just wasting everyone's time and area and cost. So memory hierarchies only work if you have your fast memory actually is useful. OK, so let's look at different memory access patterns and try to come up with a couple different techniques that we can exploit to increase the probability that the data we're going to need is in that small, fast memory. So we have an interesting graph here. And I want to explain what this is. And we're going to look at a toy example first, and then we're going to look at a memory trace, memory reference trace from a real operating system with a real program running under it. But let's start off with some examples here. We have time on the horizontal axis, and we have address on the vertical axis. And if something like your machine, let's say it has 4 GB of RAM, we actually have sort of a line across here for every single address in the machine. And then we have time. And as the program executes and goes and accesses different pieces of memory, we're going to put a dot on this graph. So let's start off by looking at something like an instruction fetch. Typically, programs will execute in order. They'll execute the first instruction, then the next instruction, and the third instruction at the addresses, sort of monotonically increasing, unless you hit a branch. So let's take a look at some instruction fetches. We start off by executing some code. And then we're going to actually execute a loop here. So when we're in the loop, we're going to be executing the same piece of code over and over again. And if you look at that from an address perspective, we start off not in the loop. So we have some address here, some different address. And then we execute these 3 addresses. And then we execute those 3 addresses again, those 3 addresses again, those 3 addresses again. We keep fetching those 3 addresses over and over again from our memory system. And at some point, we exit the loop and go execute something else. OK, there's a pattern there. Now, we're going to think about whether we can exploit that pattern in a second. Next, let's talk about accessing the stack. So computer programs typically have stacks. This is where you either spill or fill registers for. Typically, you also use it to pass arguments. And you spill and fill. Most modern-day compilers will do that when you make a function call or a return from a function call. And the argument passing is around function calls also. You'll put arguments that the later functions need on the stack, and then you go execute that. Alternatively, you can store the arguments in the registers. But in something like x86, we'll say you're going to put arguments onto the stack. And you also put local variables onto the stack, because it gives you a convenient place to put it. So let's take a look at what happens when you go to do a subroutine call. When a subroutine call, the stack is at one address. The stack pointer is somewhere here. And when you go do a subroutine call, you're going to push all of your registers onto the stack. So you're going to put something here, put something here, put something here, put something here, and the stack pointer is going to logically increase. And then once you're in the function that you called, you're going to want to access the arguments. And those are usually very close together. They're all right next to each other on the stack. Or you might have to go access the argument over and over again. This is, if you don't have enough registers, like in our first lecture, we looked at a stack-based architecture. And a stack-based architecture, we had to actually push onto our stack the same value multiple times. It's pretty common to reuse the same local variable or reuse the same argument because you don't have enough registers. And you want to go load that data from your stack over and over again. So it's pretty common to access very close together on the stack, maybe probably the same within a cache line, or access the data very close by. And then when you're done, you return from the subroutine, and you're going to pop all the data off the stack. So time is increasing this way, so you're going to remove in reverse order. OK, let's look at some data accesses. The one I wanted to focus on here is actually vector accesses. So what's a vector access? Well, this is something like an array. And arrays, a lot of times you'll be reading the first word or the first byte, then read the next byte, and then you read the next byte, and you're doing some operation across all of it. So let's say we're taking a matrix addition. We have one matrix, and we're adding it to another matrix. And they're single-dimensional matrices. You're actually going to be reading different addresses, but they're going to be in some pattern, and they're going to be sort of close by. Now, if you're accessing, let's say, every fourth element in an array, this distance here would get larger. The address distance is going to get larger, and your access patterns are going to get a little bit farther apart. And scalar values, these are sort of singleton values. So a good example here is, let's say this array that we're doing here is we're trying to take an array. Instead of add two arrays together, we're going to take one array, and we're going to add 5 to every single, or some variable x, which has, we'll say, 5 in it, to every single element of the array. So what your processor would do is it would first load the thing you're going to be adding to, so the data from the matrix, and then load from the scalar value x from main memory. Do the add and do a store. Then you're going to load to the next location of the vector, load the x, do the add, put it back, and continue that on. OK, so can we try to exploit different types of locality? And this slide is really important to grasp what's going on in caches. And this is probably the most important slide in today's lecture, is to grasp what's going on here with the different patterns we're seeing, and how do we exploit these patterns. OK, so there's two types of patterns I want to talk about. And your standard cache system is going to exploit these two patterns. But let's first of all look at them individually. And we'll be able to see the patterns here. First one we're going to talk about is temporal locality. Temporal locality is this notion that if you access a piece of data, you're likely to access that piece of data again in the not too distant future. So it might be useful to keep that data nearby. So temporal locality, I'll say it again, is if a location is referenced, it is likely to be referenced again in a short period of time. So let's try to identify that in these diagrams so far. OK, well, I see that a few places. These argument access, we access some value, and we're going to go access that value again pretty soon, then again pretty soon, then again pretty soon, and again pretty soon. And we're basically accessing something with high temporal locality. Likewise, these scalar values here, this scalar access, we're accessing it again and again and again. It's this exact same address, and the time between one axis and the next axis is pretty close by. OK, now let's look at this and see, are there other interesting access patterns here? Well, interestingly, on a stack, when we go to access a value, and we're pushing our values onto the stack, it's very common to access a value at, say, address 1,000, and then go access 1,000 plus 4, 1,000 plus 8, 1,000 plus 12, 1,000 plus 16, and access all of the nearby values. So what are we going to call that? Is that a common pattern? Well, yeah, it's pretty common. And we see that here. We see it in loops for instructions. We're actually accessing one instruction. It's very common for us to go access later instructions very close by, packed, let's say, next to it. This is pretty common that you just fall through in your code. So we're going to define this and call this spatial locality. And spatial locality says if a location is referenced, it is likely that locations nearby it are going to be referenced in the near future. And these are both just heuristics. There's nothing magical about these. These are just heuristics of how programs happen to work out. But we're going to build systems that try to leverage these two heuristics, or these two characteristics, rather, these two types of locality to improve the performance of our processors, or be able to use those small little RAMs that we're going to put in our memory hierarchy and actually store useful data in them. I also wanted to sort of point out that you can have both spatial and temporal locality mixed together. So if we look at something like running a program which has lots of loops, we have spatial locality because we're executing instructions nearby, but we also have temporal locality here because we're reusing all of this data again and again and again in a short period of time. So in the near future, we are accessing sort of the same data over and over again. Even though it's not the exact same piece of data, it's nearby. So we're sort of seeing both spatial and temporal locality exhibited there. OK, so let's look finally at a real memory reference pattern or real memory reference trace. And this has the same axes of what we saw before. We have time, and there's one dot per axis. And then we have memory addresses. I don't know what the unit on the vertical is. It's probably not. It's probably in like thousands or millions or something like that. And this is from a study that some people at IBM did many years ago. But we're going to look at this and see different patterns show up here. So the first thing I want to circle here is spatial locality. So we see that along this line here, we access the first piece of data at, let's say, this address. And we then go on and access all of the data subsequently. So this is as if we were like reading an array. We just read all the values in the array. So we have spatial locality that because we went and accessed element 1 in the array, there's a high probability that we're going to go access other data values which are nearby in that array in a nearby time. Let's take a look at temporal locality. So horizontal lines here are temporal locality. And we can see that this program is accessing this value over and over again, or at least values very close by. It's hard to tell on this resolution. But this is temporal locality, that we're accessing the same values, or mostly the same values, over and over and over again. And then finally, we can see both temporal and spatial locality in these little blocks here. We can see that we're accessing similar sorts of addresses, which is going to be spatial locality. And we're doing it all within a short period of time. So we're seeing temporal locality of reference. And caches can exploit both of these. Caches are going to exploit temporal locality by keeping data that gets used and reused many, many times nearby. So when you see axes which are temporally close by, or temporally spaced, so in time are spaced nearby, what's going to happen is a cache is going to sit somewhere here before you get to a main memory system. And when you go to access a value, it's going to memorize that and keep that value nearby. So if you go to access it again in time, and if your program exhibits temporal locality, that data value will be close by, and you won't have to go out to the big, slow RAM. And caches can exploit spatial locality. And the way caches go about exploiting spatial locality is that when you go to access a particular piece of data, your cache is going to pull in data around that piece of data. And we'll talk more about this next time, how that works, but we're going to segment data into what we call cache blocks or cache lines. And that's typically, those cache blocks or cache lines are aligned. And when you go to access a piece of data, it might be somewhere at the beginning or at the end, or it might be in the middle. You pull in all the data around that. And the heuristic here is that if you access some piece of data, let's say you only go access the first byte in a cache line, you're likely to go access other bytes in a block, so multiple pieces of data around that. So we're able to exploit spatial locality here. OK, let's begin today. So we're going to start where we left off last time, which was talking about in-order superscalars. So as you may recall, just a brief review, we were talking about these sort of a little bit more complex pipelines. We were able to execute multiple instructions at the same time. Sometimes instructions had to sort of be steered, if you will, between the A and the B pipe coming from the two different instruction registers. We have to double our decode. We need to check to make sure that there's no dependencies between the instructions we're trying to issue at the same time, and our decode logic will do that. So there's going to be some sort of cross-communication inside of there. And in our previous example, we were looking at an asymmetric pipeline. So what I mean by that is, loads and stores went down this pipe, and branches and ALU ops went down that pipe, and also ALU ops went down this pipe. So where we left off last time was talking about alignment and how do we deal with fetching multiple instructions from an instruction memory or instruction cache, but at the same time, how do we not have to make this structure have many, many ports, for instance? Or does it have to have many, many ports? So we looked at a basic piece of code here, which has a whole lot of interesting alignment issues. So at the beginning here, we were basically fetching instructions which were nicely aligned into the cache's blocks. And then this one was OK. We jumped to the beginning of a block. That was fine. Here we jumped to the middle of a block. And depending on how our cache was implemented, we might need to do sort of two fetches. Let's say you can only read out of your cache half a block at a time. Then you might have to do a fetch to get this and fetch to get that. And then here we even have things which sort of cross cache lines or cross complete cache blocks, which is quite a bit harder. So let's take a look at this. So if we have some alignment constraints, so let's say the alignment constraint we have here is that you can only fetch either from the first half or the second half of a block at a time. And if you're trying to execute something which straddles a cache line, you're going to have to fetch even more data. So as you can see, if you recall from this figure, this, and that instruction or piece of data in the RAM, when we go forward, we're basically going to be fetching extra data with that alignment constraint than we would have been fetching otherwise. This gets even harder. It's OK to sort of overfetch. It's another thing if you actually have to sort of straddle a cache line here. And because the question comes up, can you fetch those two at the same time from the cache or not? And we'll look through an example here where we're going to look with these alignment constraints and see that, no, if you can't actually fetch that, you're going to be introducing what is effectively dead cycles going down the pipe, which hurts your clocks per instruction. So here is the same instruction sequence that we had here. And these dead instructions that go down the pipe here, or killed instructions that go down the pipe, are actually just these three X's. So we've effectively overfetched. And then, when we go to overfetch, let's say here we fetched 208, but we had to fetch 20C, and that instruction is going to go down the pipe and not actually do anything. So you can see that you can actually, when you have alignment constraints, you basically can just introduce extra extra dead instructions going down the pipe, and you're not actually going to be using that and that's not necessarily great. OK, so an important question comes up with something like a superscalar when you're executing multiple instructions at the same time is what happens when you fetch 2 instructions and you, let's say, one of those instructions takes an interrupt or an exception as it's going down the pipeline. So let's take an example here. Let's say we have a load and then a system call instruction. Now, both these instructions can effectively take interrupts or exceptions. The load can take something like a TLB miss or an alignment fault. The syscall instruction, by definition, is effectively making an interrupt occur. And one of the interesting questions here is this load word, which is going to go down the pipe. If we fetch these 2 at the same time, and they start marching down the pipe, so this is our pipeline diagram. We fetch at the same time. We decode at the same time. The load has to go to the A pipe, or the load has to go to the B pipe, so it ends up in B, and the syscall ends up in the A pipe. Well, what does this exactly mean if the load is in the B pipeline, but it takes an interrupt and it commits in order first? Well, actually, let's think about that even. Let's think of even a simpler question here. What if the load does not take any faults and the syscall takes a fault? Which happened first, A or B? OK, so which should happen first in program order? A load and then an instruction after a load. The load should happen first, because in program order we go sort of top to bottom. But the load is in our B pipe here. In our A pipe, we have a instruction which takes a interrupt. Well, so what happens here, right, is that the load should go down the pipe and complete. And in order not to deadlock, basically your decode logic is going to have to sort of either know about this, or very, very late in the pipe, you have to have what we're going to call a commit point, which we're going to be talking about later in today's lecture. And you have to make some rational decision here of which of these actually occurred in order. And you somehow have to track that going down the pipe. And then you have to make a decision of, oh, well, the A pipe actually just took an interrupt. But in program order, the B pipe is the first instruction going down the pipe. So at the end of the pipe there, you're going to have to make some logical decision and have to have a little bit of control logic to make sure that you're not going to, let's say, take an interrupt for the syscall, even though, and kill the load instruction before the syscall. So one thing you could do is actually have both of them go down the end of the pipe, not kill the load, let it commit, and have the syscall actually take the interrupt. And that's probably the highest performing thing you could do in this case. Lower performance things probably would be easier, but that's probably the highest performing thing you can do in this case. OK, so we sort of introduced this two-way superscalar, in-order superscalar. One thing we need to think about is we add a lot more places that data could be coming from if we have to forward data. So we now, instead of, when we had one pipeline, we could bypass data out of here, here, and there. So there's only 3 places. But now that we have 2 pipelines, you've effectively multiplied the places that you can bypass out of, and now you can have 6 places. So if you go sort of pull the steering logic off, and then make your multiplexers bigger here, which are you're doing your bypassing, you end up with 6 different locations that you have to choose between for each input operand. And this is a relatively short pipe. So as you start to grow this to bigger and bigger pipelines, either in depth or in width, and you want full bypassing, you're going to have more and more, much wider multiplexers here and a lot more data being bypassed. So this actually becomes a problem, and you need to start to think about this really hard. So what are some solutions to this? Well, one solution that people sometimes do is they don't have full bypassing. You can only bypass out of certain locations. That's one option. Another option, which we'll be talking about a little bit later today, is you can actually maybe not actually have this pipeline register. And if you start to think of having out-of-order processors, you can start to think of committing information back to the register file early. So this pipe here has nothing happening in this stage. Well, can we just shove it in the register file? On first appearance, that sounds great. You start to think about that a little bit more, and you can start to get worried here because you start to see write after write hazards actually start showing up as real problems then. Because if you issue an instruction here, which writes to the same register, which happens at the end of this load operation, we'll say, then you could actually get out of order writing to the register file. So you need to be cognizant of that. Other approaches that people take to this is sometimes they will actually have what are called clustered superscalars. So clustered superscalar, they'll actually have, let's say, 4 pipelines, and they'll cluster them into 2 pipelines of 2 each. And you'll allow bypassing between 2 of the pipes and 2 of the other pipes. And if you do bypass between the 2 sets of clustered pipes, then it takes an extra cycle, or you have to do it through the register file or something like that. So there's other approaches there to try to mitigate the blow-up of this bypassing network. And you have to remember, in something like a 64-bit processor, each of these are 64-bit buses. Each one of these little wires here. So these things get pretty big pretty quick. So you have to worry about actually running these things around the chip, because all of a sudden you have hundreds and hundreds of 600 bits running over 600 wires running up and over just for your bypass from this simple pipeline. And if we go wider, it's going to be much worse or longer. So one thing that people do a lot to handle this bypassing from a critical path perspective, because this takes a long time, or starts to take a long time, is you start to break the decode and the issue. So we're going to sort of get away from our 5-stage pipes now. Up until this point, we've been doing things that you've seen in the first Patterson and Hennessy book. And now we're going to start thinking about things that have longer pipelines. So one good thing to do is you can actually break the decode and the register file access into 2 separate stages in the pipe, effectively making a 6-stage pipeline now. And what do we put? Well, one thing we can do is actually just break the decode into its own pipe stage, and we can try to figure out structural hazards even in that pipe stage. And that's something that people sort of traditionally do. They'll do decode, and they'll also look to see if you're going to have a structural hazard, let's say on a write port of the register file at the ends of the pipe. And then in the issue stage, I for issue, you'll do the register file, and you'll probably swizzle or crossover or steer the instructions and the operands to the correct location. And of course, you'll do this bypassing if you have lots of bypassing operands coming back. So to give a sort of a brief pipeline example here we have 2 cycles, and each that execute 2 instructions per cycle. And we can see now our pipeline has an extra I in here, which is just an extra front-end stage. OK, so this has some negative aspects. Can anyone think of one of the negative aspects of putting extra pipeline stages in the front of our pipeline? Yes. So branches, if we know that the branch gets resolved in out of the first execute stage of the pipe, or in our 2 pipe here, it's out of A0, we've just increased the branch cost by 1. So now something that would have branched, or a branch mispredict penalty of, let's say, 2 cycles just became 3 cycles. And this can start hurting your performance. And this really starts to hurt your performance as you start to go wide. So let's take this instruction sequence here, where we have this extra issue stage out in front. And we have a branch in the first instruction we try to execute. And then we just have sort of the fall-through code here, which we predict fall-through. We don't realize that the branch happens till A0. And at that point, we can redirect and just sort of kill everything that we've already gone in flight. But look at all the things that have gone in flight already. We're sitting here, which means we've had 1, 2, 3 other stages, if you will, or 3 other cycles to go fetch instructions. So we fetched these. We decoded them. We spent a lot of power. We spent a lot of time. We spent a lot of fetch bandwidth doing this. And then we just kill it all, and revector to the correct branch target. So in this example here, we've killed 7 instructions. So this can have a pretty negative impact on our clocks per instruction, if you will. So let's talk briefly about how to fix this. We're not going to fix this all today. We have a whole dedicated lecture to fixing this. But what could we possibly do to minimize the probability that there is all these dead cycles here, or all these killed instructions going down our two-way pipe? Well, we can hopefully, if we're lucky, we can try to predict the destination with some accuracy and have a branch predictor which will figure out where the destination of the actual branch is with some high probability. And then instead of executing, let's say, op A here, which is a dead instruction, which is the incorrect branch target, we can try to fetch and try to execute the correct branch target. And we're going to have a whole talk, we're going to have a whole lecture on how to get your branch prediction accuracy up. So in modern day processors, they're somewhere around 98% accurate, give or take a little bit. I actually don't know what the state of the art is on this because they keep getting better and more complex branch predictors. But there's some pretty simple things you can do to sort of get you into the mid-80s range. And then to get from sort of the mid-80s range of branch prediction accuracy to the 90s, you have to sort of put a lot of effort and time into that. But we'll have a whole lecture later in the course about branch prediction, just dedicated to branch prediction. But I just want to motivate here that if you have a longer front end of your pipe, and we're going to look at some pipelines where there's even more front end stages than just fetch, decode, issue before the branch gets resolved. Whenever you add an extra pipe stage in the front, that's going to impact your performance. Because even if you have a high prediction accuracy, your prediction accuracy is not going to be 100%. And if you mispredict, you're just going to have dead instructions going down the pipe, and it's just going to be wasting time, energy, and utilization of the pipeline. And let's start talking about exceptions and interrupts. And then we're going to start talking about superscalars too. So we'll start talking about out-of-order superscalars. So how do you actually start to execute instructions when they're not in programmatic order? And when you first hear about this, you're going to say, well, how is that possible? You shouldn't be able to execute instructions out of order. But it's relatively easy. You can actually just execute them out of order. Maybe you want to commit them in order. That may even be optional. But let's start off by talking about interrupts. So what's an interrupt? So an interrupt is typically some external or internal event that happens, and it may be synchronous to an instruction, or it may just be some external thing that happens that is going to redirect your control flow somewhere else for a little bit of time, and then it'll come back to the instruction that you were at before. So here's our program. It's happily executing instruction I-1. Then it's going to execute instruction I. Instruction I doesn't actually commit. Instead, we vector over here to an interrupt handler, which is also some sequence of instructions that processes some problem, let's say, with instruction I. And then when it's done, it'll come back, re-execute instruction 1, or instruction I. Maybe, maybe not. We'll see why there's some cases that you may not actually go to re-execute this instruction if it has a fatal fault, and then continue on. Typically, I wanted to point out that a lot of times this is done sort of for system-level code or operating system-level code or hypervisor-level code that you'll jump someplace else. So a good example of this is a timer interrupt on a processor. It goes off, and it'll re-vector you to someplace else where you have to sort of update the internal time of the machine, and then you go back to the instruction sequence that you were executing before. So let's look at some of these causes. So we'll name the first set of interrupts here asynchronous interrupts, or some people call these external events or external interrupts. And some good examples, as I said before, are devices cause an interrupt. So something like the programmable interrupt timer on x86 processor will cause a timer tick every once in a while, or every 100 times a second is pretty probable. Other devices, your network card gets a packet in on it, and the packet needs to be processed, so it needs to be read off the network and be put into RAM somewhere. Hardware failures, so things like ECC memory errors, so it's error correcting code memory errors in your main memory will sometimes cause interrupts to happen or asynchronous events to happen. Synchronous things, sometimes people call these exceptions or traps. I'm actually calling all these things interrupts because from a naming perspective, if you read different architectural manuals, they all rename these things slightly different, and there is no sort of common utilization of the terms. But if you're using something like x86, a synchronous interrupt is usually called either a trap or an exception. But that's not common across all other architectures that are not x86. So some good examples of this is if you try to execute an instruction which is not in the ISA manual. It's some gobbledygook of bits on the disk. So it's error code, effectively, or some non-valid instruction. You'll get an illegal instruction exception. Or if you're trying to execute, let's say, an operating system level instruction. We haven't talked about this in great detail. We'll touch on this later in the course. But if you're trying to go execute some instruction that only the operating system should be able to execute, but you're executing it from your user program, then you're trying to execute something like a privilege instruction. That's a good way to have this happen. Arithmetic overflow. Some architectures have it when the precision of your numbers falls outside the scope of what you can actually accurately represent. You'll get an overflow exception or underflow exception. Similar sorts of things can happen in a floating point unit. So a great example of this is if you end up with what are called denormalized numbers. So in floating point numbers, this means you basically have also lost precision in your floating point unit. So you fall out of the range of numbers that they can represent very well, and you end up in this other space that are called denormalized numbers. You'll get an exception, usually. Sometimes other sorts of things that fall into this case are things like divide by 0. If you try to divide by 0, you'll sometimes get exceptions. And you can do that. That's a great way if you on your x86. If you guys want to write a program, write a simple C program, take some number, divide it by 0, and then go and run the program. You'll get a printout. The operating system you'll get an exception. The OS will print out divide by 0 fault. And your program will stop. It'll kill your program. Unaligned memory. Some architectures don't allow you to access memory in an unaligned manner. Some architectures do. So something like MIPS. The MIPS instruction set, if you go to try to execute a unaligned instruction sequence, or unaligned load, we'll say, on the earlier versions of MIPS, you'll actually get a unaligned memory access. Later MIPS have it as an option. You can either have it take a trap or not take a trap. Common thing, page faults. So we'll be talking about paging later in this course, but if you go to try to access some piece of memory and the memory is not mapped in correctly, so you just can't, the machine physically can't go find memory, you'll take a trap. And then finally, the things like system calls or interrupts on x86, there's an instruction called int, which actually causes just an interrupt to occur, and then it takes as a parameter a number. So that's how system calls have traditionally worked on x86. They later replaced it with actually an instruction called sysenter, which does a similar sort of thing with a little bit cleaner semantics. So I think actually there's one point I wanted to talk about. Asynchronous interrupts is, with asynchronous interrupts, it's hard to know when to deliver the interrupt, because it's not pegged to a specific instruction. And if your instruction is going down the pipeline, you don't necessarily know whether to tag it to the first instruction that's in the pipe. I think it's at the sort of the fetch stage. I think it's at the execute stage. I think it's at the write back stage. So that's a challenge. Another important thing to think about with asynchronous interrupts is sometimes multiple of them go off at the same time. So let's say your timer interrupt goes off at time t equals 0. Your network card gets a packet in, and someone hits the keyboard exactly at the same time. Well, which should happen? Which should you actually go handle? Typically, machines have a prioritized interrupt request mechanism. So there will be some sort of priority encoder there, which will determine which is the highest priority. Some machines will actually have reprogrammable priority interrupt encoders effectively, which will allow the system software, the operating system, to decide what is the highest priority interrupt to go take in that case. Sometimes machines will just sort of make a decision, or the architects of the machine will sort of make a decision and say, these classes of interrupts are not or asynchronous interrupts are not very easy to handle. So we'll just sort of put those in the sort of lower priority bucket, and then some smaller set you'll actually be able to sort of reprioritize, if you will. Oh, yeah. So I wanted to talk about this. What actually happens when you take an interrupt from a hardware mechanism perspective? So this is a very idealized view, but from a mechanical perspective, things need to happen in the machine. There's some state that needs to be updated. First thing that needs to happen is you should basically stop the program at some point, and you should try to save the program counter somewhere. Because if we want to come back to, let's say, the instruction that took the interrupt, we need to know where to come back to. But we're going to go and execute some other piece of code in the meantime. So we can't just save it in the program counter. We need to save it off. And that's typically called either an exceptional PC, so EPC, that's what it's called on a MIPS processor. On x86, I'm trying to remember what it does. I think it actually gets pushed onto a system stack, so it gets put into memory somewhere. And if you look at something like MIPS, one of the tricky things here is all of your registers are still live from the previous instruction sequence here. So all of a sudden, you jump into a new piece of code, and all of your instructions are still, or all of your registers are still live. They have values you can't throw away, and you're in the interrupt exception handler. What do? Well, there's different mechanisms to this, to have this happen. Some architectures, something like MIPS, actually reserves 2 registers that are only allowed to be used by interrupt handlers. This is actually a pretty poor solution, in my opinion. So they save off 2 registers. I believe it's somewhere high. It's, I think, maybe 28 and 29. Register 28 and 29 are not allowed to be used by the basically operating system or the user code, and it's only used by interrupt handlers in the operating system to save off state. And what happens in that case is you could use those registers to basically take the other registers, compute some addresses, and do a store. Because if you recall on MIPS, you need to have an address to do the store to. So you compose the address into, let's say, register 28, and then use that as the store address. And you can store off all of the other registers into memory somewhere. And then you can unwind that back when you're going to return from the interrupt. So it's a complicated dance. Something like x86, there's some hardware mechanisms there which will actually take it and take a lot of your registers and put them onto a in-memory stack for you. So it's typically what's either a push A, which is a pushes all the register state onto the stack, and a pop A, which pops it off. That's not actually required, though. There's some operating systems don't actually do push A and pop A. Better operating systems or more modern operating systems will actually only save off what is strictly needed. But something to think about. One other important thing here, typically when an interrupt occurs, you probably want to mask other interrupts from happening. So this is a really hard problem to solve, is you have interrupts inside of an interrupt handler. Ooh, that doesn't sound like a happy day for anyone. Because what if you're in an interrupt handler, another external interrupt comes in, what do you do? You can't save the exceptional PC into the exceptional PC state now, because you've already saved the old program counter into there. You can't take that second interrupt inside of that, so you can't necessarily nest interrupts very easily. So what people do for this is, one solution actually is to take the exceptional PC and put it into memory somewhere. And once you've done that, then you can turn interrupts back on inside the interrupt handler. You can take more interrupts inside the interrupt handler. Alternatively, if you know that the interrupt's going to resolve itself very quickly, you can just leave interrupts masked the whole time the interrupt handler is happening. And when it's done, just the return from interrupt instruction usually turns off the interrupt. Or excuse me, turns back on the interrupts, if you will. So it'll re-enable interrupts. So you gotta be a little careful there. There's with interrupts inside of interrupts happening. So that's a great question. So what do you save in the exceptional PCE on a interrupt? Oops. So yeah, that's a great question. So if you have instructions sort of marching down the pipe in a two-way in-order superscalar, we'll say, you're going to save the PC of the instruction that took the interrupt. Some architectures define this differently. If you go look at something like x86, typically what gets saved in the exceptional PC is the next instruction to execute. So it's really dependent on architectures. Some architectures will save the address in the exceptional PC of the next instruction in program order to execute. Some things will save the address of the instruction that actually took the trap. And as far as, or took the exception or the interrupt, so it's a little bit of a trade-off there. One thing that's actually hard is if you have a branch that takes an exception, do you store the target of the branch location in the exceptional PC, or do you, you have to sort of resolve the branch first. So that's one reason actually why lots of architectures favor just storing the PC of the instruction that took the trap and not the sort of quote-unquote next instruction. So I actually favor storing the PC of the instruction that took the trap and not the destination of that. Synchronous interrupts, similar sort of thing. Sometimes the handler wants to resume after sort of an instruction, where so it might have to add PC plus 4 if you have an architecture, exceptional PC plus 4 if you need to jump over the instruction, for instance. Something I did want, so here, this is the next question that came up was, what does this look like in a pipeline? And when do you know to actually process the interrupt? So here we have a 5-stage pipe, so it's a little bit easier pipeline. And we can see these bubbles here are actually different types of interrupts or exceptions that can come out of the pipe at different locations. So out in front here, we can have maybe PC address exception. What do I mean by that? Well, some architectures won't allow you to execute, let's say, code out of certain regions of memory. So an example of this actually is in the 64-bit extension of x86. The 64-bit extension of x86, there's what they call the memory hole. So between what people call positive memory and negative memory, so the top bit being set, there's a big chunk of memory which is just no one's allowed to execute out of, or it's not mapped, it's not real memory. So they have a 64-bit address space, but they only use 42 bits of that 64-bit address space. So if you have any bits in the middle which are not set correctly, you're basically going to be executing out of the memory hole. And that's an example of something which can cause a PC address exception. So your PC sort of falls off the end of mapped memory. What do? You're in some piece of memory, you're in some address which by definition is not a valid address. Decode, illegal opcode. So it isn't in your ISA manual. There's lots of opcode encoding space. Usually most architectures purposely leave some space in there just for legal instructions or future expansion, if you will. And you want that to interrupt overflows and underflows out of your ALU. There's a whole host, if you have a floating point unit here, of floating point exceptions, overflows, underflows, and denormalized sorts of instructions. Data address exceptions. Well, this could be if you're, let's say, you have an unmapped memory address, or you do a unaligned load or store. So basically, every stage of your pipe here can be generating some form of interrupt. And then there's also asynchronous interrupts, which we haven't drawn yet. OK, so good first question here is, how do we handle multiple simultaneous interrupts in different pipeline stages happening all at the same time? I agree we should prioritize them. So what is the oldest instruction in the pipeline here? So this is going to be the oldest instruction in the pipe. So let's think about that. So that means it's probably going to want to kill everything behind it if there is an exception that has happened here. So if we were sort of have multiple things generating exceptions here at the same time, the oldest thing, the oldest instruction in the pipe, the instruction that's been in the pipe the longest, is going to want to kill all the rest of the things. Going forward, though, so from a priority perspective, which of these things are probably the highest priority? So do you think we should be computing overflow errors if the instruction opcode is illegal? Should we be even decoding the instruction if the address that we try to fetch from our instruction memory doesn't make any sense? So the priority of sort of when you go to figure out where or which exception or which interrupt is the cause of the exception should go this way from left to right. And then you're going to want to actually kill going backwards. So let's skip that question for a second and look at this drawing. So what you'll see here is we're actually going to just remember that we took some exception for a particular instruction and just pipe it forward. And then what we're going to do is we're basically going to say at the end of the pipe, once we know everything that's happened, we're going to call this the commit point. And that's going to feed back the other way, killing everything. Now, why do we put the commit point here? Could we put the commit point, let's say, in this stage of the pipe, in the execute stage? So let's define the commit point. The commit point is the point at which architectural state of the machine is committed to is committed, and now that may not be in the register file yet, because by definition, in this point here, it's not in the register file. It doesn't get there to the write back stage, but nothing can change. We can't take a branch. We can't redirect. We can't take any more exceptions. Well, by that definition, we can't put the commit point here because further exceptions can happen after the commit point if we pull the commit point back. There are machines which do pull the commit point back. You will see when we start talking about superscale or out-of-order superscalars, we typically like to have the commit point at the end, or near the end, because then you can sort of see if everything's resolved. You can handle your interrupts and exceptions and have exceptions going on in the pipe as long as possible. And if you try to pull your commit point early, that forces you to actually resolve of whether an exception is going to happen for a particular instruction relatively early in the pipe. So if we want to pull this forward a stage, we would have to basically check whether the address of a loader or store is valid in this pipe stage. That may be possible because we finished the calculation of the address right here, but we haven't necessarily, let's say, done the TLB lookup. But we can pull the TLB lookup earlier or something like that. That is possible. And we'll see that some architectures try to pull that early. Some architectures also try to have imprecise exceptions. This is a scary, scary place. We're not going to be talking about this very much. We're going to be talking about precise exceptions mostly in this class. But an imprecise exception is one where instructions are going down the pipe. You basically let the instruction sort of pass the commit point, and you tag the exception to the wrong instruction effectively. It's not precise. You can't stop on a dime. Architectures, there are some embedded processors that do things like that. And it's probably not the wisest thing to do if you want to run a real operating system. But like I said, yeah, so the commit point being close to the end is probably a good place, or at least after all your exceptions are done. So by the time we get to this red dashed line here, so we're after the computation of the exceptional PC and everything, we know that we're going to be committing. or at least we have a thumbs up or a thumbs down. And if it's a thumbs down, we kill everything behind here. One thing I did want to say is cause. What does that register do? Well, that register tells us why did we take the exception. So it's a priority encoder, which prioritizes, as we said, this direction, and will determine the cause of the exception. Asynchronous interrupts. There's different places to wire this in. You just sort of have to tag it to something, but you have to make sure you actually take it. So the simplest thing to do is just to put it into this big logic at the end of the pipe here at the commit point, and have the asynchronous interrupt show up at the end of the pipe. Not all pipes do this. Some pipes will actually inject an asynchronous interrupt at the beginning of the pipe, allow it to go down the end, and arbitrate like everything else here at the end stage of the pipe. The simplest thing to do is to have it come in here, and that's because otherwise you might drop this asynchronous interrupt on the ground or not actually take the asynchronous interrupt, and you want to make sure you actually have a chance to take it. Exceptional PC takes the PC and pipes it forward and saves that in a register, but this only gets loaded on a exception or interrupt happening. Okay, so that's commit points. That's important for out-of-order superscalars, because we're going to have to start thinking about where is the commit point of a processor, and it may not be where we want it. Or it's possible that we will not be able to put the commit point anywhere in the processor and actually have the processor work. So today we're going to actually look at a processor where it's not possible to have precise exceptions. So there is no line we can cut and say this is the commit point. Let's see. So we covered all this. Speculation. This is going back to like our example of PC plus 4. Do we want to assume the exception is going to happen, or the interrupt is going to happen, or not? So we're calling it an exception for a reason. It is the exceptional case. It is not the common case. So we want to somehow predict what our branch predictor tells us, or PC plus 4, or fall through, or PC, the next instruction. We do not want to just have, we don't have to wait to the end of the pipe to know whether an exception is taken or not before we try to go get the next instruction. One other thing. When we start to go to out-of-order pipelines, we're going to start to need some recovery mechanism here. We're going to be processing instructions out of order. So if we might be taking an interrupt for an instruction after its let's say, subsequent instructions have either committed or sort of started to go down the pipe, and you start to get some out-of-order time questions. So we're going to look at a few different solutions to this for recovery. In our simple cases, we just basically flush the pipe and kill everything behind us. In more complicated things, we're actually going to have extra register files that are basically going to be shadow register files. They're going to keep track of everything that's going on in the processor, of what should have happened, and then we're going to dump that into our true into our physical register file, and we'll look at that maybe today or next class. We should bypass. Bypassing is good. You should not have to wait to the end of the pipe. Okay, so let's look at a time diagram here of an add that takes an overflow. Instruction 1 here is an add, and we speculate that it does not take any sort of exception. So we fetch the next instruction, we start sticking that down the pipe. In the execute stage of the pipe, we determine that there is an overflow. But as we said, we don't actually try to do anything about this until the commit stage of the pipe. So in our simple pipe, our commit stage is at the end of this memory stage. So we actually pipe it forward one stage. At that point, we restart the front of the pipe and we start fetching the handler code, the exceptional handler code. And we're going to basically kill behind us, turn everything behind us into a no-op. So let's say we're bypassing out of EX1 here into the, well, OK, let's say we go to this one instead. Or we can come out of here. Let's say we're bypassing out of the memory stage, or the memory stage, back to the register fetch stage of instruction 3. I think that's what you just asked about. What's going to happen is we're going to let that bypass happen. We're going to let that data come around through the bypass network. But what's going to happen is at that same time, we're sending the kill signal behind us in the pipe. Or instruction 1 is going to be killing everything behind it in the pipe. So we're going to bypass the data around. It's going to get bypassed. It's going to end up in the pipeline register at the end of that cycle, but it's going to be killed basically in the end of that cycle. A better example is actually here. Let's say it bypasses to instruction 2 from the execute stage to the decode stage of the pipe. That's actually going to get loaded into the pipeline register of the fetched operand. And then it's going to go forward into the execute stage EX2 here for instruction 2. So we bypassed it. We started executing that instruction. Everything was going fine. But then we just come along and we kill it. So we're speculatively executing, it's called. So it's a speculative execution pipeline. We are assuming and we're predicting that everything is going fine. And then we're going to be killing behind us when something goes wrong. OK, so now we get into the fun stuff, out-of-order processors. Up to this point, we've been doing simple in-order stuff. We've been hinting at out-of-order, but now we're going to start looking at truly out-of-order machines. And we're going to introduce a bunch of new structures that you should not have learned about up to this point. You may have briefly talked about a scoreboard, but we're going to start talking about a bunch of other structures. OK, so let's talk about different portions of a pipeline that can be in order versus out of order. The front end. So what do I mean by the front end? The front end is instruction, fetch, and probably decode. This is pretty hard to do out of order. Because you want to know, I mean, unless you've actually sort of can predict the future, it's pretty hard to know. So most of the machines we're going to be looking at have the front end being in order. So IO here means in order, OOO means out of order. Issue. So this is the stage in the pipe that actually says, all the operands are ready, go start executing the instruction. Well, so there are some things that can be in order, but you could probably even get more performance if you try to do that out of order. So probably not today, but next lecture we're actually going to talk about how to have the issue be out of order. Write back. So this is writing to something that looks like a register file, but not necessarily having hit the commit point of the processor. So this means that things are no longer in flight in the bypass network. It's been committed to a register file. I won't call it the register file just yet. Well, you can do that in order, out of order. Oh, excuse me, you can do that in order, out of order, different choices there. And then finally, commit. So this is saying, yes, I actually want these instructions to actually commit. And I'm basically, after that point, you're not able to roll back the machine state to a previous state. And we're going to look at machines where that's both in order and out of order. This is sort of a gentle introduction to out-of-order execution. And we're going to be building some different architectures. And this name here just is sort of a naming of 5 architectures we're going to look at as an introduction to out-of-order. The I4 is in, so or in order, in order, in order, in order. I2O2 is in order, out of order, out of order. Into out of order, in order is in order, out of order. It's the number just means how many stages in a row are the same as the letter before it. OK, so I want to briefly touch on some nomenclature over here. And you shouldn't know what these things are yet unless you went and read Shen-Lipasti, which I highly recommend. Scoreboard. This is a structure where we keep information about what instruction is ready to execute. Reorder buffer sometimes gets merged into a lot of different meanings, but typically when we execute instructions out of order, this is a place where we can go and actually reorder them to commit them in order. And we resolve all the dependencies so we don't actually commit out of order. Store buffer. This is something where we'll actually hold off storing to memory until the commit point, because we don't want to write to memory too early, because that would be bad, because then that would effectively be committing. So yeah, this is one important thing to remember about commit points is if you commit too early, what is an important notion of a commit here? Well, it's any state that you can't roll back. So if you do a store to main memory, that's a commit. That's really hard to roll back, unless you somehow can keep all that state of what was in that memory location before that. But people typically don't do that. Instead, you'll actually sort of have a buffer which keeps track of all the stores you're trying to do. And every once in a while, when you actually do a commit of the instruction, at that point and only that point do you store to main memory. And finally, we'll be talking about the issue queue, which is if you are issuing out of order, this is a structure which allows you to determine when it's safe to go and issue an instruction or not. And this is what's important about this is it keeps all of the dependencies, the read after write, write after write, write after read dependencies in check. And that's what that structure is doing. So we're going to look at some of these structures today. OK, so a motivational code sequence here. And this is a motivation for out-of-order execution. Here's a simple code sequence. And let's take a look at some of the read after write dependencies for this code sequence. Here we have a write to register 1 and a read of register 1. So that is a dependency there. So instruction 0 has instruction 2 as a dependence. So we'll draw a nice arc there. Let's see what else happens here. Instruction 2 writes to register 5, and that gets read in instruction 3. So that's a dependency arc there. OK, interestingly enough here, instruction 1 isn't dependent on instruction 0, and instruction 2 and instruction 3 are not dependent on that. So we can just put in a separate little bucket here. Instruction 4 here, let's take a look. Register 12, register 11. It reads register 11. So it's dependent on instruction 1. 5 is dependent on the output here, 12. So it gets put after 4. And likewise, 6 reads register 12. So it is dependent. So you have to start to think about if we have an out-of-order processor, we can choose the order of this instruction sequence and that instruction sequence. And if we have a multi-issue or a superscalar out-of-order processor, we can even think about trying to execute these completely independently at the same time, and we can get performance from this. Because we can find parallelism inside of a sequential execution stream. So one important thing here to realize is today we're going to be talking about how to dynamically, in hardware, schedule this and this at the same time. And we're going to be using this as a motivating example. In the VLIW, or the Very Long Instruction Word lectures, we're going to be talking about some software techniques that can determine when to execute this and this at the same time, and architectures which can take advantage of that, where the software has determined that these two things are completely independent. OK, so an important thing to realize here is that why do these even happen? Why do we end up with sort of non-dependent instruction sequences in a program? This is like a philosophical question. Should this even, why is this possible? So what do in-order instruction semantics, or excuse me, sequential instruction semantics force you to do to instructions? Forces you to come up with an order. You need to come up with some order. I need to write it on a sheet of paper in some linear order, or store it in my memory on my computer system in some order. An important point here is that in the instruction set architecture of a sequential computer, by definition, the instructions need to be serialized. This is a limiter. This is a problem in sequential machines. You need to come up with some order. So there is no way to express that this and this can execute at the same time in a sequential in-order machine, or a sequential machine rather, unless you do it something like this. You need to come up with some order. Like this is expressing the parallelism, but it's hard. The hardware has to go and figure out where that parallelism is now. You could think of an alternative instruction set, which is not sequential, but instead is a graph of different dependencies like this. And people have built those sorts of machines. They're not very common. They're typically called data flow machines. And if we have time for it, we'll have one lecture about that at the end of the term. So there are machines that allow you to express this and this are not dependent on each other. And maybe sometime in the future, they do become dependent based on some branch or something like that. So you can think about that. But in a sequential processor, you need to come up with some ordering. And this is a limiter for these machines. So effectively, let's say the compiler optimizations, knows that this and this can execute at the same time. By definition, if it can generate this code, it knows those two things can execute at the same time. Unfortunately, it has no way to express it. And that's a bummer. Very long instruction word machines, which we'll be talking about a little bit in the future, allow you some ability to say, I want to execute, let's say, this and this at the same time. But it's very limiting. Data flow machines allow you to do much more complex sort of graphs of instructions and say, this is dependent, this instruction is dependent on this instruction, and that's all I really need to say. And so effectively, sequential machines have over-constrained our designs. OK, so let's start evaluating our first out-of-order, in-order machine. So I4, this is actually an in-order machine, but we're going to be analyzing it as a motivator and then sort of a slippery slope, if you will, into true out-of-order machines. So here we have fetch, decode, execute, memory, write back. Same 5-stage pipe. I rename things a little bit easy to make it easier here. This actually follows the nomenclature that's in your labs, where the execute stage has an X and the decode stage is not ID, but instead D. But this should all look relatively similar. I took out all the sort of extraneous bypassing and other stuff in this pipeline. So it's a sort of caricature of a real pipeline. OK, so let's say we want to do superscalars here. Let's say we want to start adding multiple pipelines to this processor. So we're going to take the same processor pipeline, and we're going to split it off and have two pipelines here. We're going to have a memory pipe and an execution pipe. This looks similar to our A and B superscalar. But for today, let's focus on a in-order machine where these two pipes cannot have different instructions in the same stage at the same time. So we're going to look at a single fetch processor here, or a single issue processor, if you will. But this is a motivator. We'll see why we're doing this as we build up. It's a more complex out-of-order things. Most of these things hold actually for the multi-issue variants, but your head will hurt a little bit less if you think about the in-order variant, or the in-order single issue variants first. OK, as I said, yeah, things get a little more complicated. Let's take that same pipe that we had from before and add in a 4-stage multiplier. So now we have an execute stage, a single execute stage, which actually has some work in it. So this has an ALU inside of it. The memory, let's say, has 2 stages. This does the address computation. This is the actual memory access. And then here we have a multiply, which takes us a long time. It's pretty common. Multiplies are big, complicated beasts. So it was 4 stages of multiply. And then out over here, we have the write back. OK, so this gets us thinking. And we want to start to think what these things look like on the inside. So the first question is, do we want to bypass this pipeline? And how much pipelining, or how much bypassing do we need? In-order pipe, 3 pipes, or 3 functional units, we'll call it. 1, 2, 3. But we probably still need to bypass. Can we bypass out of right here? Out of Y1, does that make any sense? So the multiply is not done till here. So it makes no sense to bypass out of there. Do we need to bypass out of here? How about here? Here. OK, a lot of bypass locations. So this starts to, you can see the bypass exploding very quickly in this sort of pipeline. And that's pretty much to be expected. If you don't bypass, and you have to wait for everything, let's say, to get back to here, your clocks per instruction of your machine goes up. And we sort of go back to that simpler machine we had seen in earlier classes, where sort of you have to wait for instructions to go all the way to the end of the pipe. And that's a bummer. OK. Yeah, so that's what we just said. I did want to introduce this term, functional unit. So functional unit means one execution pipeline. So this is a multiply functional unit. This is the memory functional unit. This is the execute functional unit. OK, so now we're going to start introducing some extra structures and start talking about some extra structures, which will make our lives easier when we start to have multiple pipelines and complicated things are happening. The first thing I want to introduce here is the architectural register file, or ARF for short. So the architectural register file is where we keep the canonical state of the machine that has been committed. Hence, it's called architectural register file. If you see me say register file, that may or may not be an architectural register file. It may have in-flight values. But the architectural register file is the committed state of the machine. So we draw that sort of at the end of the pipe here, because that's where writes happen to this register, the architectural register file, as shown here by this W in the nice the nice pipeline diagram. We have W, and we try to read it at the issue stage of the pipe, or the register fetch stage of the pipe. I did want to say that when we went to go do this, we added an extra stage here. So we went to a 6-stage pipe because we're assuming that we bypass everything, and we want to have a little bit of extra time. And we'll see, for some more of the complex pipes, we'll start to put stuff in this decode stage. But for right now, decode does decode. Issue stage does some instruction steering to which functional unit, and not a whole lot more. So that's what's in our architectural register file. We read it here. We write it there. That makes sense. We may have to bypass some in-flight values around. But those are not in our architectural register file. Those have not been committed. Those are just in-flight speculative values. SB. So what's SB here? It's the scoreboard. So what does a scoreboard do? So we're going to show some pictures of scoreboards. But for right now, what our scoreboard is going to allow us to do is it's basically going to be a convenient side structure where we're going to keep track of where different values are in flight in these different pipelines. All of this data, if you go back to our earlier pipelines, was there. We had sort of the instruction registers that went down the pipe here, which in the control, which kept track of what was in each stage. The scoreboard is just a convenient place to put all that information and centralize it all. So when you go to build a pipeline like this, you don't want to have to go pick off of random locations in the pipe. It's easier just to sort of memoize that data in one location in the pipe, in the scoreboard. And when we start to go out of order, we're actually going to store some information in the scoreboard, which gets very hard to pick out of other locations. The scoreboard, read and write and write. What happens here? Well, we read it to figure out where we go get the bypass information from. So in this, we're not going to use that calculation we used before, but we're going to read it to figure out where the bypass information is coming from. And we're going to write it when we actually issue the instruction. So we actually issue an instruction, we have to update some information in there. And then as the instruction goes down to the end of the pipe, if the instruction actually commits, we also need to do something in our scoreboard. If the instruction doesn't commit or takes an exception, we also will have to do something at the end of the pipe. We'll have to clean up the scoreboard. So let's look at a scoreboard. Here's our basic scoreboard. This is for a long multiply pipe, the pipe we just saw. And we're going to keep track per real register. R0 in MIPS is a dead register, so we're not actually going to, or a register which has no dependencies going through it, so we're not really going to talk about that. So P. So we have one bit in here which says if there's a write pending to that register. F, or functional unit, keeps track of which of the three functional units we should be going to pick off the value from. So this is important when we go to do the bypass calculation, what's going on. And then we're going to have a shift register for each register, if you will, where we're going to inject a bit, and every cycle we're going to clock it forward. And this is going to tell us where to pick off the value. So this tells us which pipeline to look at out of 3, and the data available tells us in the other dimension what stage in the pipe to go pick off from. So if you go look at what functional unit you are and you cross it with this information, you should go figure out where to go do a bypass from. OK, so every cycle, logically, you can think of these bits shifting to the right. So it means the data, if there's a 1 here, that means the data for register 1 is going to be available in 4 cycles in the somewhere. Probably the architectural register file if you implement this relatively simply. Let's see, other things I wanted to say about this. I think we covered this all. Yeah. So you need to use the functional unit and the data available fields to figure out when to bypass and where to bypass from. And then if the pending bit is just 0, that means go look in the architectural register file. Do not go pick it off the bypass network. OK, now we get into a fun example, buyer motivating example that we saw at the beginning of class. So here we have that same instruction sequence we saw at the beginning of class. As we know, you can try to execute some of those things either at the same time or out of order. But for right now, we have an in-order, 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 in-order machine. But let's look at what the scoreboard has to say about this. So on the bottom of this graph, this chart, we actually show the scoreboard. And red denotes that the value is ready. So let's take a look at something here. So in cycle 3, we start executing instruction 0. Instruction 0 is a multiply. So what happens is it was in, sorry, so I want to actually explain this. Here's cycles. D means what's in the decode stage of the pipe, what instruction number is in the decode stage of the pipe. I is what's in the issue stage of the pipe. So 0 on cycles, instruction 0, the multiply enters the decode stage, then goes to the issue stage, and then it moves to the execute units. So it actually gets put into our scoreboard. And what happens is it gets put in for register 1 into its scoreboard just for register 1, and that just marches down the pipe every cycle. So every cycle, it's going to move to the right. And now if you look at the pipeline, if you look at the functional unit, and you know it's a multiply, and you look at where it is in the pipe, you can say, oh, this is when that value actually becomes ready. So we now know exactly where in the pipe and when, or excuse me, which functional unit and when that value is ready by looking at the functional unit and the bits in the scoreboard. If we look at something, let's say next instruction here is an add, instruction 1, it moves here, and then it just goes down the pipe. And it's ready basically the whole time. We don't have to wait for this value to become ready, because the execute instruction, you can basically bypass out of the execute unit, and it's almost always ready. That's why it's read the whole way down. And you can sort of see here that register 1, this is when that scoreboard entry is valid. And this is when the register 11 scoreboard entry is valid in time. OK, so let's look at our first real read after write dependence. So here we have a multiply, which is dependent on R1. As you can see, that instruction is going to sit in the issue stage until Y3 happens, then that gets bypassed down here. Excuse me, it gets bypassed down here into the issue stage, and then that instruction can issue. If we go look at the scoreboard, that corresponds to this becoming read, and then we can go and actually issue instruction 2 to here, and we've basically bypassed that value. And register 5, which is the destination of instruction 2's multiply, is valid. So this is a relatively simple pipeline design here, or a relatively simple processor. But what's nice here is you can use your scoreboard to keep track of when things become ready without having to go, and which pipeline to go look in, without having to sort of look at intermediate bits in the pipeline. And it's going to become much more important as we go to sort of out-of-order machines. OK, before we move on, does everyone understand how to look at one of these diagrams? Because you're going to have to draw these later in the course. So this is a great question. So let's look at this picture here. So we only have one entry per location in the pipe here. So you're saying we only have one of these entries. We have multiple bits going down here, but we only have one entry here. So what happens if you have, let's say, things which issue to 2 different functional units with different latencies to the same destination register? So that's a very important question. What's going to happen is you're going to fill in with this functional unit the newest instruction that gets issued's location. Because from a bypassing perspective, that's all you need to know. So that's very important. You don't need to know, from a bypassing perspective, something that was older in program order. We only need to bypass the newest value. One thing that we do need to do is make sure that we don't have a write after write hazard. So what that means is we're writing something later in the pipe than earlier in the pipe. That doesn't happen in this pipeline because we pipe everything forward. We don't actually have write after write hazards in the write back stage. The next pipeline we're going to look at does have a write after write hazard. And that's going to require us to think a little bit harder about the scoreboard. Exactly. Yep. So we're going to have, that's sort of the next pipeline diagram, is we have a much more interesting scoreboard. Actually, two, not the next pipe, but the pipe after that is going to have a more interesting scoreboard. One interesting thing to note is strictly for what we've talked about today, you don't even need bits. You don't need to track 2 different writes to that same register, because you only need to know the most recent write to the register. So one way that I've seen people build scoreboards is instead of having bits marching down here, you just have a encoding, like a log base 2 encoding or a binary encoding of where to go look in the pipe. for the newest value, and then you just increment that or decrement it every cycle or something like that. So you just have, instead of having shift registers, you can have that. And that's strictly enough for this. The more complex pipes we're going to look at, as Pramod said, we're going to have to track both the location, or the functional unit in the pipe, and what stage in the pipe it's in. So you're saying, how do I know that this is not ready until 4 or something like that? OK, so that was a subtle point, is that if you know what functional unit, if you know the functional unit latencies, you just look it up in a table. You don't need to actually track that information. There's just some piece of logic which says, for a multiply, if the functional unit is multiply, then we can't bypass till here. If it's an add, we can bypass from here or there or something like that. So you don't need to track that in a table. It can just be part of your combinational logic in your decode unit or your issue logic. Does that, you don't have, I'll say it one more time. To see this, like this is this example here. We have a mul that writes R1 and something which else is supposed to read R1, but we end up stalling here. In this table, the way we know that is we know the functional unit. And because it says multiply, we know that we have to wait until it gets to here, or rather probably here, instead of trying to pick it off earlier. If it said ALU, then we could have it pick it off earlier. So we don't necessarily have to encode that. That's why in this picture here, things turn red on some of these earlier than others. It's that functional unit information which encodes that. You could even think about having that functional unit bits encoding some number, like you said. Some people design scoreboards like that. OK, so I just wanted to briefly introduce this, and then we're going to break. Next class, we're going to be talking about in-order front end and issue, out of order, write back and commit on these pipelines. It looks pretty similar, except some pipeline stages are taken out here. And this makes you think harder about when to go read the scoreboard. So we're actually going to use this decode stage to do some stuff with the scoreboard. And then we're going to start talking about truly out-of-order machines, where you have these other fancier structures like reorder buffers and store buffers. OK, let's stop here for today and pick up next time. OK, so today we're going to pick up where we left off and continue talking about out-of-order processors. And things are going to start to get a little complicated, but that's good. We don't want to build, well, we want to try to build simple things, but we also want to build high-performance things. So let's start talking about some more complex out-of-order processors than we talked about last time. So last time we talked about in-order processors, and we introduced a scoreboard. And then we started to talk some about in-order, where the front end of the machine is in order and the issue is in order, but the write back and the commit are out of order. That also uses scoreboard. And today we're going to start talking about things that even have higher performance. And this is sort of roughly put in a sort of order of performance and sort of what people build if they actually want high performance in their computer systems. And we're going to start talking about in order in the front end, out of order in the back end. And we're going to have to introduce things like a reorder buffer and a store buffer. And then we're going to talk about a machine which has in order front end and all the back stages that are out of order, which may not make a whole lot of sense because out of order commit starts to look a little odd. Likewise, that's the case for this processor. And so why does out of order commit look a little odd? Well, when you start to have out of order commit, it's very possible that you could, if you want to have a precise exceptions point, depending on how you sort of implement that processor, and depending on where you put the commit point, if you put the commit point, let's say at the end of the pipe, it's very possible you'll commit results to your register file or your architectural register file before you know that those results are good. So you've basically just execute instructions and commit information which is not correct in program order. And we'll show some examples of that today. And then finally, we're going to talk about sort of the highest performance thing here, which is a in-order fetch, out-of-order issue, out-of-order execute, and write back, and then finally an in-order commit. So this, you can have precise exceptions, have a commit point at the end of the pipe. And for this, we need to introduce an issue queue, which is where the instructions sort of live for a while as they are getting ready to go issue. And this allows us to do out-of-order issue. Just to recall back our motivating examples. We're going to be using this example throughout today's lecture again. 2 different instruction code sequences, not dependent on each other. You should be able to execute these things in parallel if you had enough parallelism in your machine. and we talked about this already, so I'm going to skip past the in-order machine and get to in-order, front end and issue, and out-of-order, write back and commit. So in this processor, we're going to have basically 3 pipelines here: a long multiply pipeline, a memory pipe that, say, takes 2 cycles, and then a short ALU pipe here on the top. We have a scoreboard like we had before, and this is going to track where data is available in the pipe. Where data is available in the pipe. And the architectural register file is sort of sitting at the end. So this looks relatively similar to the in-order issue, in-order write back, in-order commits processor. But there are some interesting things here. If you compare this picture here to this picture here, we just dropped all these pipeline stages. So that's pretty cool. We don't have to bypass out of there anymore. We can just sort of shove the data in the architectural register file. And if we preserve read after write, write after write, and write after read dependencies, things should be OK. But let's see if we can actually do that. So let's first take a look at the scoreboard for this in-order issue, in-order fetch, in-order issue, out-of-order execute, and write back, and out-of-order commit processor. So the scoreboard looks very similar to the in-order machine. And we can use it to track structural hazard on the write back port. And this is really important. If you try to have, let's say, a multiply and then an add after it, it's possible that the multiply and add, if under pipelining, might have to go use the write back port at the same time. So you get a structural hazard. And we're going to show a pipeline diagram of that happening in the next slide. We still don't actually need to have a more complex scoreboard. So briefly, someone asked in last lecture, in the scoreboard, do we need to track which functional units each value is going down the pipe? We still don't need to do that for this relatively simple pipe, because for a write after write dependence, we're basically just going to stall. If you want to break that requirement, then you need to start tracking more complex things in the scoreboard. And you may even want to have something like a register renamer, which we're going to be talking about next class. And that's going to allow you to basically break a write after write dependence dynamically in the processor. So an important point here, because these pipe stages are different lengths now, in our scoreboard, we had different places where the bits, where the entries in the scoreboard could be. But now if we go to execute an instruction which is long, we're going to put it in a 1 in sort of the first entry in the scoreboard, and it's going to march down every cycle as tracking the information as it goes down the pipe. But if we're trying to, let's say, execute a add instruction, it doesn't actually have to wait 4 cycles to get into the architectural register file. So we can actually insert here a 1. And then it just marches down the balance of the pipe. for a particular location. And this is what I was saying, that because we're not going to allow write after writes hazards on a particular register, you're never going to have a case where there's basically multiple inversely ordered bits in this table. If you had that, you would actually have a more advanced scoreboard, and I'll show a picture of that a little bit later in today's lecture. OK, so let's go through an example of how to use this scoreboard and how to walk through a in-order issue, in-order fetch, in-order issue, out-of-order execute, and write back an out-of-order commit processor. So here's the same code sequence we had in the previous example case. So we're going to be using this throughout all of the class. Let's take a look at this and sort of see how this pipeline diagram happens and notice a few things. First, let's take a look at some read after write hazards and what the pipeline has to do. Mul R5, R1, R4. This reads R1. Well, R1 is created by this multiply in instruction 0. So it actually has to wait to get the bypass here from instruction 2 is going to have to wait to get this value. So you can see here it's basically just stalled. And what's happening here is your in-order issue. You can't go try to issue subsequent instructions under that. Later in today's class, we're going to be talking about pipelines which actually have out-of-order issue, such that while this is waiting around, you can think about trying to go and issue the next instruction that's not dependent on that previous instruction. And by doing that, we can get more performance, because we can basically be reordering instructions and trying to use our functional units and use our ALUs as much as possible. But for right now, we have a bypass coming out of Y3 here, out of this multiply down into the register file access stage of that next multiply. So that's sort of one thing that's going on. Let's take a look at another read after write dependence here. So another read after write dependence is actually register 11 gets written here and read down there. Well, what do we have to do anything special for this? So it sort of marches down the pipe. The write happens here. Let's see where the read for this instruction, instruction 4, tries to happen. Well, the read tries to happen there. Well, at that point, the data is actually in the architectural register file. We don't have to worry about any funny bypassing or anything like that. And you can sort of work through the rest of the things going on here. But there's a few other things I wanted to point out in this picture. First, because you have different pipe lengths, you can actually see that, let's say this add here is writing the architectural register file before a previous instruction writes the register file in program order. And this has some consequences, some large consequences, when you're starting to think about if, let's say, this instruction here, the multiply that preceded the add took some sort of fault or took some sort of exception. Because now you've basically changed the architectural register file before before that other instruction has finished. And that other instruction didn't actually finish. So what does that mean? One other thing I wanted to point out in this picture, which is a really interesting case, is right here. So this add instruction here is dependent on R12. R12 gets created here, and basically at the end of the stage, it's ready to bypass. So if we look down, we'll say, well, this instruction here, we don't even try to read from the bypass until here. So that value is ready. But for some reason, this instruction stalls. Can anyone see what's going on with that instruction? All of its inputs are ready. It's ready to go. It's a party to go to, but it doesn't issue. OK, so that is what's happening here, is that if you were to remove this I stall stage here, this would get pulled forward, and now you'd have this writing and that writing at the same time. So we actually have a structural hazard on the write port of the register file there. So you have to stall. OK, so let's take a look at how that shows up in the how that shows up in the scoreboard. So when we go to sort of look at this, so what we have here is we have cycles. There's 18 cycles across the top. Or actually, there's 19 cycles across the top. The first one's 0, but I don't draw that. If we look at, let's say, this cycle here, instruction 1, which is this add, is in the I stage. So it's in the issue stage of the pipe. So it's looking for its operands, basically. And what's going to happen is this add needs to check to make sure that it's not going to conflict on the write port of the previous mul. In this case, it doesn't actually happen. But when this instruction moves to here, so this is what I was saying, is that it doesn't actually put ones in the 4 location and sort of marches down. Instead, it's going to start here at the with only 2 cycles to go before it writes the register file, because the pipe is shorter. So it has to check this location and says, well, for my register that I'm trying to write, is anything else currently scheduled to go write that location in 2 cycles? And our scoreboard can answer that question. If there was a 1 in this box, yes, we would know that there was a mul or some other instruction that had long latency that there would be a conflict. So when this instruction were to move here, this 1 would also clocks every cycle and moves down our scoreboard. It's going to conflict at that point, and we're going to know we're going to have a write hazard on the register file. So we can sort of see those things happening in our scoreboard. And then we could also use our scoreboard to actually detect that real case. So this case here, this last instruction, this last add, we're going to see that show up over here. So let's try and find that. OK, so we have instruction 6. It wants to basically move forward in the pipe. But it checks this location here and says, OK, or in this cycle here, instruction 6 basically should be in the issue stage. And it doesn't move out of the issue stage. It's sitting in the issue stage. And it looks in this location, which is basically two cycles till the ends of the pipe, and sees that there's a 1 there. The box is trying to indicate that. So it looks there and says, oh, there's a 1 there. That means I can't issue this stage, and I need to stall. And we get this stall showing up. These other boxes are here to here to represent the other adds that are happening and the other muls and things. So we actually check these other locations. Actually, this is just the other adds. These are, we're going to check for this add here, this add here. This add checks here and sees a conflict, so it has to check again the next cycle. That's why there's 4 little boxes vertically on that chart. Other things, this is just a different representation here. You can see R1 is being written, and it has a long latency in the pipe. This other register has a shorter liveness time because in our scoreboard because it's an add instruction. OK, so do we have any questions about that before we move on to a more complex pipe? So this is assuming a fixed latency for every instruction. That is correct. Or at least per pipe or functional unit in the pipe. You can definitely have functional units which have variable latency. So an example of that is, well, there's sort of 2 good examples of that. One is something like a divider unit. Sometimes people build divider units so that you keep dividing until you're done. And it's sort of a way to shorten the length of a divide. So that sometimes has variable length. Another good example of this is something like a load that misses in your cache in an out-of-order processor, and you have to wait for the load to come back. Good ways to handle that, actually, in a scoreboard. Sometimes scoreboards will just have an extra sort of special bit on the side for each destination register, which says, this register is just out to lunch. It's in some long variable length pipeline. I don't know what's happening on it. Don't try to bypass it. Don't try to do anything special with it. And just wait for it to come back and that bit clears. So processors I've built for these variable length instructions will typically just have an extra bit for maybe the different functional units, like one for maybe the divider and one for the load miss case or something like that, such that if that exceptional case happens, or if the load misses, or if you go and take a divide, which has a variable length, because divide can take anywhere from like 2 cycles up to like 20 cycles in some pipelines, and in everything in the middle, you'll just mark a bit saying, this register is not ready in the scoreboard. And then if someone tries to go read that register, it just knows to stall. So it's just a slower performance sort of way to deal with that. But that's a tough case to handle. But a scoreboard can help there, and it's a sort of extra information in the scoreboard. OK, so like I said, we have this out-of-order commit processor. It's doing out-of-order write-back, and it's doing out-of-order commit. Ooh, well, out-of-order write-back may be OK. We maintain our write after write dependencies, so we're not actually going to end up with incorrect state in the architectural register file because of that. But something bad can happen is what happens if we go and try to take an exception. So let's say we have our same instruction sequence that we've been looking at up to this point. And here, we're wandering around. We're going down the pipe. And this instruction here takes some sort of fault, and it's figured out at the end of the pipe at our commit stage. So the multiplier goes all the way down to the end. We end up with, I don't know, multipliers don't take a whole lot of great faults. But let's say it takes some sort of exception. What is going to happen? Well, that instruction is dead. All the other instructions are dead because it took a fault. Unfortunately, we already wrote the register file. Dun, 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 dun. Yeah. OK, so now we end up in our trap handler, or our exception handler, or interrupt handler. And all of a sudden, register 11 is just wrong. It has the wrong architectural value. So this is one of the reasons why people should try not to build out-of-order commit. It gets tricky to have out-of-order commits with precise exceptions. Now, there are some ways to do it. So one way is limit the types of instructions. So if you have an in-order issue, out-of-order commit, out-of-order write-back, what you could think about doing is, you know that this doesn't write until this point here. So what if we resolve all of our previous, let's say, all of the previous exceptions? If we move our commit point earlier in the processor, we can actually make this work and have precise exceptions. So if our commit point, let's say, is in the either memory 1 stage or first stage of the multiplier or something like that, at that point, we haven't written any other state here that's wrong. That write back hasn't happened. So we can still kill everything down. Unfortunately, that means that you can't have an exception happening here, or anywhere else sort of like later in your pipe. So that's a problem. So you can limit the types of exceptions, push your commit point early, and still have an out-of-order commit processor with precise exceptions. But that even is tricky. So this is a great question. So why can we not have 2 commit points? Some processors do have 2 commit points. And some processors will have, it's called sliding commit point. So that you try to commit things sort of early, and then if something else, for certain types of instructions, you can move the commit point later. But typically, you want to have a commit point in one place where you say, after this point in the pipe, all of the state is past this, has been committed, and those instructions cannot be rolled back, and those instructions cannot be undone. But there are examples of things where people will have a sliding commit point. I've actually built a processor which has a moving commit point, but it gets tricky because what it basically means is certain types of instructions cannot execute after certain other types of instructions, because if they do, you sort of violate that sliding commit point. Like this example here, if the fault can be taken here, there's no way to solve this problem. But you could have something where there's a sliding commit point where if you have a mul followed by, let's say, an add, you can actually sort of slide the commit point out. So there are processor ideas that you can try to have a sliding commit point. But otherwise, you have to check. That gets quite a bit complicated. But I don't really want to get into that today. Let's leave that for sort of advanced topics discussion. But in what we're going to talk about in this class, we're going to say we want to have one commit point, and we want to say one place in the pipe is the canonical location that past that point, all the data that is in flight has executed and is committed. And we need to know sort of one location for that. OK, so now we get to move on to even more complicated processors. In order front end, in order issue, out of order write back, and in order commit. OK, so this is going to solve some problems that we have. The biggest problem it's going to solve is it's going to solve a problem of precise exceptions. We can now have exceptions sort of all the way at the end because we're committing data in order. So let's take a look. That should probably have a line there. You can scribble that in on your own drawings. OK, so let's take a look at some other structures we've added to this diagram to make life a little bit more interesting. OK, the front end looks pretty much the same. We split the load and the store apart into two separate pipes here, a load pipe and a store pipe. And the store pipe is shorter because it just has to basically do a store, we'll say. Maybe it's 2 stages. Doesn't matter that much. It's not that material in this drawing. But something interesting to look at here is we added a bunch of extra boxes over here on the right side of this foil. So let's define these things. So we had our architectural register file, which is our committed state to the processor. And we added a second register file, typically called a physical register file, or PRF. Sometimes people call this a future file. And you'll see that in the literature. There's some papers published about future files. And the reason it's called a future file is it's basically executing speculatively in the future. The values in here have not been committed to the processor. They can be thrown out. If you take an exception, if a branch happens, for a variety of reasons, these are speculative. You're not guaranteed to actually have to keep those. The architectural register file, though, is committed state. OK, we added 2 other structures here. Something we call a ROB, or a reorder buffer. And we added a finished store buffer. So let's talk about the reorder buffer first. So in this pipeline, we actually want instructions to basically execute and write the physical register file out of order. Because this is an out-of-order processor. We'd like that to happen. We're basically making the execution and the write back out of order. But we want the commit to be in order. So we need some structure that is going to guarantee that the write to the architectural register file happens in order. And that's what the ROB is going to do. So what it's going to keep is it's going to keep completed instructions and that could come in out of order and are going to leave in order. So things come into this out of order, and they go out of it in order. And this is a reordering structure. It's typically a table. that is sort of written. Well, we'll talk about that in a second. It's written in different places in the pipe for a couple different reasons. But you typically want to keep track of the instructions in order somehow. And then when you go to pull out of the reorder buffer, you want to pull in order out of it. But the writes and the tracking of the information that happens to it can be out of order. And the other thing here is this finished store buffer. The reason we have this finished store buffer is if we have a store operation, we don't want to have the commit point like here so early in the pipe. Because once you store to main memory, it's really hard to go get that back, possibly even impossible. It probably is impossible. You wrote to the main, if you had the old value and you overwrite it with the new value, the old value is forever gone in your main memory. You can't get it back. So the solution to that is instead of doing the store here, you have the store happen later in the pipe, and you just sort of remember what you're supposed to do, the address and the data that's supposed to be happening. And for anybody who cares, that store has happened if it hits this future store buffer. So you probably need to have your loads check that future store buffer with higher priority than your cache, because there could be a store living in that location. OK, so that's the sort of structures here. Let's talk about where things get read and written. This one's really interesting. Our architectural register file isn't read anywhere. What's up with that? Well, we're going to use the physical register file for all the intermediate values in our pipeline. And the architectural register file is only there if we take some sort of, let's say, branch or interrupt. And that's the only time we actually need to go take this information, and we probably want to dump it into the physical register file or dump it into the future file when an interrupt happens or when a branch mispredict happens. But otherwise, it doesn't have to be read. Scoreboard is the same as usual. Read and write in your register fetch stage, written at the write back stage. And that's no longer tracking architectural register file registers. It's now tracking physical register file registers. Reorder buffer. This one has a whole bunch of different places it gets read and written. Primarily, what's going to happen is when the instruction is issued, so it goes from the decode stage to the issue stage, that's going to allocate a location in the reorder buffer for the entry in the reorder buffer. And then at the end of the pipe, once the value completes, we have to change some state information in the reorder buffer saying, oh, that output register for a particular instruction is now ready. And then once we actually go to do the commit, we have to basically clean that instruction out of the reorder buffer. The future store buffer is written just sort of at the end of the pipe here and cleaned when the actually posts to main memory. It's a little hard to draw this, but that information, somehow through the memory system, if you have a load that reads from that, we'll probably read it either in L0 or L1 in a sort of a bypassing mode, if you will. It'll go check that structure. We'll talk more about that next class. OK, so here is sort of a basic reorder buffer. If you go look in some books, they have a lot more data stored in a reorder buffer. But this is kind of the minimal reorder buffer you need for an out-of-order pipe. And this reorder buffer is used to keep track of in-order committing of instructions, but things will be put into it out of order. So just let's first talk about the sort of information in here. We keep track of state. So what do we mean by state? So this is the state of an instruction. So each one of these entries here is a different in-flight instruction in the pipeline. And we're actually going to store in order into the reorder buffer. And we're going to keep it sort of as a queue. So this picture here, this state is, we'll say dash dash means free, and P means pending, and F means finished. Probably should not have chose two F words there. That's a little confusing. But the newest instruction is, if we have a new instruction execute, it's going to end up here in this entry. And when an instruction commits or retires, it's going to remove this entry, the bottom entry. So we basically have a sort of circular buffer running around. There's a head and a tail pointer sort of chasing each other in this data structure. So tail, head. What's interesting about this, and why this is cool, is because let's take a look at this instruction right here. This instruction has an F, which means it's finished, that it's not pending in the pipe. It's hit the reorder buffer. The data is stored in the physical register file. But instructions that are older than it, which would be these two instructions, are still pending in the pipe. So let's say these are two multiplies, and this is an add. So this add is basically already done. These two instructions, which are these long latency instructions, are still pending in the pipe. In this cycle, we cannot commit anything. So we only commit instructions when the oldest instruction becomes finished. And that's when we can commit and remove something from the reorder buffer. Some other things we need to keep track of here. We have a bit here, S, for speculative. So what this means is if you have something like a branch, you mark instructions that are newer than the branch with a speculative bit. So what this is saying is if that branch mispredicts, it just gives you a convenient place to go find all the dependent instructions on it to go flush and kill. So if you have, let's say, one branch is allowed in the pipe at a time, and the branch mispredicts, what you can do is basically look for all the entries in here that have ones and just invalidate them ad hoc and just flush the entire pipe. You don't have to worry about there being some value you need to worry about. So it's just a convenient way to figure out which instruction is speculative, and if the branch is mispredicted, what you have to kill. Stores. We'll be talking about this in a few more slides later, but store bit, what it's really going to do is this is going to say, if this instruction is a store, it knows that we need to do something else with it. We need to do something with the future store buffer when it gets to the end of the pipe. It's sort of a convenient place to put it. And then here's the actual business, the business part of the reorder buffer. V, which says that the instruction actually writes a register. And then finally, once the instruction goes all the way to the end of the pipe, it is going to fill in a location in here, which is the physical register file entry that is the destination of that value. So this basically allows the pipeline to know where to go find the actual value. We don't actually store the actual values in here. We just store a pointer into the physical register file because it's fewer bits. And this can tell us, oh, well, go look, let's say, when this instruction here, which is already finished, is ready to go retire, or it's ready to go commit, go look in physical register file number 7 or something like that, and it goes and pulls that value out from there. So a good discussion of this is in the Shen Lepaste book that is sort of supplemental material for this class. OK, so let's talk about the does anyone actually have questions first before we move on? Because reorder buffer is a key data structure here, and it's a complicated one. OK, great. Next structure we added was the finished store buffer. And this could actually be multiple entries, but for this pipe, let's just say there's only one. So we're only allowed to have one store pending in this pipeline, because it makes life a little bit easier. Things you sort of need to actually have here is you need to have both the address and the data, whether it's valid, probably the opcode. Maybe the opcode will tell you if it's store byte, store word, sort of data width types of things. And that's most of what I wanted to say here. This is what I was saying before, is if you allow multiple loads and stores in the pipe at the same time, you're going to have to bypass from the finished store buffer to the loads. and possibly even stores if it has to write combine. So if you sort of store to different parts of a word, you may even have to bypass that, depending on how your pipe works. Or you can assume that there's only one memory instruction valid in the pipe at a time. You can have one of these entries, and no loads can happen while a store happens. That's not very good performance. People probably would never actually build that, but that's something to think about. OK, so now we get some more pipeline diagrams. I run those pipeline diagrams. And we're going to see how this is different and what happens in the reorder buffer. First thing I wanted to say here is this little r that you see show up in these diagrams. That means that we've written the reorder buffer, but we're not ready to commit. So from here to there, we basically have this add has written the reorder buffer, and we're waiting for it to commit at the end of the pipe. But we can only commit in order. So you can sort of see these C's are all lined up in time. So we're only able to commit from left to right, and we can't reorder one of those C's relative to another C. Let's see, what did I want to say here? That was the main thing. The dependencies are the same. It's the same code we've looked at before. That's what I wanted to say. Which one is that? Yes, it's this one. OK, so here we have this add writes register 12 right there. This add goes and reads register 12. So we have a read after a write happening. What's interesting here is this read after write that's happening. The write happens there. The read happens, let's say, here. That data is not in a bypass anywhere, or it's not in the forwarding logic of the processor. That value is actually in the physical register file. So this is kind of showing an example here that data, when you're doing the bypass, can come from bypass network locations. It can come from the physical register file. And those are sort of the two places it can come from. But everything else actually in here, surprisingly, is basically coming from bypass, except for that one location. So bypasses end up being really important. But you can have data coming from the physical register file. So could the C be here? Could this C move over one? So it's commit in order. And we can only commit one thing at a time in this basic pipe. More complex pipes, we're going to allow multiple commits at the same time. When we start to mix superscalars with out of order, at the end of today's talk, we're going to be able to think about trying to commit multiple things at the same time. But we can't really do out of order, so these has to be monotonically going that way. Brief example here. This is kind of fun. This is trying to show different entries in the reorder buffer and when those things get allocated. And largely what's going to happen is for a destination, so let's say instruction 0 here allocates the reorder buffer, and R1 becomes active. And it's a long latency. It's a multiply. It doesn't show up. The circles here mean that the instruction is finished. It's gone to the end of the pipe, and it's ready to go. You could have other things, like this is an add that happens to register 11. It allocates, it finishes early, but it doesn't commit till late. So it has to stay in the reorder buffer. So it takes up space in the reorder buffer. And you can sort of see other examples of that. These adds here finish relatively quickly, but they have to wait to commit in order. And they're basically dependent on this instruction here committing before they can go commit. So it's a nice little structure that can track all of those things. OK, let's look at commit points and if exceptions occur. We're going to have the same example we had before. The mall here is going along, and it write-backs to the physical register file. Now you're going to say, whoa, it wrote the register file. How can it take an exception at this point? I thought if it took exception, it wasn't supposed to write the register file. But we have two register files. So it writes the speculative state register file, or the future file, or the physical register file. And the slash here means we don't actually commit that instruction. So the commit doesn't happen. Now we get to go look at sort of other in-flight instructions to see what's going on here. Can these other in-flight instructions potentially write information out of order, and where can our commit point be? Well, here's this add that before in the previous example wrote to the register file, and now it writes to the physical register file, but does not write the architectural register file. Instead, it enters the reorder buffer here, denoted by the little r, and it just sits there until it actually gets a chance to commit in order. But that doesn't get a chance to commit, because a previous instruction kills it, and because it takes an exception, and kills everything. And then you can go and start some new instruction here, let's say, that is the exception handler, and fetch that out here. One interesting thing about this example, actually, that I wanted to say is sort of in this transition, lots of state has to change in the machine. You've taken an exception. The architectural register file is correct. The physical register file potentially has many incorrect information, or many incorrect values in it. So on this transition, what's really going to happen is you're going to copy all of the state of the architectural register file, all registers, over on top of the physical register file. So you basically rolled back all of your speculative state in the machine in one fell swoop. Obviously, that can maybe be a little bit expensive, but you don't take interrupts that often. You do take branches relatively often. We'll talk about that in a second. But what's nice, that's logically what's happening. Sometimes people will actually commingle the architectural register file and the physical register file, and they just sort of keep pointers to different pieces of information. So you don't actually have to sort of roll back information. You just sort of change the pointers. But for right now, let's model it as two completely separate register files where we copy all the state from the architectural register file to the physical register file on some form of rollback on an exception or a branch. Branches. So how do we make the branch latency better? Or what do we do on a branch, first of all? So sort of ignore these bottom examples here. This is a different code sequence that we've been looking at. This is not the multiply, add code sequence. Instead, this is a branch. So we have a branch. The branch commits. We know the branch is good. But these instructions here are the fall-through case for the branch. This instruction here is the target for the branch. So we need to squash all of these instructions in the reorder buffer. Conveniently, we have a bit in the reorder buffer that says all of the things that were dependent on the branch, if the branch is misspeculated, just remove them from the reorder buffer and basically throw everything out of our reorder, or throw those entries out of the reorder buffer, invalidate them in the reorder buffer. What gets a little interesting here is when do we start to execute the target? Well, let's say we compute the branch information here in the execute stage, and we can sort of redirect the fetch stage. That's OK. But this squash is a little bit odd, because what this really says from a pipeline perspective is that you have to invalidate multiple entries in the reorder buffer in one cycle. And this, to some extent, is a structural hazard on the reorder buffer. You might need many ports into that reorder buffer, or you need to at least keep the valid bits in some other extremely highly ported structure. You could think about doing something even more interesting, where you kill instructions early. So the difference between this picture and this picture is once we compute and figure out that the branch is taken, we just instantaneously squash all these instructions, and we change the reorder buffer. Or we write to the reorder buffer, killing all the speculative instructions. Now, if you note, this doesn't actually help performance in this case. Places where this can help performance is if you have an out-of-order processor that's a superscalar processor. You could think they could try to sort of put other instructions in these locations in the pipe, or try to restart earlier, or have other things go on in the pipe, and you're just using less resources in the pipe. So this is going to be the highest performance case. This is sort of going to be medium performance. Low performance, you can have a way that you don't actually have to add extra ports to your reorder buffer. And the way you can do that is you let the in-flight instructions that are dead continue going down the pipe until they get to the commit stage, and only then do you clean them out of the pipe. And you clean it out of the reorder buffer. So you sort of are waiting for these speculative instructions to reach the commit stage and then squash them there. In this example, the performance of all three of these are the same. But I will say this is going to be the lowest performance if you have a more complicated code sequence, because you are basically using up a lot of pipeline resources. You're using entries in the reorder buffer. You're using locations in the pipes that you could try to reuse for something else. OK, so as we said, we sort of have these three different cases in increasing complexity. But you get some performance. Oh, sorry, in decreasing complexity, but increasing performance. So I think one thing that definitely comes up, and this is probably going to make this multi-ported issue come up, is if you start to have multiple branches in the pipe at the same time, then the simple case of just moving the tail pointer is not really going to work, because you might mispredict one of the branches but not the other branch. That's going to mess you up a little bit. OK, so let's keep moving on here. Avoiding stalls due to store misses. OK, so you got a store in the pipe. It takes a cache miss, and now it's clogging up the commit point of the processor. Because depending on how you want to look at this, maybe you don't want to commit until that store has actually reached main memory, because that's what you're going to call commit for that store. So you can't necessarily pull it out of the future store buffer, because it's not able to actually sort of commit. You try to pull it out of the future store buffer and write it to main memory, or you write to your cache. It misses in your cache and takes a couple extra cycles. So we'll see like this. Here's a store word, and let's say it takes a few extra cycles here, 3 extra cycles stalling to actually go and write the level 2 cache, we'll say, or pull in the data from the level 2 cache into the L1 cache and merge there. So there's a way to solve that. And what's bad about this is because we're doing in-order commit, it pushes out the rest of these instructions later. And that's kind of bad. So what you could think about doing is adding an extra stage in the pipe and just allowing the store to miss and basically moving it past the commit stage, saying this store has committed. You sort of mark it down and say, well, it's committed. I don't have to worry about this anymore. And you basically can decouple the end of the pipe here, or the store actually happening to memory, until later. And what it allows you to do is you can basically have commit in order. You can pull back these things earlier. This looks like a typo. This should probably be back 1. And then you can commit in order and have that store sort of still outstanding out to main memory. One important thing you need to do here is, as I have said before, if you let another load into the pipe or a store into the pipe, you're going to have to bypass out of this data structure and that data structure now back to the load stage of the pipe or the store stage of the pipe. And that adds extra wires into your out-of-order processor. But we've basically decoupled store committal from, or it's technically committed once it gets past this point, but it's not in main memory. But it's to everyone else and to the processor, it looks like it's been committed, because you try to go read the value and it looks like it's committed. in-order fetch. So we have an in-order front end, and we have out-of-order issue, write back, and commit. So what this is going to try to do is we're going to try to fix some of the problems that we saw here, where we'll actually had, let's say, this instruction here, this add, is waiting to issue because our issue was in order. So that instruction could issue. All of its inputs are ready. R11 was written right there or something like that. So R11 is ready. It's ready to issue. But because we have in-order issue, by definition, we can't issue out of order. So now let's look at a machine where we can issue out of order. So we can actually move it to the execute units, do our register fetch out of order. So to do that, we actually have to add another data structure. And this data structure we're going to call the issue queue. And this is going to be something like an associative FIFO, but it's not going to be FIFO. We're basically going to store instructions into it, and then we're going to put instructions into it in order because our fetch is in order, or our front end is in order. But we're going to pull out of it out of order. But we have to be a little careful because when we go to pull out of that data structure, we have to make sure that all of the appropriate registers are ready. So all of our dependencies are ready, or at least somewhere in the bypass, or we can go pick it off the bypass by the time it actually needs the value, or in our bypass stage. Let's take a look here. We still have an architectural register file. We got rid of all of that complex reorder buffer stuff on this example. So we don't have a reorder buffer. We don't have a store buffer. We have out-of-order commit. So we're going to have the same problems we had before with precise exceptions in this pipe. But this is going to give us sort of an easy introduction to understanding what the issue queue looks like. So the issue queue gets written when instructions enter it. So sort of at the decode stage, this is itself is a register structure. So it's like flip-flops in here and a bunch of logic and stuff. So you can't just go from this stage to this stage in the pipe without having any registers. So it gets written there, and things are basically going to update into this. So when things actually end up in the architectural register file, we're going to mark bits in the issue queue saying, oh, that register you're waiting on, it's now ready. And if you get, let's say, 2 registers that are ready and you are dependent on 2 registers, you can issue. And we can issue out of order. OK, so I have read and write here in the issue stage. Why do I have that? Well, when you actually go to issue it, you basically want to mark that instruction as, oh, yeah, I actually did issue this instruction. You want to sometimes people build this as actually remove the instruction from the issue queue. In this basic case, we're going to leave it in the issue queue until the end of the pipe because we need some way to track the liveness of the instruction. But the next processor, we're basically going to think of it as sort of a, I won't say FIFO because it's not strictly first in, first out. But it's a data structure where you can put stuff in and then remove stuff out of. So it's a buffer, or a multi-entry buffer. OK, let's take a look inside of the issue queue. And this is assuming something like MIPS. So in our issue queue here, we're going to have, first of all, we're actually going to have the opcode, because we're going to have multiple instructions sort of ganging up in here. So it's possible there can be like, I don't know, in this case, 1, 2, 3, 4, 5. There's 5 instructions just sort of sitting in this data structure. So you sort of slacken, there's a buffer and slack in the front of your pipe, effectively. You might need the immediates values, because that's sort of part of the opcode, or part of the instruction. And then we're going to basically have things for the 3 different registers. And what we're going to put in here is we're going to put the register identifiers. So here, let's look at the sources first, because that makes a little more sense. The V bit is going to say that this instruction needs the source. So it's possible that, as we said, there's some like immediate instructions don't read both source operands. So for an immediate, only one, probably this valid bit is going to be set, and this one's going to be 0. The p bit is pending. So what that means is somewhere later in the pipe, there is a in-flight instruction that writes to that register. So we're going to basically track that with a bit here, saying that is still pending. Now, the reason we actually have to keep that pending information and the validity information sort of separate, and why we need to keep both of them, is it's possible that multiple instructions could light up simultaneously as being ready to go. So if you have, let's say, 2 instructions that are both dependent only on register 5, and register 5 is not ready, it's the destination of a multiply. But then register 5 gets written, it's going to actually clear the pending bits. So it's no longer pending. And it might be in multiple places. So it might be like here, and maybe even there. It's going to clear the pending bits in whoever's trying to read register 5. And then because we're only, let's say, going to have single issue on this processor, you can only pull one thing out at a time. So you need to sort of pull one thing out, and you need some way to leave the other instruction in the issue queue, having all of its operands ready. So that's how you do that. OK, so how do we figure out if an instruction is ready? Well, we see if it actually uses it, that the operand uses the particular operand identifier, and we see if it's pending. And then we have to check the other for 2 inputs. We need to check the 2 inputs. And then we also have to make sure there's no structural hazard somewhere else in the pipe, like if we're trying to schedule write ports. And we're going to use the scoreboard to do that. The other thing is if we want high performance, we probably don't want to have to wait for values to get to the end of the pipe. So in reality, this is going to get more complicated because it's going to be these things plus information coming from the scoreboard, which says when a particular register identifier is ready, or when a particular register is ready. Let's talk about the destination here. This just tracks whether an instruction writes a destination or not. And like I said, in these basic pipelines, we're going to leave instructions in the instruction queue until they get to the end of the pipe. And when it gets to the end of the pipe, this is where we go to check to see what other locations we need to sort of clear out. So if there's an instruction, let's say, sitting here, which has the valid bit set, and it's writing to register 5 as the destination, when that instruction commits, we're going to clear it out of the issue queue, and we're going to say, oh, well, it wrote register 5. Let's scan through all these other places and look for places that say register 5. And if they say register 5, we are going to flip the pending bit from pending to not pending anymore. And we're going to remove the instruction from the issue queue. OK, so centralized versus distributed issue queues. In a sort of logical sense, in a perfect world, it's probably nice to have a big centralized issue queue. You can scan over all the instructions. You don't have to sort of look around. But this can sometimes be harder to implement because you have to put all of your instructions in one location. And sometimes they don't necessarily sort of cross-communicate very well. Like floating point units, they have floating point registers versus integer register files or something like that. They don't necessarily need a whole lot of communication. So you could have distributed instruction queues where you sort of steer, let's say, here the execute or ALU and memory ops to one of these for these functional units, and you have a different instruction queue just for multiplies or something like that. I'm going to put a paper on the website for you guys all to read. It's Tomasulo's algorithm. It's a very famous paper. And in that, they talk about distributed instruction queues. Strangely enough, sort of the first place in literature that these instruction queues showed up was around that time or in that paper. And they actually go straight to the distributed version and kind of skip the centralized version, which I always found a little bit odd. But lots of people build centralized ones today. one of the reasons that I think the Tomasulo algorithm people went for this distributed one first is because they were actually implementing on multiple discrete chips. So they had an issue queue per chip. So they had like a floating point chip and an integer chip, and they steered the instructions. And they didn't want to have one data structure that crossed two chips. Today we have lots of integration, so we don't have to worry about that as much. OK, so I just wanted to briefly say this was the question that came up last time, and scoreboards. If you have to worry about write after write hazards in the pipe, the things we are talking about today, we didn't have to really worry about that. But the stuff we talk about next time, we're going to have to think about better scoreboards. It looks the same as the previous scoreboard, but you might need to keep the functional unit, or you need to keep the functional unit number, or some bits that represent the functional unit, and then those march down the pipe versus ones marching down the pipe. You have, let's say, different numbers like 1, 2, 3, or you have other things marching down the pipe. But that's only if you have to track write after write hazards. OK, so that was just a quick aside. Let's look at this in order fetch, out of order issue, out of order write back, and out of order commit processor in a pipeline diagram. And I'm going to show a new little thing in our pipeline diagram here. We have a lowercase I, which means the instruction enters the issue queue. And then when it exits the issue queue, it just starts going down into the issue stage of the pipe. And I'm trying to think, what do I want to show? This is not that complicated of a drawing. Here I'm actually showing the issue queue, what is in the issue queue. So I have 3 issue queue slots, because this is a relatively simplistic pipe. This first instruction, which goes to execute, register 2 and register 3 are just already ready, so we don't have to worry about it. But an example of something that's more interesting, let's say, is I don't know, where's a good one? Here we go. This will enter the issue queue, but register 12 does not become ready until late. So once that comes ready, we can basically start pulling things out of the issue queue and issue that instruction. So that shows up. Let's see if we can show that here. Register, what is this, 14, 12. OK, so this one here, we're waiting for that to happen. Let's see. Yeah, we're waiting for, no, where is it? 12. This add. This pipeline diagram looks wrong. Yes, that actually is what I wanted to show here. This is interesting. The value actually becomes ready early. But is that what's actually happening here? The value becomes ready at the end of this execute stage, but it can't go to issue at that cycle because there's something else issuing, so it has to be pushed out. So we're only doing a single issue per cycle. If we had multiple issues, you could think of something more interesting happening here. Yeah, so this is a really complicated case, because if we pull this back, let's say to here, we get a write back hazard. The W would conflict with the other W. If we try to issue here, sorry, that was if we issued here. If we try to issue here, we get a structural hazard on the issue, so it actually gets pushed way out there. So that's kind of a bummer. So sometimes you just lose. OK, so here's an interesting case. So let's assume that all the instructions are preloaded into the issue queue. So showing this, we have fetch, decode, issue, issue, issue. And basically, these things are just sort of sitting in the issue queue. And then we start looking. What happens? Does the performance get better than the previous example? So interestingly enough, even if you sort of issue everything into the pipe early and then just sort of fill up your issue queue, pulling out of the issue queue can still be a limiter, and the number of ALUs can still be a limiter. So there's other structural hazards. The performance of this code and this pipeline does not actually get any better, which is sort of interesting. You'd think, oh, well, I don't have to wait for things to sort of drivel into my instruction queue. I just sort of preload my instruction queue. But the performance really doesn't end up being better. So this motivates us going to both out of order mixed with duplication of structures. Like maybe we can issue 2 instructions at the same time, and maybe we can have 2 ALUs. So this is, motivates us having a superscalar. In order issue, out of order, excuse me, in order front end, out of order issue, out of order write back, and in order commit. So the middle portion of the pipe here is all out of order. And then finally, we commit in order, and we fetch in order. So this has all of those structures that we had before. It's sort of the union of everything. We have a issue queue. We have a future store buffer. We reorder buffer, physical register file, scoreboard, and architectural register file. This requires us to have everything. And we can start thinking about what this does to performance. So I'm going to push through here because I only have 2 more slides, and the state would get lost otherwise. OK, so let's see some interesting things happening here. So we have out of order issue. So we can see this add here issuing before this other, before this multiply. That's pretty cool. Ignore this bottom for a second here. We have that same problem sort of showing up here. We have this write happening. But even in an out-of-order issue processor, this should be able to get pulled back, as I said before. But it doesn't, because at this point, you'd have a write hazard. You'd have a hazard on the write back of the register file. Something similar, if you try to issue here, you'd be issuing 2 instructions at the same time. So this starts to be a problem. So it actually ends up getting pulled out. Interestingly enough, the performance of this is not a whole lot better than what we had before. If you sort of like cut it here, we're at 15 cycles. The commit gets pushed out far because you have to commit in order. But this fixes a lot of problems that we had in the in order fetch, out of order, out of order, out of order, because we can have precise exceptions at the end of a pipe. We can have out of order issue, out of order execute. We still do in order fetch because that's kind of the semantics of programs. So let's take a look at, let's say we had the ability to do double issue, but not double execute. How does this change? It changes this to this diagram. And as you can see here, we actually have I here and I here in the same time period. So we've pulled that back one. And you would think that would actually help. But so we don't have a write conflict. Everything's still sort of OK here. But the commit still happens at the same time. So that's not always as good as you think. In reality, what you want to start thinking about is having out of order and with. So here we have a out of order 2-wide superscalar, what we showed before, in order fetch, out of order issue, out of order write back, and in order commit. And what we can see is we actually are fetching 2 instructions at a time, decoding 2 instructions at a time, issuing 2 instructions at a time. And this can actually help a little bit, but you still have problems. So here we're just going to have, we'll be able to issue two, but we're not going to have two ALUs. We're going to have the same sort of back end of the pipe. And what we start to get limited by is we end up with sort of execution resource bottlenecks here. So next time we're going to start talking about how to sort of add multiple ALUs, and you can sort of pull this earlier, and maybe even have two multiplies or something like that, and try to remove some of those complexities. But what's nice about this is if you have double issue, out of order, write back, these add instructions that are not dependent on these malls at all can just happen. And that's really nice. OK, we're going to stop here for today. OK, let's get started. So today we're going to be continuing our venture into out-of-order processors and superscalars. And we're going to start talking about how to fix write after write dependencies and write after read dependencies in a processor pipeline. We're also going to talk a little bit about one of the questions we had last time about on a branch, what do you do to the reorder buffer, and how do you clean up the state in the reorder buffer? So let's start off. So a little bit about what we're doing today. We're going to talk about speculation in branches. As I said, we're going to review about that, and then answer the question we had last time about what happens to the reorder buffer when you have a speculative branch and what are good strategies there. Then we're going to talk about registry naming and how to break write after write and write after read dependencies. And then we're going to talk about memory disambiguation if we have time. And memory disambiguation is basically figuring out how to have loads and stores execute out of order relative to each other, and figuring out how to get the right data for a particular load after a store. And we call that memory disambiguation. OK, so let's start off by looking once again at our in-order pipeline, or I4 for short. And let's look at what happens on a branch. So here we have some code. Instruction 3 is a branch. Branch is to target T here. And it's executing along. And because everything is in order, we don't actually have to worry about any form of control hazard really happening here, or any form of really bad hazard happening here if we can just basically reach behind us and kill all of the instructions behind us. None of them will have committed any state at that point. So this is pretty nice. So we did have speculative instructions here, these three adds, and they started doing stuff, but they don't have a chance to get to the write back state of the pipe. So they don't even touch the physical register file. So we don't have to clean up physical register file. We don't have to clean up any of the state here. We do need to reset the scoreboard when we take a branch mispredict here, and the speculative state is wrong. But otherwise, everything is OK. OK, so life gets a little more complicated when we start to look at in-order instruction fetch, in-order instruction issue, out of order execute and write back, and out of order commit. So here's our pipeline diagram. And what's interesting to see here is here we have our branch. Note that the sort of what is happening in the instructions moves around a little bit. But besides that, nothing much else is really changing here. We're still able to catch our speculative instructions before they write back. And what's key here is that we're doing in-order issue. And it's because we do the in-order issue that the subsequent speculative instructions, while they are speculative, they're not going to run ahead and write back early, if you will. And what that would basically mean is you'd have for this add instruction, there's no W sitting here before this branch hits the branch resolution spot in the pipe. And let's say we resolve our branches in X0. And then, so this branch here can just redirect the front of the pipe. It can squash all the subsequent instructions and reset the scoreboard. So life is relatively easy. In order issue, or excuse me, in order fetch, in order issue, out of order write back, in order commit. Gets a little bit more complicated here. But what's nice here is we can prevent instructions from writing the physical register file for the same reason as the other pipe, because we did in order issue. These subsequent speculative instructions cannot go execute any earlier, and we know that it's pretty quick to go actually issue the, or it's pretty quickly after we issue the branch instruction that we can resolve the target. So there's maybe a little bit of a shadow there, but if it's one cycle, nothing is going to be able to get to the write back stage of the pipe. Now, we do need to clean up the reorder buffer because this pipe starts to have a reorder buffer, so it's not just a scoreboard that we need to clean up, but we need to actually clean up the reorder buffer here. And we have an option. We can either remove from the reorder buffer immediately, or we can wait until these other instructions sort of get to the commit stage to remove from the reorder buffer. And this is the question we had last time, and I'll address that in 2 more slides in a little more detail. OK, so now we start to get to out-of-order issue processors. So here we have in-order fetch, out-of-order issue, out-of-order write back, and out-of-order commit processor. And if you recall, this is the processor that we looked at last time, which we said could not have precise interrupts, because you can have things basically write early. Well, for that same reason, you can have instructions that write the register file, or write the physical register file early in a pipeline like this. Or actually, in this pipe, there's both architectural register file and the physical register file. It's all together. But if you take a look here, let's look at this add. This add writes the register file before the branch, which is dependent on the multiply, has been resolved. Uh-oh. Well, we just wrote the architectural register file. We wrote non-rollbackable state, if you will, or a state that is not able to be rolled back. And we actually committed the wrong state. And this speculative instruction was not supposed to have executed in correct program order. So this is the same problem that we see with imprecise exceptions showing up here. So one thing you could do is you could have a pipeline like this, and you can try to fix this by not having any form of control speculation. You can basically stall all these subsequent instructions here, these 3 adds, and actually potentially all the rest of these question mark instructions here until the branch has been resolved. But that's going to limit your performance. So there's a problem with this form of pipeline with out-of-order commit here, is that you have no way to sort of roll back any state. OK, so this takes us to the our pinnacle pipeline that we had last time. In order issue, or excuse me, in order fetch, out of order issue, out of order execute and write back, and in order commit. And let's take a look at this. And there's sort of 2 competing questions here that we have to think about. First thing is we see that this actually does a write right here before the branch is known. But conveniently, it's writing a different data structure. It's not writing our architectural state. It's writing our physical register file. And just like on a interrupt of some form, we can roll back the architectural register file into the physical register file. We can do that for a branch here also. So one of the interesting questions that comes up is, where do we resolve the branch? And when do we try to kill subsequent instructions? Do we try to do that right when the branch gets resolved? Oops. Or do we wait till the branch commits? OK, so this actually goes back to the question we had last time of how easy is it to go clean up the reorder buffer, and how easy is it to go clean up the physical register file. So let's take a look at this example here. Now, having said that, this is all doable. People have built pipelines where they actually do go clean up sort of all these in-flight instructions. But let's look at the complexity of that. So here we have, right when we know the branch gets resolved, we actually kill all of these instructions, and we redirect the front of the pipe to go fetch our target, our true target. Well, let's go look what's happening in the physical register file for this case. So in this case, for the physical register file, this mul has written the physical register file. That's a good value. We want to keep that mul. This add here has also written the physical register file. We don't want to keep that. Ugh. Life starts to get a lot more complicated here. In a pipeline like this, what we're really going to have to do is we're going to have to clean up speculative state in the physical register file, and we're going to have to do selective rollback. So instead of just taking the entire architectural register file and overwriting the physical register file on rollback, we're going to have to figure out which of these things were speculative and which of these things were not speculative. That's doable. But you probably need some extra structures to go do that over and above what we've already talked about in class. Or rather, you're going to have to track which physical registers need to be rolled back on a speculation mispredict. Something a little bit easier is just to wait to the commit stage. So if we wait to the commit stage, we can see here as we commit, well, we know that all of the previous instructions of this branch have committed now to the architectural register file. So we know the architectural register file is up to date relative to the branch. So we can, and these other speculative instructions may or may not have written the physical register file. The physical register file is just completely out of date at this point. So what's nice here is we can copy the entire architectural register file to the physical register file and effectively roll back everything. OK, so this brings us to the question that we had during last class about the reorder buffer and what do you do with reorder buffer pointers in this branch misspeculation case. So the question really here is, well, do we have to wait for these instructions here to get to the end of the pipe, these speculative instructions to get all the way to the end of the pipe to go clean up the reorder buffer, or can we just adjust a pointer of the next instruction in the reorder buffer? And the answer, so I spent a bunch of time thinking about this, is we should just be able to adjust the pointer in the reorder buffer to say where the next location is and just fill that in with this target instruction here. And that will effectively clean out all of this state here. But where this gets tricky, that works great in this case. But as I said, if you go look at this other case here where you actually you're trying to preemptively sort of kill things, this is not going to work in this case. Because what's really going to happen is we have selective rollback we're going to have to perform here. And just changing the pointer in the reorder buffer is not enough to go do that. We're going to have to sort of individually clean up entries if we want to go do that. And that gets a lot more complicated. One other thing which we haven't talked about yet, and one motivation for why you may want to wait to actually clean up the reorder buffer until you want to wait till the speculative instructions reach the end of the commit stage of the pipe, if you will, to clean up the reorder buffer, is there's other structures, if you have a register renamer, which you're going to want to clean up in that same manner. So we're going to be talking about register renaming in this lecture. And what happens is if you sort of think about these in-flight speculative instructions, if you have more physical registers than architectural registers, it's possible that if you have to abort these instructions, these speculative instructions, you have other structures like a free list of physical registers, which you have to deallocate somehow. And you can sort of do like a bulk deallocate, but it's a convenient place to sort of deallocate when it tries to commit. So let's look at that in a minute. But that's basically what I want to get across is, yes, you can just adjust the pointer for the simple case. Trying to do something more aggressive gets quite a bit harder because you have to speculatively roll back the physical register file in addition to the reorder buffer. Well, the reorder buffer, you can just adjust the pointer, but the physical register file you can't just do that with. And if you wait to the end of the pipe, you can get you can deallocate physical registers a little bit easier. OK, so that brings up the question of register renaming. What is register renaming? Hopefully some of you skimmed the Tomasulo algorithm paper that I assigned, because we're going to be discussing that and the motivation for that work. OK, so what is limiting our performance in these pipelines, these out-of-order pipelines that we've discussed so far? OK, a couple things. Write after write and write after read dependencies. Let's talk about these. In write after write dependence, you're going to write to one register, then you're going to write to the register again. And in our pipelines that we've talked about so far, you're basically going to stall the pipe while you're waiting for the first write to commit, because we're not able to handle multiple writes in the pipeline at the same time. But these are not fundamental dependencies. So computer architects put on our thinking cap, and we came up with ways to break these dependencies. A read after write, and that also is true for a write after a read. So if you do write to, let's say, register 4 after a read from register 4, well, there should be nothing wrong with that. But if you're trying to execute the instructions out of order, you need to think about that. A read after write is a true dependence because you actually need the data. You need the value to go execute the subsequent instruction. And we're going to call write after write and write after read dependencies name dependencies. And we're going to call a read after write a true dependence that we can't break. OK, so let's look at some example code here and see what can go wrong if you just ignore all the name dependencies. Like I said, they're not true dependencies, so maybe we just don't need them. OK, so we have a different code sequence here. We have a mul, and then 2 add immediates. Let's identify some important things in here. First, let's identify the true read after write dependencies. So I put some circles and some arrows here. So let's take a look here. This writes register 1, and the second mul reads the result of that. OK. Let's see here. This add reads register 4, and the previous instruction writes register 4. So that's a true dependence. We can't break those. We may talk at the end of the term maybe about some ways to break those, but they get pretty crazy. So let's look at the write after write dependence. So the first write after write dependence is here. We're writing register 4, and then we write register 4 again. But in an out-of-order processor, if we try to break all these dependencies, we can see that we're actually writing to register 4 here, and then we write register 4 here. And that's like out of order. Whoa, what just happened here? Well, we said we just broke the dependency. We're not going to stall the front of the pipe on this. So if you go to execute this on one of our out-of-order issue pipes that we've looked at so far, let's say this is executing on the in-order fetch, out-of-order issue, out-of-order execute, and write back in in-order commit pipe, we can see that we will write to register 4 in time before we wrote to register 4 here. Now that's going to cause some major problems. We just wrote the wrong value. Oops. And the other one here is a write after read dependence. So here we have a read of register 4. And here we have a write of register 4. And because this add got pulled so early in the execution order, we actually wrote before this instruction had a chance to read the value. And the reason this instruction got delayed was because it was also dependent on a true dependency here. But it's dependent on two things. But all of a sudden, we wrote register 4 with the value from this add, and then we went and read it, and we read the wrong value. So we can't just go change and break write after write dependencies and write after read dependencies very easily. We need to think a little bit harder about this. One last interesting thing that happens here, this is kind of fun. We do commit in order in this pipe. But look what happens to register 4. We wrote register 4 here, and then we write register 4 again. And then we commit from physical register 4 to architectural register 4. So we just committed the wrong state also to the architectural register file. So we're having lots of problems here. It's not just basic things. So what's the solution to this? Well, the solution is we can start thinking about how to add more registers. So at the top here is the same example I had in the previous slide. So nothing new there. But I wanted to compare this to, let's say, our conservatively stalling pipeline from a performance perspective first. So here we have our in order fetch, out of order issue, out of order write back, and in order commit pipes. This is our most advanced one from last time. But it conservatively stalls on write after write and write after read dependencies. And that's drawn here with these arrows. So we can't even issue this instruction until we know that, let's say, these two instructions here, which have something to do with register 4, commit. And then we can go to issue this. Now, this might be a little bit conservative. This might be even a little bit over-conservative. It might be possible to pull this back 1 or 2 cycles, maybe to sort of the point where this instruction does the write back. But one of the challenges there is you can't necessarily track that very easily inside of your reorder buffer unless you have something there that scans for this exact case. And it's not going to save you that much performance either. What I'm trying to get across here, though, is that the performance of this instruction sequence is actually worse. It takes longer than our incorrect, but we'll call ideal case here on the top. So let's do one little change to the instruction sequence, highlighted in red here, and see what happens to our execution. So we took this add, which wrote to register 4, and changed it. We added another register usage here, and now we write to register 8. And lo and behold, it breaks all the write after write dependencies, and it breaks all the write after read dependencies. And all of a sudden, we get to our idealized performance. This is the exact same case as that. But we require another register. Well, can we just add infinite numbers of registers? So what's a con of adding infinite numbers of registers? Anyone have any ideas? So if we're trying to use more registers here, we might use up all of our architectural registers. Can we just add more architectural registers to our instruction set? Yeah, so it takes up space. So if we look at our registers, we could have a larger namespace for our registers. But if we have 32 registers, that takes 5 bits. If we have 128 registers, that's going to take 7 bits. If we have infinite, that will take infinite number of bits. But what we're going to talk about in today's lecture is how to do this in hardware such that you have some more registers in your physical register space, but not more registers in your architectural register space. And this is, I should point out, this is not only a register problem. This could also happen with memory. If you name your memory inappropriately, if you have very small amounts of memory and you try to reuse the memory very aggressively, you can get naming problems in that also. But for today, we're going to mostly be focusing on register renaming. And so I'll define register renaming as we're going to change the naming of the registers in hardware to eliminate these write after write name dependencies and the write after read dependencies. OK, so we're going to be talking about 2 major schemes. And they are mirrors of each other and have slightly different hardware requirements. But they're mostly, when you think of them, they're just sort of logically duals of each other, and there's different ways to think of the same problem. So the first scheme we're going to be looking at is we're going to add pointers in our instruction queue and our reorder buffer to allow us to have different register names in them and not actually just have architectural register names in those data structures. The other option, which is if anyone read the Tomasulo algorithm paper, is to actually store the actual value, the data value, in these data structures, in the reorder buffer and in the instruction queue. And they look very similar if you sort of think about it, and they're going to have the same performance. I'll give you the sort of end of the novel at the beginning here. They're going to have the same performance. They're doing the same thing, but they're slightly different in the mechanics perspective. And we're going to start off by looking at this first one here. We're going to have pointers in the instruction queue in the reorder buffer, mainly because we already have pointers in our design that we looked at last time. This in order issue, out of order, or excuse me, in order fetch, out of order issue, out of order execute and write back, and in order commit design. OK, so let's take a look at what we have to add to our pipeline. So we have our in order fetch, out of order issue, out of order write back, and in order commit processor that we had before. Note it had variable length pipes, it had a reorder buffer, it had a future store buffer, it had a scoreboard, it had an instruction queue. So it had all the structures we talked about last time. And now we're going to add two more structures to it. And we're going to modify the structures that are there slightly. But let's talk about what this is going to do. So the first structure we're going to add is a free list. And the free list is going to keep track of physical registers that we can go use. So the physical registers will probably have more physical registers than we have architectural registers. But you need to keep track of which ones are free to be used, because we're going to basically be allocating and deallocating from the number of physical registers quickly as we execute. The other structure here we call the rename table. Sometimes this is called the RAT, which is the sort of the Intel nomenclature for this. Or actually, the RAT is either this table or the table that we're discussing in the Tomasulo algorithm variant of this, but they're very similar. And what this table does is it's going to map from architectural register to the most up-to-date version in our physical register file. So it's going to say, we have an instruction that's sitting here at our decode stage. Where do we go find the value? Because this gets complicated. We just renamed everything. We have different names for everything. It's in some physical registers. We need to go figure out where that value is. And that's what this table does. We're also going to add two fields to the reorder buffer. I'll talk about that in a second. And we're going to want to increase the size of the physical register file so that we can get more performance. If we have the same number of physical registers as we have architectural registers, and we need to have at least one physical register for each architectural register, we're not going to get any more performance from having a register renaming step to our pipe. OK, so this is kind of for completeness, where everything gets written in the pipe in time. Two things I want to point out here. The free list gets updated at the front and also gets updated here at the end. And the condition that you need to deallocate a physical register gets a little complicated. But we'll talk about that. And the rename table gets read up here, because that tells you where to actually go get the value. It also gets updated here when we actually emit an instruction down the pipe. And we also want to update some pending bits when we get to the end of the pipe, so that it knows whether to go sort of pick up from the physical register file or the architectural register file for rollback issues. OK, so let's jump into these data structures and see what we add. OK, as I said, we're going to add stuff to the reorder buffer here. Now, our previous reorder buffer looked very similar to this. We had some state, whether things are pending, free, or finished, where we said dash dash represents free, and F means finished. It means the instruction got to the end of the pipe and is waiting to commit. We had a bit that says whether it was after a branch. You might have multiple of these bits if you allow multiple branches in flight. A bit that says it's a store or not. A bit that says whether it writes a register. So this says whether the destination is valid. And that's important for us to know, because when we get to the end of the pipe, we need to know whether to actually commit some state into the architectural register file. And we have a field here, which we had before, which was the physical register file specifier. So this tells us where to go read from. That's all good. But now we add some extra bits here. The first one is a architectural register file specifier. OK, so this gets a little complicated. What are we thinking about here? Why do we need this? Well, when we get to the end of the pipe, and we're going to do commit, if we go back and look at this picture here, in the commit stage, we take something from the physical register file, put it into, and the reorder buffer drives this. It says, OK, copy that into the architectural register file when the commit occurs. Well, now we've renamed everything. So it's not an identity map from physical register number to architectural register number. So we need to know where to actually go write in the architectural register file. And that's what this does. It just tells us where to go write. So this is where we read from. This is where we write to when this instruction, let's say it's the most recent instruction here, this turns to finished. It's going to go commit. We read the value from here. We write it into the value pointed to by here. And then we have one other field here, which is a little bit odd. We have the previous physical register. Why would we need that? That doesn't make any sense. It was the what is this doing? So this is something we actually read out of the rename table at the front of the pipe. And what it's going to tell us is it's going to tell us, let's say this was register 4. This is where the in-flight physical register is. And this is the previous physical register that held the value of register 4 before we did the update. And the reason we need to know this is when we hit the end of the pipe, we need some way to deallocate physical registers. And we're going to use this to track that. And we'll give an example in a minute. But what this is really going to do is it's going to say, oh, we wrote to the new value of register 4, which means that the in-flight value, let's say it was register 4, physical register 27, and the new one is physical register 30 or something like that. We need to deallocate physical register 27. And we can do that when we reach the end of the pipe by committing this instruction out of the reorder buffer and cleaning up all the state. OK, a quick picture here of the rename table, the renaming table. This is indexed by register. P tells us whether we have a write in flight. So it knows that that value is not in the architectural register file. And preg here just tells us where in the physical register file to go find the value. And this is really important when a subsequent instruction that's looking for that value shows up, and it wants to get that value before it hits the architectural register file. It looks here. This tells us. It tells us, oh, it's pending. It's going to be here in a little bit. Together with this and the scoreboard, we might even be able to bypass it early in a good day. In a bad day, we have to wait for it to get to the physical register file, but it's a lot better than having to go pick it out of the architectural register file. And finally, we have a free list. And this is literally just a bit per physical register, which is very different than a bit per architectural register. And it's just going to have, let's say we have big N physical registers, or I don't know, we have 256 physical registers. And we have a bit saying whether that register has been deallocated and it's ready to be used. for future register renaming, or whether there's a instruction using that physical register, or it's waiting to commit to the architectural register file. This will tell us that information in this table here. There's just a bit that says whether it's free or not. Pretty simple. Actually, before I go on here, I wanted to make an interesting observation. Where does this register renaming become really important? Well, if we go look at something like the original Intel architecture, they had 8 registers. And if you want to run high-performance code, you have to reuse those registers pretty quickly. So they got register limited very quickly when they tried to build faster and faster processors. So they had to introduce register renaming quite early in the Intel microarchitecture implementations. And they had many, many more physical registers than architectural registers very quickly. Because 8 isn't going to get you very far. They can have like about 100 in-flight instructions. And by definition, you can't have that many in-flight instructions if you maintain write after write stalling effectively, because you're going to have to rewrite some register. It's kind of like a pigeonhole problem. If you have more than 8 instructions, at least one of those instructions is going to cause a write after write dependency, and you're going to stall the pipe. So they're not going to be able to have, let's say, more than 8 in-flight instructions pretty quickly if they did not do register renaming. So they did register renaming very quickly in their pipelines. OK, so this gets us to the eye chart here. Let's walk through a basic case of what's in all these different tables as we execute our basic simple code here. On the top, we have the 4 instructions, 2 mols, and some adds. This was our original test case. Note there is all these dependencies through register 4 we need to worry about. There's both read after write, write after read, and write after write dependencies. We're going to execute it quickly here by pulling, as you can see, this add fires early or issues early, the final add. And this is really driven by the register renaming. So let's take a look at what happens here. And let's try to interpret this. Here we have cycles. Cycles are also across the top of the stage. We show what's in the decode, issue, write back, and commit stage of the pipe. We leave out the execute stages because this is too much to draw here. And it's drawn at the top in a different form. Let's first look at the rename table. So we're at the rename table, or we're actually going to say we only have, for clearness here, let's say we only have 7 architectural registers. But we're going to have, let's say, 11 physical registers. So we're going to have more physical registers than architectural registers in this example. We start off and we say, OK, well, register 1, if you want to go find architectural register 1, the value's in physical register 0. And we can basically just, we just come up with some allocation. And the circles mean that it's not pending. It's not in flight in the pipe. That's just sort of the base case. Everything is, the pipe has been relaxed. Everything is allocated. And we just do a basic allocation here at the beginning. Now, as we go to execute, some interesting stuff starts to happen. First thing that's going to happen is we're actually going to here issue this instruction which writes to register 1. We need to rename this at this point. Register 1, we have to rename to something else. So in this table here, if we look, we rename register 1 to physical register 7. OK, that sounds good. What happens next? Well, we next sit here and we try to execute this instruction here. It's this mol, and it goes and tries to read register 1. When it goes to read register 1, though, we can go look at the rename table and say, oh, well, that's actually in flight, and it's in physical register 7. So if we go look over here, we can draw this and say, oh, that value is actually in physical register 7, and it's currently not ready, maybe. But P4, the other input, register 5, OK, yeah, register 5 got renamed to P4, is ready. So it's ready to go. Okay, let's. One other interesting thing that happens here is we can see that as we go to allocate this, we have to remove it from the free list. So this list here is just a list of all the free registers. We start off with 4 free registers, and we sort of narrow it down as we start to do writes. And at some point, we run out. So I wanted to make an important note about this, is that when we run out of physical registers, we're going to have to stall the pipe, because we can't do any more renaming. We can't issue more instructions at that point. So that's really important to realize, is that when you build your machines, you have to have enough physical registers that you don't run out very often. Now, it's possible that you could still run out. So let's say you have hundreds of in-flight instructions, and you only have, let's say, 64 physical registers. You might still run out, but the probability of that happening might be relatively low, and your utilization, and you sort of bake into this your CPI. Your CPI may not be less than 1 or may not be low. So the probability of that actually happening, you may not worry about it too much. Another cute little story here is there's actually been some interesting bugs in processors around the free list. So there were some alpha processors where they actually leaked free list entries in their register file. So what happened was if you ran a certain piece of code for a long enough period of time, all of a sudden this processor just ground to a halt because it was not able to allocate more physical registers, and it ran out. It ends up with fewer physical registers than architectural registers, and the machine just stopped. And this was a sort of well-known bug in some of the early alpha. I think this was actually in the first out of, let me think, where was this? I think this was in the 21264 had this problem. They fixed it, and they pulled those chips off the shelf. And that's a really bad thing to have happen in your processor. Kind of embarrassing. But as I said, if you run out, you're not going to be able to issue more. But in this case, we made sure we had enough. So we're not actually going to see any stalls. And let's look at how things get on the free list here, because that's a little bit interesting. In our reorder buffer, I said we had extra fields. If you recall, we had the previous physical register that this was allocated into. So if we go look at this instruction, which is the first instruction we go to execute, that mul, R1 was in P0. So when that instruction commits, we actually put P0 onto the free list. And we're going to look at a case in a second why you can't do it earlier. Because it seems like you should be able to basically deallocate physical registers earlier. No one's probably going to be reading that value. Why can't you just get rid of it early? But we'll look at in a second a test case that's a problem with. Let's see, any other fun insights here? That's about it, what I wanted to get across from this diagram. As the code continues on, we end up with more and more free physical registers. One thing I did want to, just to walk through this to understand this a little bit, let's say we have this instruction here, which is our, let's see, 1, 2, 3, 4. It's our last instruction that we execute. Let's go see what it's doing here. So it writes architectural register 4. So we have to store that in the reorder buffer because we need to know where to go to do the write. We had allocated P10 to that. And we did that right here when we actually issued it. So we pulled it off the free list. And the previous thing that it wrote was P8. So when that ultimately commits, P8 is going to end up back in our free list. So that's a nice little thing. The circles just show when the values are no longer pending. So they actually are not in the pipes anymore. And you can see that continuing here. This instruction here, which is the second multiply, when it commits, it's going to free up P3. So P3 ends up on the list. P5 ends up on the list. P8 ends up on the list. And then when we see true read after writes, for example, right here, we need to make sure to pick up that correct value. And we do that by looking up in the rename table. So let's go find that in this chart here. So instruction 2 is, let's see what it's doing here. So that's going to be right here. It's waiting on P8 to become ready in order to issue. So it's sitting in our instruction queue, and it's just going to stall. It's going to stall all the way out to here. Or it's going to stall to right there. And that's when it comes out of the instruction. OK, so let's look at freeing up physical registers and what is a good policy for freeing up physical registers. So we're going to have a different piece of code here we're going to look at. It's going to be just a bunch of adds. And we're going to look at this code has some read after write dependencies in it, namely R1 there. And let's say we try to go execute this. Well, we're going to, here's some execution order. And we're going to look at, or sorry, that one there is what I meant to go point at for the read after write. We have a write after read dependency here. So let's look at some execution order and see what happens. Let's say we allocate physical register 0 at the beginning somewhere for register 1. And then when we do the commit, we free it up in our free list. Well, lo and behold, another instruction in time comes along here and allocates into physical register 0. And it goes and writes to it, and we free it up there. This instruction here, which we had renamed, we had renamed R1 for, and we go to try to read this value, goes to do the read, and it looks in physical register 0. And it gets the wrong value. Ooh. Yeah, we don't want that. So what's a good policy here? Let's say instead we don't free up a physical register until someone else goes to write that physical register, or a subsequent instruction goes to write that physical register. Because then we know that that physical register is in use or could be in use by other readers of that value. So if we look at this case here, let's say we write physical register 0, and then we allocate a different physical register. We allocate physical register 2 for this right here to register 8. And then we deallocate when we go to overwrite register 1. So by doing that, we know when this R1 gets written that no one else can possibly use that physical register that is after this instruction in program order, because we overwrote it. So that value is no longer visible. So that's pretty nice. So that's the a very good heuristic or a very good way to get this correct is you can just keep the physical register live until you rewrite the physical, or you rewrite the architectural register that physical register maps to, and then at that point you can remove it from the number of allocated physical registers and put it on the free list. If you do it early with an out-of-order execution pipeline, bad things can happen. You can go read the wrong values. OK, so this brings us to a couple optimizations on register renaming. Biggest one here is you can try to combine the architectural register file and the physical register file to save space. And the insight here is if you go to try to combine these two things, you can store the architectural register value and the physical register value in the same physical storage location if that physical register is no longer pending. So if there's nothing in flight to it, and you don't have to roll back, and if you're just going to roll back to the same value anyway, why keep extra space for this? One change you need to do here is, so you're going to remove the architectural register file, but you still basically need to know when you go to do a rollback of some speculative, say you take an interrupt or you take a branch mispredict, you still need to know where to go roll back out of. And we're going to do that by, let's say, having a second renaming table here, which allows us to keep track of just the architectural state. So we have a speculative renaming table, then we have an architectural renaming table. It just has pointers in it instead of actually the values at the end of the pipe. And what's also nice here is instead of copying values, we don't actually have to move something out of the physical register file into the architectural register file. Instead, we just have to update a pointer in a table now. And we did the copy. Could potentially also make rollback easier, because we just have to update some pointers now instead of actually copying an entire register file, which can take a while or requires lots of ports or something else. So you can have a little table there to just do this remapping for you. And as I say, you can typically get away with less space than having, for the same performance than if you were to have two separate structures. One of the downsides is you might need to have more, depending on how you implement this, your architectural register file and your physical register file are now together. It may be bigger, so your register file access might be a little bit slower. Something like that could be a downside versus having it in two separate partition structures. Let's move on to our second scheme. So our second scheme, if we go back to the earlier slide, we said that we can either store pointers in the instruction queue and have pointers in the reorder buffer, or we can just store the values. And if you go read the original reservation station paper by Tomasulo, he actually stores the values in the reservation station, or we're calling instruction queue, and the reorder buffer. OK, so a couple things change when you do this. One structure is missing. First of all, there is no physical register file. We removed that. We're going to store in-flight instructions in a merged reorder buffer physical register file effectively. Second thing that's changed here is we no longer have a free list. And we'll see in a minute why we don't need the free list. But instead, we're basically just going to use different reorder buffer entries to keep track of our free list. And we're going to have to modify a bunch of stuff here. We're going to actually keep values in our reorder buffer instead of a pointer. Our renaming table is going to be modified. Our instruction queue is now going to be able to keep track of actual data values. And our physical register file, as I said before, has gotten merged into our reorder buffer. For completeness here, let's take a look at the where things get read and written in the pipeline. And one notable change I wanted to say here is the architectural register file, which in previous architectures was only written. We didn't do reading of it except on rollback. We now actually read from it because we might need to go find some canonical state there in this architecture. So we add an R there to denote that. OK, so let's look at how we have to modify the reorder buffer. Still looks like our reorder buffer from before. We need to know, for the same reason in the pointer-based design, we still need to know the architectural register number for the particular instruction. So this is when we go to write to the architectural register file, where do we write to it? Because we did renaming, so we have more physical registers. We can't just have an identity map there anymore. And now, we got rid of a lot of that other complexity we had, but we added a bunch more bits to go do this. We now actually can store values in our reorder buffer. So what this is instead of values waiting in the physical register file to be committed, they're just going to stick around in the reorder buffer entry, which is interesting. And so it's going to stick around in here while it's waiting, while it's pending, and then it's actually going to write to the architectural register file when it gets committed. Okay, so we also modify the instruction queue. So this is going to tell us where to go get the values when we're going to go execute. It's also going to store the values now. So what's interesting about this is if you go back and look at the Tomasulo algorithm paper, they broadcast commits that are happening. And those commits end up in the reservation station of the actual value. So we're actually going to store in these two source operands here the values if we get a instruction which commits. If the instruction is pending, if it's in flight, we can't go and just get the value because the value doesn't exist. It's being calculated. And we have this dependent instruction sitting here waiting for something. So instead, if it's pending, our source field, we're not going to store the value in here, but we're going to store a identifier into the reorder buffer. And that what it's going to do is it's going to name the exact instruction that has to complete in order for this value to be ready to execute. So if you think about this from sort of the Tomasulo's algorithm perspective, there's these sort of broadcasts coming back. And what this is going to allow us to do is say, oh, there's a broadcast reorder buffer entry 7 just committed. Or actually, we probably don't even need that. We probably just need it to get stopping pending. We just need to get it to be finished, because then it'll be deposited in the reorder buffer. We can go pick that value out at that point and store it here. And then we can basically have the other instructions that are renaming and executing, which go and blow away that value. But because we stored the value here, we have the most up-to-date value for that register. And we know it's no longer pending, and it's valid, and it's ready to go, at least this one. And we might have to wait for both of these to get ready in order for an instruction to leave the instruction queue. OK, so the rename table also changes a little bit. Not as much as the other one, the other structures. It's still indexed by the register. We're looking for register 2, we'll say. It'll tell us where to go look for that. There's a couple different places where it's going to tell us to go look for it. It's going to tell us either it's in flight, and it's going to put the identifier into the reorder buffer. So it's going to say when that value gets into the reorder buffer and the instruction transitions to finish, but maybe not yet committed, it's going to tell us where to go get it. And that's important for subsequent instructions. They're going to read the rename table to go find the value. Or it's possible that the most up-to-date value is actually in the architectural register file, and we need to go look there. So let's say the reorder buffer, you haven't written, let's say, to register 2 in a very long time. And lots of other instructions execute. And the reorder buffer gets filled up with other things for other instructions for different destination registers. It's very possible that the canonical place to go look for the value is in the architectural register file. And we need to track that. So we sort of have 2 bits here that sort of just say where to go look for it. Either it's in the architectural register file, or whether it's in flight. And then if it's in flight, we have to go look down here. And if it's in flight, that means that and if p is, let's say, 1, it's actually in flight. And if it's 0, well, it's sitting in the reorder buffer waiting to retire. This is just going to tell us where to go find the actual value for subsequent instructions that want to go read the rename table to go find the value. OK, well, we'll move on. And we'll look at the eye chart here again. And what's interesting about this is we no longer have a free list. We got rid of that structure, so we don't have to worry. our renaming table, instead of having actual physical registers, it's going to have reorder buffer entries. We'll call that a physical register. We've basically merged our physical registers and our reorder buffer together. And similar sorts of analogs happen to when something becomes free, but it looks a little bit different. So when something becomes free, we're going to actually change the valid bit in the rename table to a 0. And that's effectively the same thing as becoming free. And there's analogs there between these two designs. They're almost exactly the same from that perspective, from a logical perspective. But when you become free, you basically can remove it from the table. So how do we do the mapping from the architectural register to physical register? Yeah, it could be random. In this design, it's a little bit different because you're basically going to be pulling out of the reorder buffer in order to some extent. You're going to, your physical register number is going to be your reorder buffer entry slot number. And because we want to retire in order, we're basically going to allocate from that in order. So it's not really random. It's just sort of the next reorder buffer entry. Let's see. What other points I want to make here? Actually, OK, I want to make a point. It's around, OK, so I think what I said was a little bit confusing. So I want to clarify this. When do you deallocate a reorder buffer entry? Because it's a little bit different than deallocating a physical register entry. You apply the same algorithm we applied before. When you go to actually commit the instruction to the architectural register file, that's when it's becoming free. It's basically stopping being used here. That's a little bit different than the, there's analogs to before, but we're effectively moving it out of the reorder buffer into the architectural register file. And at that point, it becomes free. So I want to actually strike what I had just said before about it's exactly the same. It's different, but subtly, that when you go to actually commit the instruction, you're moving it to the architectural register file, and you effectively deallocated that reorder buffer entry, and you've updated the rename table. So that's subtle. That's actually subtle there. So we're actually, when it commits, it stops being used, which is different than a later instruction actually writing that. So that is quite a bit different. Sorry about that. Let's move on to memory disambiguation. So this is kind of the analog of read after write hazards through the memory system. Whoops. OK, we have a basic instruction sequence here. We have a store followed by a load. When can we execute the load? Well, that's a tough one. If the load's not dependent on the store, we can just go execute it out of order. We can potentially even execute the load before the store in an out-of-order machine. If the load's dependent on the store, so if, let's say, register 2 is equal to register 4, then we're going to have a problem. So how do we go about trying to solve this? Up until this point, in our pipes, we've said, OK, loads and stores are in order, because that can solve these problems. So let's say we just execute all loads and stores in order, and we can still allow other instructions to move around it. So it's out of order relative to other instructions, but we have in order memory instructions. And that's going to guarantee that we're not going to have any problems. But we're leaving performance on the table here. We could go faster. We could actually execute loads and stores out of order if R2 and R4 are different. But we're probably going to need some extra structure to do that. OK, so let's take a look at a conservative out-of-order load example. So our conservative one, let's split the store into two sort of subparts, an address computation and the actual data write. By doing this, we can guarantee that the store, because we did the address computation early, we can know that that subsequent load is not going to alias, or we know that R4 is not going to be equal to R2. And we can go execute the load before the store in this case by splitting the store into two different parts, the actual store portion and the address computation. And we still need to, unfortunately, check every single load against all previous uncommitted stores, and we need some structure to go do that. So that's kind of a problem. That's a bummer. And we're not able to execute any load if we don't know the store address of any of the stores before us, because we're just not going to know whether we can go execute that or not. OK, well, could we do one better? Let's start speculating, because let's guess that these are not equal. Let's execute the load before the store. And then we hold off committing the loads and store instructions, and we do that in order. And if something bad happens, so if the registers do equal each other, we have to replay all of these instructions. And what's annoying is we also have to kill all of the subsequent instructions. So anything that was after that load and store, which could have picked up a value from the load in the store, or well, rather from the load, any dependent instructions of the load, we're going to have to go kill all that. And depending on how precise we want to be, we can either try to kill just everything after it, or we can try to kill just selectively the things which are dependent on it. That gets really hard to track. And we have a pretty high penalty here for inaccurate address speculation. So if we go and we just execute these two instructions, we put them into the pipe, and they were dependent on each other, we have to roll back a lot of state. So one sort of heuristic on this was done in the Alpha 21264, is called memory dependence prediction. So what you do is you're still going to guess that the loads in the stores do not alias. But then later, if you find that the two registers do equal each other, you're going to squash all the instructions. But then you're going to do something special to that load. You're basically going to say, that's a wait for the store. You sort of put a barrier in so that you're not going to get like multiple rollbacks over and over again. So this is kind of a conservative way that when you see that you're rolling back a lot, there's a lot of thrown away work that you're doing there. So instead, you can just say, well, this load, I think, is dependent on that store. You could potentially even remember that across instruction sequences. So if it's always the case, let's say this load is dependent on the store, you could potentially keep it into your instruction cache or something like that. And then, when you go to execute that same load at a different time, it's going to wait for all the stores to complete, and it's going to barrier. This is kind of a prediction. It's just a heuristic. But it's one way you could potentially not cause that load to always replay. And if you have sort of multiple dependent loads, or excuse me, loads dependent on one store, you could potentially cause those loads not to have to replay multiple times. But the big advantage here is when you go to re-execute that load sometime in the future, you're not going to flush the entire pipe. So this is kind of like a branch prediction, if you will. It's like this branch, I've trained the predictor to say that load usually is dependent on a previous store, so just wait for all the other stores to clear out of the pipe. So it's a cute little trick. OK, so we're almost out of time. OK, so speculative loads and stores. We're going to introduce a store buffer to hold the speculative state. So let's take a look very briefly here. I'll flash up what a store buffer looks like. And then we'll think about it for a second here. So here you have your cache, your L1 data cache, we'll say. We're going to send all the addresses that go to the L1 cache also to this other structure here, which is the speculative store buffer. Inside the speculative store buffer, there's going to be bits basically saying whether it's valid or not. And the load is going to check against here. And let's say the data hasn't actually gone into the cache. It can go pick up the new value here. And the S bit is basically just going to tell us whether it's in flight or not. So it's possible that we allocate into here, but the store isn't at the end of the pipe yet, or we're still calculating the data. So we need to know that we're going to get a hit if we get a load out of order, and we need to go check for that. And that's really why we have 2 bits here. And then sometime in the future, we have to eventually move the data into the data cache, because this structure will get full. If we sort of fire enough stores against it, it's going to get full. So it's probably a good idea to go move that data into the data cache at some point. We can do that at our convenience, though. And if the store aborts, this is important here. So if the store, let's say, was speculative itself, and it's on the wrong side of a branch or something like that, we just remove it from this table. One interesting thing here is if the data is in both this buffer and in the cache, which one takes precedence? So the store buffer has the new values. So we have to look there. And then finally, it's possible to get multiple stores in here which have the same tag, the same address. Because let's say you're storing to the same address over and over again. And when you go to read, you need to go read the youngest value out of there, because that's the most up-to-date one. So the lookup through here is a little complicated. You actually need to do it in program order. OK, so we'll stop here for today. So we're going to be continuing today talking about VLIW, or very long instruction word processors. This is an alternative way to exploit parallelism in a processor, but instead of doing scheduling dynamically, as we've been talking about in out-of-order processors and superscalars, we're going to look at ways to do it statically in the compiler, and then architectures which can exploit that. But let's now start talking about very long instruction word processors. So we've been talking about the superscalar processors. These superscalar processors have a fair amount of complexity in them, especially out-of-order processors. But where does this complexity come from? And can we remove all that complexity? So that's what we're going to be talking about today. So here I drew a picture where I have the issue width of a superscalar processor. And we represent that as W. And then we have the lifetime of an instruction. So that sort of gives you a matrix of things in flight in the processor. Now, these may be sitting in your instruction queue. We're not going to count if they actually, let's say, get all the way to the reorder buffer, because by the time they get all the way to the reorder buffer, they probably, depending on how you build your processor, you probably don't need to continually check those against the other instructions that are coming. You've already broadcast that back to either your reservation station or your instruction queue to issue further instructions. But if you think about the complexity here of what you're really doing when you try to go issue an instruction, you're trying to take these in-flight instructions and you have to look up basically against them or in your instruction window all of the instructions when they complete against basically all of the other instructions, all the registers. Now we built some structures that make this so you don't have to do a complete all-to-all check. So example structures that we create to help out with this, first of all, the scoreboard, instead of keeping track of where everything is, sort of our original design where we had portions of, or which register destinations sort of flowing down the pipe, and then we did an all-to-all compare. Instead, we just keep track of the location and latency of the most recent write to a register. And it turns something from a all-to-all compare into an index lookup based on the register. So that's a little bit nicer. But if you think about what's happening in the issue queue, we're still doing a, as an instruction retires, it's going to basically broadcast the registers that get completed against the instruction queue and try to wake up instructions and see which ones are ready to go. And that roughly, as I said, scales like this, because you're going to be retiring multiple instructions per cycle. And let's say you have a bunch of stuff in the instruction queue. You're going to have to check against all of those. And this can get painful. Let's take a look at first sort of the complexity of this for in-order machine. So in-order machine is not so bad. L is kind of the pipeline length. You have your width, but you just basically have to have a scoreboard to figure this out. And as we said, that's an index-based structure. Now, when you start to go out of order, you start to have this sort of complexity of all of the results that come back have to be broadcast against either, if you have a distributed instruction queue, all the reservation stations, or if you have a single instruction queue, you have to check against all of the possible instructions to go issue. And what's interesting is one of the big challenges of building these structures is not actually quite what you'd think. There's an interesting challenge that you have too many things that could wake up in one cycle. So let's say you have a single instruction, or let's say all of the instructions in your instruction queue are waiting on register 5 to become valid. All of a sudden, instruction, some add, let's say, writes register 5 and it enters the reorder buffer, so it gets the end of the pipe. Well, now all of a sudden you have to wake up all these instructions and choose some instructions that are the width of your machine that can go issue. Also, you still need to make sure that you can satisfy all of the different requirements in the machine of functional unit mixes. So if you have, say, two adds, 2 multiplies, and 1 load and store, you can't just go pick randomly from there. You need to pick exactly that mix. So this becomes a big mess of combinational logic. And this is why front ends of processors can actually, and out-of-order processors can start to get longer and longer. You get more and more stages in there to do this. And as we talked about last time, in like the Pentium 4, there's actually multiple stages out in front there to be able to do this. And unfortunately, you even have to pipeline that, which makes this even more challenging. So roughly, if you look at sort of the out-of-order control logic here, it's sort of growing somewhere between the width squared to the width cubed. And this is not very good. Sometimes there are a couple circuit level tricks that can help you. So if you go look at people who actually do full custom logic for designs of processors, they'll make something that they call pickers. And what a picker is it's actually instead of using straight combinational logic to go compute what instruction is ready to go execute, you'll instead have a much more analog circuit in there, where you'll basically have some custom analog circuit there, which is almost like a CAM or a content addressable memory, but it's not quite a CAM. It's more of a circuit which will choose what instruction is ready to go, and it is typically you want to have some heuristic that is the oldest instruction. This is to prevent deadlock, so you don't really want to issue arbitrary instructions. You want to issue the oldest instruction because you want to make forward progress in the machine. So what I'm trying to get at here is this is a lot of hardware complexity. It's growing as the width of the machine, and some things actually make this even worse. So here, I have a little note here that as you increase the width of your machine, let's say you had a 3-wide machine, and all of a sudden you want to go to, let's say, a 4 or 5-wide machine. Typically, you need also a larger instruction queue or instruction window to look across in order to find enough parallelism to keep the machine busy. So as you go wider, you also typically have to make the machine sort of deeper, or at least make your instruction queue deeper, to find enough parallelism to feed your functional units. That's not good. So this causes these sort of blow-up factors here. And you can build these things, but they're hard. So are there alternatives? Yes. But before we move on to those alternatives, let's look at the sort of complexity of this in a real processor. So here we have a die photo or die micrograph of the MIPS R10000 processor. This was used in workstations by SGI for many years. It's a real out-of-order superscalar. And one of the interesting things is if you go look at how much area is dedicated just to control logic, it's pretty substantial. So in this processor here, here's our actual data path. It's relatively modest. Cache, instruction cache, data cache, those are pretty big structures. You can see those. We have some other, let's say the data tags, instruction tags, the TLB, those are biggish sort of things. And then all this stuff here is quite large. Let's look at what's inside of here. We have sort of next instruction sorts of things. We have the free list for the, we had talked about this, right? We talked about the free list for the which register is free, if you will, to reuse in your out-of-order processor. We have a big thing that just does register renamer. We have different queues here. So this is a distributed instruction queue or a distributed reservation station processor. So there's one for just address calculation instructions, integer instructions, and floating point instructions. But what's interesting to see here is the percentage of this die that's actually doing compute. Let's say this integer data path, the floating point data path, the floating point multiplier, is sort of pales in comparison to all the overhead. So this is just sort of to get this idea across. Another problem with out-of-order superscalars or superscalars in general is thinking about how do we express parallelism. And I alluded to this in a previous lecture, but it's worth repeating. So let's take a look at what happens for code, sequential codes on a out-of-order superscalar. We start off here with some piece of C code. We put it into our fancy superscalar compiler. That generates some sort of data flow graph and probably also control flow graph inside the compiler. So sort of instructions, there's dependencies between the different instructions. And the compiler right now is trying to find independent operations because it's going to try to come up with a schedule. Unfortunately, you have to come up with a sequential schedule because the instruction sets on sequential processors require you to come up with some order, even though it's very possible that there is no one perfect order. It's also possible that you're sort of over-constraining the problem here. Why are we coming up with some ordering when we don't need to? But in our sequential ISA, we have to come up with that. We write it out to disk somehow, or save a file with this code. And then we have to go and actually try to execute it. And what's funny that I just get a chuckle out of this, is the compiler knew what the dependencies were. And then we have our superscalar processor here, which goes and takes apart the sequential code and tries to reorder the instructions and tries to find parallelism in the instruction sequence. But the compiler knew that. But we had like a breakdown here in the middle that we just weren't not able to express that between the compiler and the processor. Compiler knew about the parallelism. Compiler knew about all the ordering and the requirements. It had to come up with some sequential code sequence, provides it to the processor. The processor takes that sequential code sequence back apart, does out-of-order scheduling like we did on the exam on the midterm. And it's going to, we build a bunch of hardware here, which has high complexity, as we were talking about in the combinational logic, checking the dependencies. And then it comes up with some schedule. This is done via our reservation stations or our instruction queues. And something's going to fire, and it's going to come up with some schedule. And it's going to execute those instructions by preserving read after write dependencies. And hopefully, if our superscalar processor is fancy, we have some registry name where we can break some of the other dependencies also, the write after write and the write after read dependencies, and come up with some schedule that's high performance. Now, there's no guarantee that this schedule is what the compiler would have done if it was smarter, or if it could somehow express parallelism across this interface. But it does something. And what's funny about this is there's a whole lot of power that's being wasted. It's a whole lot of effort that's being wasted in the processor. There's a lot of effort of the designers of the processor that are effectively designing all these circuits to take apart the sequential code sequence and do something useful with it. So it's a lot of work being done there. Is there a better way? So this is where some people got the idea that maybe there is a better way. And I wanted to point out that this is only the tip of the iceberg of what we'll call better ways of having better instruction sequences or better encoding standards between compilers and the hardware. This is actually an open sort of research topic now. Very long instruction word processors, or VLIW for short, is one take on it. There's been a fair amount of work done after this, which we're not going to be talking about in this class, sort of in the last 5 to 10 years, that has looked at this in a little bit more detail, especially given sort of multi-cores and can you schedule across multiple cores. Or there was a project out of University of Texas in Austin, which tried to schedule across something that sort of looked like cores, but wasn't quite cores. That was sort of, we'll call a super VLIW, but had some dynamic aspects and some static aspects. But for right now, let's talk about very long instruction word processors. OK, where does the name come from? Let's start there. Well, these things were actually originally called long instruction word processors. The name kind of fell out of favor. At one point, people made a differentiation between long instruction word processors and very long instruction word processors. And it was kind of on how many instructions were packed together. The differentiation is largely sort of fallen out of favor now. And people mostly call all of these things VLIWs, or very long instruction words, because it's hard to say what is long, what is very. It's kind of just an extra term. It's kind of like people talking about large-scale integration versus very large-scale integration versus ultra-large-scale integration, or people just sort of keep tacking on extra letters in the front. But let's talk about VLIW instruction sequences and what does one of these things look like? Well, a VLIW instruction will actually have multiple operations within one bundle. So typically, this is either called a bundle or an instruction, with multiple operations inside of it. So in this example here, we have 6 operations that can be executed in this one instruction, or in this one bundle. And typically, there is sort of fixed format. So let's say we have, you can execute 2 integer operations, 2 memory operations, and 2 floating point operations per cycle, and that's what you're allowed to encode. So instead of having on the disk a sequential sequence of instructions, now we still have a sequential sequence of instructions or a sequential sequence of bundles, but each one of those instructions, each one of those bundles will actually encode multiple independent operations. So let's look at sort of an example code sequence of this. So for instance, you could have something that looks like this. Let's say so what's interesting about this is we can see that there's actually 2 operations in this first instruction, in this first bundle. The second one only has 1 operation. And this multiply and this add will actually execute, semantically at least, they can execute in parallel. Now, what's interesting is if you look at this, I purposely wrote this to show what looks to be a read after write or write after read or some sort of dependence between these 2 registers and these 2 instructions here, this mul and this add. But that's not what's actually going on here. In a Verilog instruction word processor, within one instruction, within one bundle, these sorts of dependencies are ignored. So just because this reads R3 and this writes R3, they're not dependent on each other. The subsequent instruction is dependent on R3. Let's say if this was R3, then that would probably read the result there. But within one bundle, it doesn't actually matter. So the semantics of the instruction set are everything within one instruction or everything within one bundle are parallel with each other. And there's not dependency checking. What's nice about this is we just took all that piece of hardware that we built. We took all that instruction checking, all the dependency checking, all the scoreboarding, and we just threw it out the window. We don't need that hardware anymore in this instruction set or in this architecture. So that's pretty cool. So we actually took out a bunch of hardware that we didn't need, and we basically let the compiler do that checking for us. Now there's a question of this mul. If this multiply takes multiple cycles, whether this instruction here picks up the result of R3. Sorry, should be drawn the other way. Or let's say if the add had longer latency, if it doesn't pick that up. And we'll talk about that in a minute. There's sort of 2 different choices there in VLIW designs. Well, let's look at our slide here. Typically, in sort of traditional VLIWs, each operation has a certain amount of latency. So, and it's guaranteed. Unfortunately, because of this, the architecture of the machine is very tied to the compiler. The compiler needs to know how long each operation takes. So that's sort of a downside. And in a typical VLIW, there's no data interlocks. So we don't even have a scoreboard. Now, there are some architectures which do enforce interlocking that are VLIWs. But in sort of the traditional, most basic VLIW, you don't have a scoreboard. You have no interlocking. So if you were to have, let's say, this subtract operation, were to read register 1, which the mall wrote. And the mall, let's say it's a floating point mall, it took four cycles. In the most basic operation, this mall here would actually get the old value of R1. So it would not get this value. Instead, it would get the original value of R1. But we'll talk about that in more detail in a second. There's a sort of a choice there in VLIW designs. But yes, so we reduced our hardware. We don't have a register renamer. We don't have an issue window. We don't have a reorder buffer. We don't have a scoreboard. And we let the compiler do a lot of the work. Downsides to this. We're not able to react to dynamicism very well, or dynamic problems. So cache misses, branch mispredicts, things like that. Because we're not going out of order, because we don't have all that extra hardware in there, we can't go schedule around those problems. So that's a downside to these architectures. Now, people have thought really hard about how to make VLIWs have some of the benefits of superscalars and out-of-orderness and out-of-order superscalars. So at the end of lecture today, and probably in the next lecture, we'll talk about some of the techniques that people have added back into VLIWs that bring us somewhere in between an out-of-order processor and a VLIW processor, and get some of the benefits of both. OK, so two models. This goes back to when you have an instruction which writes to a register, and the latency of that instruction is coded to be longer than 1, which value do you pick up? Do you pick up the old value, or do you pick up the new value if you have an instruction which is effectively in the shadow of the other instruction? So the first VLIW model, and this is a sort of classical naming scheme. I did not come up with this. It's called the equals scheduling model. So the equals scheduling model, you have an instruction, and the latency of the instruction is specified. The compiler knows it. And if you have an instruction which tries to read a value that gets written to before the first instruction actually does the write, it'll get the old value. So let's go through an example over here. So we're going to have our multiply again. OK, so here we have a mul and an add, which are bundled together. So they're going to execute concurrently. We have an and instruction, or and operation in the second instruction, in the second bundle here. I should say that I'm using brackets and semicolons to delineate sub-operations. Or the brackets delineate an entire instruction or entire bundle. The semicolon is just there to delineate between two operations within one instruction. And here we have an and. We have what looks to be a read after write dependence here. Something like that. And let's say our pipeline looks like this. We have x0, which does ALU ops. We have y0, y1, y2, y3. And then we have, let's say, a two-stage memory pipeline. And somewhere over here, we have sort of write back. So this looks similar to sort of pipes we've looked at before. But now comes the question, let's say multiplies go down this 4-stage pipe, very similar to things we've looked at before. Loads and stores go into the memory pipe, and ALU operations go into the X pipe. Should this AND get the result in the multiply if it's scheduled one cycle after it, or should it get the old value of R1, the previous value of R1? So we're going to define in the equals scheduling model that the multiply value for R1 is not ready until the end of Y3. So in the equals model, this AND, the compiler is not trying to express a read after write dependence. This does not actually exist. It gets the old value of R1. And the compiler knew about this, and everyone's OK with this. Now, if this AND was, let's say, 3 more cycles later, it would actually get that value, and there would be a read after write dependence. So in the equals model, we're just saying that the operation takes effect exactly at the specified latency and never earlier. Some positives to this is you get some pretty cool register usage. So if you think about it here, register 1 was live after this multiply. So effectively, this gives us a little bit less register pressure. We can have a little bit more registers in flight without having more physical registers or having more architectural registers at all. We can basically just have more registers because it doesn't go dead when we overwrite it. It goes dead when this multiply takes effect. So as I said, we don't need any register renaming. But the compiler really depends on not having the registers visible early. Unfortunately, this causes some problems, these sorts of architectures. This is actually the sort of first formulation of very long instruction word processors looked like this. There's these equals architectures. The major problem with these actually comes around if you have things that are unpredictable mixed in with this very predictable code sequence. So let's say you take an interrupt. Let's say we just put some unimportant instruction here, some subtract operation. The subtract takes an interrupt. Now, semantically, this multiplication, this add, complete. Because the interrupt doesn't happen until the instruction after it. It doesn't happen until this subtract operation. OK. Now you fall into the interrupt handler for the subtract. What happens when the AND goes to execute? Does it actually pick up the correct value of R1 here? No. It picks up the new value of R1, and it was supposed to pick up the old value of R1. So that's traditionally a problem with EQ or equals scheduling model architectures. People have solved some of these problems. Or sometimes when people build these processors, they don't have interrupts. So some of these VLIW equals processors were not able to handle interrupts at all. So that's something to think about. That's sort of the first case. Now let's look at a little bit more forgiving case. We'll call it the less than or equals model, or LEQ scheduling model. So here, in this model, a value is allowed to become value. A register value becomes valid with the new register value anytime between when it issues and the scheduling latency. So what this means is the compiler still can't schedule an instruction early. So it can't go and try to read the value early, but you're guaranteed not to have a problem when there's an interrupt if, let's say, you come back and you filled in the right value. So the compiler sort of schedules around this and knows not to schedule something too early. So you still don't have to implement interlocks. You still don't need a scoreboard. But you can now have precise interrupts. Some other positive things pop out of this. You end up with binary compatibility preserved when the latencies are reduced. So let's say you make a faster processor where your multiply, instead of taking 4 cycles, only takes 3. That's a positive here. You may not get more performance from it, but at least you won't get incorrect execution. So that's a sort of a positive outcome here. OK, so a little bit of history. Usually I try to not harp on history too much in this course, even though I really enjoy it. The VLIW processors is, I wanted to make one point that a lot of this research is relatively recent. So if we go look at sort of the dates on this, these first processors and the first real VLIW processors was done in like the late 80s. So this is not going back to the 60s. This is like a portion of computer architecture work which is actually very, very recent. The first long instruction word processor was actually a floating point systems, FPS, that's what it stands for, processor. And this was actually a coprocessor to VAX machines. So it's something that could speed up your floating point on a VAX machine. This was very much the most basic VLIW processor. There was no interlocking, didn't take interrupts. It was really sort of for hand-coded vector arithmetic and floating point math. Probably when people talk about VLIW, the thing that pops into their head first is actually the Multiflow Trace processor, which was made by a small startup company called Multiflow. This was an outgrowth, actually, of a bunch of research that was done at Yale by Josh Fisher and a bunch of his students. And I won't go into too much detail here, but one of the interesting things is they really, really did have a long, very long instruction word here. 1,024 bits long instructions. So this is like a beefy instruction. This is, and you can have anywhere from 7, 14, or 28 operations per instruction. And this was not dynamic. What this actually was is this is how they made different configurations of their machine. So they actually had wider machines that were more expensive and narrower machines that were cheaper. So it's sort of a family of processors, and they customized the compiler to this. Josh Fisher actually is much more of a compiler guy probably than an architect by training, and you can sort of see that in his group's work and the PhDs that have come out of it. He now works for HP Labs, and is sort of semi-retired. At the same time, actually, there was also another company that was commercializing a very, very similar idea. This was the Sidra 5. This was Bob Rao, who's another very famous computer architect. He was a professor at the University of Illinois, and he developed a lot of these things, then sort of left and started Sidrome. And some of the interesting things in that processor is they had this cool thing. Instead of having a register renamer, they had a register file that the naming of the registers sort of changed as you did sort of function calls. We'll talk more about that later today, or maybe tomorrow, or maybe next lecture. But more really want to get out here is this is very recent. OK, so very long instruction words processors still want to have high performance. And we took all this hardware that was in a out-of-order superscale, and we sort of threw it out. Well, something's got to make up for it. And what makes up for it is a very, very, very smart compiler. So we put a lot of emphasis on the compiler in these sorts of architectures. And the compiler really has to do the scheduling. It has to do all of the dependency checking. It probably has to avoid all the different data hazards. And this is just sort of just getting started. We're going to talk mostly next lecture about all of the different optimizations that a compiler can do to try to approximate what a out-of-order superscalar can do, but by doing it statically. So it's a pretty cool trick. If you take all that hardware, you put it in the compiler, you run it once, and then every time you go to execute the code, you don't have to go and recalculate all the dependencies. Sounds good. OK, so let's see how we execute some code here, and what is the sort of performance aspects to executing loop code on a very long instruction word processor. So here we have a very basic array increments. We're going to take every element of this array. We're going to increment it by the value c. We run it through our compiler, and here's a sequential code sequence. This has not been scheduled yet for VLIWs, or for our VLIW architecture over here. So we load the value, we increment our counters, we actually do the floating point add, we store the value back, we increment the array index, and then we loop. Seems simple enough. Let's see how this gets scheduled here. Well, because the architecture and because the compiler knows about the latencies here, let's say this load here has a few cycles of latency. So it's going to actually schedule this add later. And the add, it's a floating point add. This has a couple cycles of latency also. So it schedules the consumer of that result here, this F2, later. And yeah, I don't know, it can sprinkle in the array additions and the counter additions kind of somewhere free. It has lots of open slots. But let's say it schedules it at the same time as the load and the store. So this is pretty cool. We are actually executing 2-wide parallelism here. And we didn't need all the extra overhead of in-order superscalar. Oh, and we can even schedule the branch somewhere. OK, so first question here. How many floating point operations are we doing per cycle? Are we doing very well here? This looks pretty poor. We have one floating point operation here, just this add. And we have 1, 2, 3, 4, 5, 6, 7, 8 cycles. Yeah. So we're having 0.18 or 0.125 floating point operations per cycle. It's not that great. We do have some parallelism. You know, we're executing 3 instructions here. It's better than nothing, but we're not really using the machine very well. Our out-of-order superscalar would probably try to take instructions that are below here, maybe intermix them, try to reorder a bunch of things, and try to run faster. So what's a technique to go faster? Well, one of the big as I said, we have a lot of emphasis on compilers in this unit. One of the things the compiler can do is it can actually unroll the loop. So here we have our loop. We unroll it 4 times. And now we're going to sort of take the loop overhead, and we're going to factor it out such that it only happens once every 4 times. Ooh, that sounds good. We're probably going to do some more work here per each iteration in the loop. But things get a little more complicated. What happens here if n, big uppercase N here, our terminating value, is not a multiple of 4? Well, we need to do something about that. We probably need to check sort of before we go to execute here whether we're doing OK or whether we actually are a multiple of 4. Conveniently, if n is big enough, we probably can run as a multiple of 4 for a long period of time, and it's only the last iteration that we have to clean up. But we need to generate some cleanup code, and the compiler is responsible to do this. So these compiler optimizations do take some effort. OK, so let's look at the scheduling now of our loop unrolled code. We can do a bunch of loads up front here. So we've intermingled these loops. And what's kind of cool is we can actually pull out the loads and sort of throw them to the top, and the stores and push them to the bottom, and then put all the adds sort of in the middle, and maybe sprinkle the array updates somewhere else. And when we go to actually schedule that, we're going to do something similar. We're going to have the loads executing first, execute the floating point adds, have the floating point stores, and have the result. But what you can notice here is we're actually starting to get some overlap. Because we've unrolled, we can overlap this load and the first floating point addition, because we've effectively covered the latency of our functional units by putting other loop iterations during that time. So if you look at this schedule versus the schedule back here, we've just sort of taken these dead cycles and we've put the other loop iterations in those dead cycles. In this loop unrolled case, we're incrementing these counters and the indexes not by 4 anymore. We're incrementing by however many times we've loop unrolled times the offset. So we're incrementing it by 16 now. Does that make sense? Because in this code here, we were incrementing R2 by 4, because that's the size of a single value is 4 bytes. So we have to sort of move our array index over by 4. But now, because we're batching up all this work together, we actually have to move the index by a bigger value. So we're moving it by 4, because we've unrolled 4 times the size of the data value, which was 4. So we're moving it by 16. And one of the nice things here, if you look, is in both the loads and the stores, we're using our register indirect addressing mode here to add in some offset. So we're actually offsetting, let's say, 12 plus this base register of R1 to figure out where we're actually doing the load from. But it's just sort of a convenient way that we don't have to compute a bunch of addresses. OK, so going back here, we can see we're starting to overlap actual operations with other loop iterations. Well, that's really cool. So we're starting to get some performance here. So let's look at the performance. So we'll ask the same question here. How many floating point operations per cycle? Well, hopefully it's higher. 1, 2, 3, 4. Divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cycles. OK, so that's 0.36 is a lot better than 0.125. So this is good. Loop unrolling is helping us. But is this everything, or can we do more in our compiler? So the smart compiler people came up with even a fancier idea, which is called software pipelining. So it uses a term we've seen before, pipelining, but does it in software. So the idea here is that instead of just having one loop, unrolling the loop, and then overlapping the iterations, we're actually going to take multiple of these schedules and interleave them, and try to fill some of these empty slots. So let's look at this. We're going to have the code unrolled 4 times. This is the same piece of code we had on the previous slide. And we're going to draw our schedule that we had before. So here's the schedule we had before in purple. OK, that doesn't look so bad. But now we're going to schedule it with another iteration of the exact same 4-time unrolled loop, shown here in green. So we've just overlapped this with this other iteration of the loop. Well, are we done here? Well, not quite. We still have some open slots here. So let's try to overlap even another iteration, as shown here in red. Now, the fix-up code that you need to have to do this correctly gets more complex, because all of a sudden now you're basically overlapping multiple iterations. But as long as you don't modify some value, as long as you don't do a store speculatively or a store, you're probably OK. Because otherwise, you're just doing loads, doing extra loads, doing extra work. You're doing extra work, and you're filling slots thinking that you're not going to have anything go wrong, or thinking that the index variable, n, if you will, is multiple of 4 and large, and you're not at the end. So let's put some names to these things. So we call the beginning here the run-up, the prologue. Here we actually have our sort of actual iteration. You can see that the, sorry, this is in green. That doesn't show up very well. There are instructions here. There's adds. It's pretty full. We're actually doing a lot of work on our VLIW machine here. And then the epilogue here is when we're done. This is when we're falling out. We're sort of at the last loop iteration of the outer loop, if you will. So let's do some math and look at the performance of this. OK, so that's the same question here. How many floating point operations per cycle? Well, we go look over here. We have 1, 2, 3, 4. And we have 4 cycles in our tight loop case. That looks pretty good. That's cool. We just got a bunch of performance. But we had to do a lot of compiler optimization to make this work. But we were able to use the parallels in the machine, and we were able to overlap 3 different iterations of this loop that we also did a software transform to unroll it 4 times. So this is called software pipelining. And I have a nice picture here to sort of show what's going on visually. So we're going to have time on the horizontal axis, and we'll have sort of activity of how many instructions are executing or something like that on the vertical axis, or shown here as performance. When you run multiple loop unrolled iterations, you have sort of some startup. You have the actual, you're running the loop, and then you come down from that. And that's better than having a lot of startup and sort of come down with a very small loop iteration portion here in the middle. But when we go to look at software pipelined, we can overlap basically one iteration loops execution with, or one loop's startup or with the loop iteration of another loop. And we can actually execute sort of our prologue, execute multiple iterations very tight, and then have our epilogue here. Yeah, so our software pipelining, we're only paying the startup and wind down costs once for the execution of a loop and not every iteration of the loop. So that's fun. That's cool. We're getting performance. Only the world was dense loops. Life would be easy. Alas, the world is not all loops. If we just had a processor which just did dense array calculations, and all of our problems in the world were just dense array computations, life would be really easy. But they're not. A lot of times code has lots of branches. It has if-then-else clauses. And here we sort of graphically show something like a if-then-else. So we have some piece of code. It makes a decision. It either executes the code on the left or executes the code on the right based on an if statement. So this is the if true statement, and this is the else clause. And data-dependent branches are a problem typically for very long instruction word processors. Now, why is that? Well, in an out-of-order processor, you can try to execute code sort of around the branches and move instructions above the branch and below the branch. But if you're doing static scheduling, when you hit this branch, and let's say it's a hard-to-predict branch, you can't really do anything because you've packed a bunch of instructions next to each other and they need to execute atomically. So it's not like you can like sort of move code up and down across that branch. The superscalar can do that because it has this instruction window, it has a bunch of techniques, a bunch of hardware to be able to do that. But in our VLAW processor, that's a problem. So I wanted to introduce a compiler, an important compiler nomenclature here, which is important for this class. It's called a basic block. So what is a basic block? A basic block is a piece of code which has single entry and single exit. So this is a basic block. It has one entry and one exit. And why is single entry important? Well, if you can jump into the middle of this piece of code, the compiler cannot necessarily reorder the instructions inside this block. And if you have multiple exits, and say you exit here, the compiler can't push instructions below that exit point. But if you have a basic block, the compiler basically knows that this instruction sequence is going to execute effectively atomic, but not actually atomic. I mean, you can have other things going on inside there, but from a compiler perspective, it can reorder the instructions around in here to get better performance. OK. So loops are easy. We can solve for pipeline. We can unroll. Squirrely code, if then else, spaghetti code, a lot harder. So the compiler guys came up with some fancy tricks to make VLIWs work better and to take advantage of some of the code motion that a out-of-order superscalar does, but in the compiler and not in dynamically in hardware. And one of the more famous ways to do this is something called trace scheduling, which was John Ellis's, who was one of Josh Fisher's students' thesis work. And this was in the Bulldog compiler out at Yale. So what you do is you profile the code. And you come up with the probabilities that these branches go the one way or the other way. So when I say profiling, this is not something that the hardware is doing at runtime. This is something that you do with the program while you're sort of still back in the compiler stage. You take the program, the compiler goes and runs it on some given input set, and comes up with probabilities of which way things go. And then what you do is you take this profile information, and you come up with some guess at what is the most probable one. And we're going to circle that here and say these darkened edges are the most probable sort of path through this squirrely piece of code, given this is the entry point. Now, this doesn't mean that you can't have branches that sort of branch out of this. But if you do, you need to have some fix-up code. Because what we're about to do is we're going to take this entire sort of big swath of code here. We're going to remove all of the branches. And we're going to schedule for our VLAW processor as one big monolithic piece of chunk of code. And by doing this, we can move instructions, let's say, that are down here, which there's open slots to execute in the early portion of this code sequence. We can move them up. And likewise, you can move things that use the result of long latency instructions up here and push it down across branches. So our out-of-order superscalar does this with branch speculation. But our compiler can do this on our VLAW processor using trace scheduling. But when we do this, we have to be careful, because there's always the possibility that, while unlikely, you can still branch the other way. So typically, the way this is done is you have some form of fix-up code. If you branch away, you have to sort of fix up anything that was after the branch that made a committed change, if you will, to the processor state. You need to sort of roll that back somehow. So we're basically in software doing the rollback case from our out-of-order superscalar. So instead of taking the architectural register file and copying it to the physical register file on branch mispredict, instead our compiler generates a code sequence which does that same operation if you were to branch away here. and will roll back only the certain registers that need to be rolled back and only the memory state that needs to be rolled back. So that's pretty cool, is that we can basically take a lot of the functionality that was done in our out-of-order superscalar and put it into software using trace scheduling. This is a rich field in the compiler research world. And there's been a lot of problems with VLIWs, or classical VLIWs. And people have sort of built things that are somewhere between superscalars and classical VLIWs to solve some of these problems. People have come up with fancy compiler optimizations to solve some of these problems. And some of them are sort of still open. First one on our list here, object code compatibility. In a superscalar, because we came up with one serialized instruction sequence, and the architecture came up with all the scheduling, you could change the number of functional units under the hood in your microarchitecture of your processor, and no one was ever the wiser. It would still execute the piece of code. It may not be optimal, but it would still execute. That's not necessarily the case for classical VLIWs. So you have to recompile the code when you change the microarchitecture. So it's a very tight coupling between the architecture and microarchitecture, because our instruction encoding now says there's exactly, let's say, 2 integer, 2 memory operations, and 2 floating point operations, something like that. But all of a sudden, if you build a machine which has a different mix, your schedule is completely wrong, so it's going to have bad performance, and it's just not going to execute because you probably changed the instruction encoding standard when you go and make that different VLIW. Another big problem is code size. As you can imagine, there's a fair number of no operation instructions or no operation operations inside of a VLIW bundle. If you can't fill a slot on a superscalar, you just don't put the instruction. On a VLIW, if you can't fill the slot, you have to put a no op there, because you got to put something there. So this causes some serious problems. Also, things that hurt this even more is these fancy techniques that we talked about, loop unrolling, software pipelining, that bloats the code size. We're replicating code. We've unrolled the code. We are using more space. This hurts our instruction cache size and instruction cache footprint. We'll talk a little bit more about this in a few slides, but variable latency operations are very hard to deal with. So if you have a load, you don't know whether it's going to take a cache miss or not. So your schedule may be wrong if you guessed wrong. You can do it with some high probability. You can say, oh, I think this load usually takes a cache miss. Or you can say, oh, I think this load usually doesn't take a cache miss. But you can guess wrong. And there's similar sorts of things with this, with sort of branch mispredictions. Scheduling for statically unpredictable branches. This gets very hard. There are some techniques to solve this. There is something called predication, which we'll talk about in a few slides, that helps to solve this. So you can add things back into the architecture, into your VLIW architecture, to deal with sort of short branches that are very hard to predict, or data-dependent branches. And as I said, depending on your design, precise interrupts can be challenging, to say the least. If you're actually using the EQ model, you probably have a hard time figuring out what to do on a single step, or if you actually have a branch sort of in the middle while you have a pending operation going on, sort of undefined, it's icky. It's sort of similar to having like branch delay slots and having a fault in your branch delay slot. What do you really do with that? Also, this is an interesting point here, is that does the fault, if you have a fault on, let's say, one operation in a bundle, does the entire bundle fault or just the operation fault? Or take an interrupt? Typically, the way people implement this is you have the entire bundle or the entire instruction be atomic. So if anything in the bundle takes a fault, you actually don't allow any of the sub-operations to commit. That's kind of the most rational thing to do. People have done things in the middle. I probably don't recommend you building any of those machines. And the VLIWs that I've always built, an entire bundle is atomic. That makes traps a lot easier. But people have not always done that. One of the interesting cases, if you think about this, if you have, let's say, 5 instructions in a bundle, and only one of them faults, maybe you handle that one, but you let the other ones commit, and then when you come back, you have some sort of mask to say which ones you need to re-execute. People have built things like that. They get tricky. OK, so let's talk the rest of today's lecture and next lecture, we're going to talk about techniques to solve a lot of these problems or solve a lot of these challenges. Some of them are compiler, some of them are hardware, and some of them are both. First thing people try to do is they try to come up with compressed instruction encodings or fancier instruction encodings. But when you go to do this, it makes the front end more complicated. So here we have, let's say, some instruction. But inside of that instruction, we can have different groups, which inside of the group executes parallel, but between groups is not parallel. So something like the Itanium processor, which was the IA64 processor from Intel, actually looks something like that. Other things you can do is you can have compressed instruction formats. And then when you go to actually execute it, you uncompress the no-ops into your instruction memory, maybe. That's what multi-flow trace processor did. This marking parallel groups is what I was talking about before. Sidrome had an interesting solution to this. They actually had a single operation VLIW instruction. So to save space, they sort of had their wide instructions. But if you had a case where you were only going to execute one operation in an instruction, there was a special encoding format just for that case. And that saved a lot of encoding space, or a lot of instruction space, if you will. Another example of this actually is a processor I worked on called the Tylera Tile64 processor. We were a 3-wide VLIW. We had an encoding standard, or we have an encoding standard which allows you to execute either 2 instructions at a time or 3 instructions at a time. And that can, when you're executing 2 instructions at a time, you have a richer palette of instructions you can execute. So it's sort of something in the middle, gives you some better code density benefits, but not with the sort of complexity of having sort of compressed formats and things like that. OK, so that's one way to deal with the instruction encoding challenges. One thing you can think about, though, is you can just have a bigger iCache, or and a wider bus from your iCache out to your memory system. That does solve a lot of these problems. That costs hardware, but it's a sort of a simple, stupid solution to the problem versus a smart solution. These sort of things on this list here are complex, smart solutions. Simple solution, just have a bigger instruction cache. And if you have bigger code sequences, you won't feel the performance hit as much from that. OK, so now we're going to sort of go through different problems with VLIWs and different solutions to those problems. Sort of the top one on this list is a problem of hard to predict branches and how that can limit instruction level parallelism. So you just remove the branch. And we're going to call that predication. So we're actually going to add instructions to the hardware, which we're actually going to add 2 instructions here. So this is limited predication. But we're going to add 2 very simple instructions. And if you look at these instructions, they're very similar to the question mark, colon, or the select operator in C. So what does that operator do? If we have A equals, I don't know, C question mark, D colon E, semicolon. What does this do? Well, it loads A. If C is true, it loads A with D. If C is false, it loads A with E. Well, you can think about actually doing this with some sort of if-then-else piece of code, which is pretty common. If A is less than B, so you can sort of put that here. X gets A versus X getting B. That's our select operator. Well, we can add two special instructions here for our limited predication. Move if 0, and move if not 0. Well, what does this do? Well, if this operand is equal to 0, then this RD gets RS, else, and that's all it does. That's all that instruction does. And the flip one here is it checks if it's not equal to 0. Why is this cool? Well, this allows us to transform control flow into a data instruction. So we taken a branch out. So if we look at this piece of code, if we were doing it with branches, set less than, we do a branch. So this computes our condition code flag here, branch equals, and if it's the one way, it branches here. If not, it jumps over it. So we have a bunch of control flow here. We have two control flow operations, the branch and the jump. When we add these instructions, we can basically do that if-then-else in an instruction. And basically, every VLIW processor you're going to look at is going to have predication, or at least limited predication. This is not full predication. This is limited predication. We'll talk about full predication in a second. OK, so let's think about that for a second. We just took control flow. We turned it into something which is never going to take a branch mispredict. That sounds pretty cool, because branch mispredicts, were pretty bad. If we had a branch which was hard to predict, we didn't know with high probability if A was greater than B or not, we can just sort of stick this code sequence in here and just be done with it. And why this is really important for very long instruction word processors is because whenever you take a branch mispredict, you're basically having a bunch of dead instructions, and you can't schedule something in that point. But a out-of-order superscalar can attempt to sort of schedule things in there. We can try to schedule non-dependent operations. But our compiler has to come up with some code sequence and has to make them parallel at compile time. OK, so a few questions here. What happens if the if-then-else has many instructions? This was a very simple case here. We just sort of had one thing inside of each of these if-then-elses. It's not the end of the world. What you can do, and typically what people do with partial predication, which is what this gives us, is they'll actually execute both sides of the if statement, interleave them in your VLIW somehow, and then choose the result at the end with a predication or a move z instruction. Or these are typically called conditional moves. If you go look in something like x86, I think these are actually called cmove. If you go look in MIPS, it's called moveZ, but people sort of name these things slightly differently. So it's not the end of the world, but when you go to do that, you're actually going to execute extra instructions that you may not have to have executed. And that's a bummer, because you could very easily, if there's a lot of code in here and a lot of code in here, and you're executing both code sequences, you're basically doing twice as much work. And if it grows large, you're doing lots of extra work, and you may not have enough open slots to sort of fulfill that. At that point, you have the choice. You actually put a branch in. If it's unbalanced, also not the end of the world. It's probably actually a little bit easier. You're probably not going to execute twice as much code. At some point, though, you may want to actually, if it's super unbalanced, like 1,000 instructions on the one side of the branch and like 2 instructions on the other side of the branch, you may just want to put a branch, an actual branch there, and not try to predicate it. Because if you took the side which only has 2 instruction, or the 2 instruction case, well, all of a sudden you've bloated that by an extra 1,000 instructions kind of in the common case, and that's not very good. So that's partial predication. Let's talk about full predication, which is kind of the extension of that. Instead of just adding a simple instruction which moves data values dependent on another value, it being 0 or not, let's say every single instruction in our instruction sequence, except for maybe, let's say, branches or something like that, can be nullified based on a register. What does this look like? Well, here we have some little bit more complicated piece of code. We have 4 basic blocks. It's roughly an if, then, no, see, if, else, then, and then sort of some code at the end. And let's see how this works with predication. Well, what you can do is, first of all, you have to somehow set the predicate registers. So typically, these architectures have extra registers, which we call predicate registers. The predicate registers get loaded with some values sort of early. And then, let's say this instruction and this instruction execute in parallel. Different notation here. Let's say there's just a semicolon here, and there's sort of brackets around that. And this, in front of the instruction here, in parentheses, we have a predicate register, which says whether this instruction was supposed to execute or not supposed to execute. Now you can do even more complex things than our partial predication. Instead, now you can basically execute everything and not have to do any moves at the end. You don't have to do any bookkeeping, and you can only execute just the sort of side of the branch that you need to execute. Scott Melke in ISCA 95 showed that if you do this and you sort of have a fancy enough compiler, he was working at UIUC on the Impact compiler, you can remove, let's say, 50% of your branches. A lot of these branches are sort of short little branches in your programs, and with full predication, you can do some pretty fancy stuff. This showed up in the Plato compiler, which was a HP, or the Plato architecture by HP, and the sort of compiler for that, which was the Wenmei Hu's project at UIUC, the Impact compiler. So you can sort of see that you can get a lot of benefit from this. So I'm going to stop here today, but I just wanted to briefly wrap up and say we started talking about how to deal with dynamic events and how to get a lot of the advantages of speculative execution from out-of-order superscalars, but in a statically scheduled regime. And we're going to talk more about how to do some of this code motion, how to move instructions across branches, how to move memory operations across other memory operations. And then we're going to talk about how to deal with some dynamic events, which are hard to deal with in a statically scheduled environment in the next lecture. OK, well, let's stop here for today. So today we're going to continue our discussion of very long instruction word processors. And we're going to start talking about how to change a classical VLIW processor into a processor which can actually get a lot of the parallelism and instruction level parallelism you can get inside of out-of-order superscalars. And to do this, we're going to have to add a lot of extra features to a traditional or a classical VLIW. And we're going to slowly work through that. And we're going to basically list out or enumerate all of the possible different types of instruction level parallelism and where that comes from in something like an out-of-order superscalar. And we're going to systematically add features into a very long instruction word processor or VLIW processor to get us to that point. But I'll give you a hint that not all the things that out-of-order superscalars can get are easy to get in VLIW processors or even possible in the realm of things that people have built up to this point. So before we do that, I wanted to take a step back and review something from last class and also review something from, I wanted to clarify something that I had said about how the EQ model and the LEQ model, or the equals model or the LEQ model, work from a scheduling perspective. So let's let's back up to slides way back at the beginning. And more of what I wanted to say was just a comment that the equals model of VLIW scheduling and the less than or equals scheduling model are just scheduling models. That's all they are. They're not actually something that's in the hardware. They may influence what the hardware has to do or what the hardware has to provide. So for instance, if you have an equals model and you have an instruction followed by another instruction in your very long instruction word processor, and let's say the instruction reads the value of some register in sort of the shadow of while that value is being computed, you're going to get the old value in an EQ model. So as a quick code example here, we can take a look at a bundle of instructions here. Let's say you have something like a multiply, R1, R3, R4, and in the same bundle or in the same VLIW instruction, we have some other random thing here. We're going to use the curly braces here to denote that it's one instruction or one bundle. And then this multiply, we'll say, has a latency of 4 cycles. So you can't actually go read the result. And if we look at something like an EQ model, we're going to end up with, let's say we just have some other instructions in here. But this one here is important. We have an add. Which reads R1. Note this multiply writes R1. But as we said, the multiply has a latency of 4 cycles. So this, in the EQ model, is going to get the value before the multiply. So it's not going to pick up this result. And then let's say we just have some other random stuff. I don't know, maybe some non-dependent adds and subtracts. And I'm not going to write the registers here because they don't read anything or write anything which is read or written in these 2 bundles. Maybe you have a no-op. And then finally, down here, we have something which does a load of R1 and gets the result of this multiply. So all I'm trying to get across here is this is a scheduling model of what the compiler needs to do and where it needs to place code that we're talking about in these scheduler models. It's not a hardware problem. If we were to try and take the same piece of code and run it in an LEQ model, the main difference is this add here, which reads R1, would not be allowed in the shadow here. So what would the shadow of this multiply, or the delay of the multiply? Because if you were to, for instance, take an interrupt or something like that, and this add were to get moved later than this load, or move more than 4 cycles later, or 3 cycles later, you would actually pick up the new value, and you'd basically change the semantics of your program. So if you were to do this in something like a LEQ model, this add would have to be above the multiply, and you'd have to replace this with a no-op. But more of what I'm trying to get across here is that these are just scheduling models and not actually scheduling models that the compiler wants to use and not models, or not hardware models. The hardware has to implement something which makes sense for the scheduler model. But when we talk about these different concepts, they really are just a software scheduler model. OK, so now we're going to go back forward here and move on to new content today. So today we're going to continue our discussion of very long instruction word processors. And we're going to start talking about how to change a classical VLIW processor into a processor which can actually get a lot of the parallelism and instruction level parallelism you can get inside of out-of-order superscalars. And to do this, we're going to have to add a lot of extra features to a traditional or a classical VLIW. And we're going to slowly work through that. And we're going to basically list out or enumerate all of the possible different types of instruction level parallelism and where that comes from in something like an out-of-order superscalar. And we're going to systematically add features into a very long instruction word processor or VLIW processor to get us to that point. But I'll give you a hint that not all the things that out-of-order superscalars can get are easy to get in VLIW processors or even possible in the realm of things that people have built up to this point. So before we do that, I wanted to take a step back and review something from last class and also review something from, I wanted to clarify something that I had said about how the EQ model and the LEQ model, or the equals model or the LEQ model, work from a scheduling perspective. So let's back up to slides way back at the beginning. And more of what I wanted to say was just a comment that the equals model of VLIW scheduling and the less than or equals scheduling model are just scheduling models. That's all they are. They're not actually something that's in the hardware. They may influence what the hardware has to do or what the hardware has to provide. So for instance, if you have an equals model and you have an instruction followed by another instruction in your very long instruction word processor, and let's say the instruction reads the value of some register in sort of the shadow of while that value is being computed, you're going to get the old value in an EQ model. So as a quick code example here, we can take a look at a bundle of instructions here. Let's say you have something like a multiply, R1, R3, R4, and in the same bundle or in the same VLIW instruction, we have some other random thing here. We're going to use the curly braces here to denote that it's one instruction or one bundle. And then this multiply, we'll say, has a latency of 4 cycles. So you can't actually go read the result. And if we look at something like an EQ model, we're going to end up with, let's say we just have some other instructions in here. But this one here is important. We have an add. Which reads R1. Note this multiply writes R1. But as we said, the multiply has a latency of 4 cycles. So this, in the EQ model, is going to get the value before the multiply. So it's not going to pick up this result. And then let's say we just have some other random stuff. I don't know, maybe some non-dependent adds and subtracts. And I'm not going to write the registers here because they don't read anything or write anything which is read or written in these two bundles. Maybe you have a no-op. And then finally, down here, we have something which does a load of R1 and gets the result of this multiply. So all I'm trying to get across here is this is a scheduling model of what the compiler needs to do and where it needs to place code that we're talking about in these scheduler models. It's not a hardware problem. If we were to try and take the same piece of code and run it in an LEQ model, the main difference is this add here, which reads R1, would not be allowed in the shadow here. So what would the shadow of this multiply, or the delay of the multiply? Because if you were to, for instance, take an interrupt or something like that, and this add were to get moved later than this load, or move more than 4 cycles later, or 3 cycles later, you would actually pick up the new value, and you'd basically change the semantics of your program. So if you were to do this in something like a LEQ model, this add would have to be above the multiply, and you'd have to replace this with a no-op. But more of what I'm trying to get across here is that these are just scheduling models and not actually scheduling models that the compiler wants to use, and not models, or not hardware models. The hardware has to implement something which makes sense for the scheduler model, but when we talk about these different concepts, they really are just a software scheduler model. OK, so now we're going to go back forward here and move on to new content today. OK, so we left off talking a little bit about how to encode instructions in VLIW, or how VLIWs encode instructions. And as you may recall, in a VLIW instruction encoding, you have a very long instruction word. So it could be, I don't know, many, many bytes. So if you go look at something like the multi-flow processors, the multi-flow trace processors, they had very long instruction words. They could, I think, execute something like, in their largest machine configuration, 20-some instructions. And they had to encode this. But one of the challenges was that you didn't necessarily want to have all of that encoding space used all the time. So if you are executing a simple instruction or something which doesn't actually need all of that encoding space, you end up with a whole lot of no-ops. Or if you have a very long dependency string in your execution trace, if you will, so you have an instruction which is dependent on the next instruction, which is dependent on the next instruction, which is dependent on the next instruction, and you cannot fill any of the extra slots, you're going to end up having a lot of no-ops in your program. So how do we go about solving this? Couple different solutions here. Sidra 5 went off and added a particular instruction, which is a single operation instruction, and used a much smaller amount of memory. So this would effectively reduce your instruction cache pressure. There was compressed formats in memory, so you can hold your instruction sequences in memory, and then when you go and pull it into your instruction cache, it would expand to the fully expanded version. And this is kind of like a compression algorithm. You're basically compressing your VLIW instruction sequences, because otherwise these things are very, very large and have lots and lots of zeros or no-ops in them, because the probability you're going to fill sort of 20 instructions per cycle is low, but you want that capability there in case you actually do want to execute 20 instructions per cycle. Another solution here is what's actually used in the Intel Itanium or IA64 processor line, and also the TI DSPs, the C6000 series. They have the ability to effectively mark where a bundle starts and stops. So it's something sort of between a variable length instruction and a fixed format VLIW instruction. So we'll talk more later in today's class about how IA64 or Intel's Itanium handles this. But roughly what happens is they have a fixed instruction format, and you can fit sort of 3 instructions per bundle, or what they call a bundle. And then if you want to go over that, you can keep going over that. And they have special bits in their instruction which says, oh, well, this is going to express some more parallelism later. So you need to look at the next bundle and try to fetch that bundle, and that's all can be executed parallel. So it's still a parallel execution semantics, but the formats are not necessarily fixed. And this is sort of outside the bound of classical VLIW. Now it's going into a little bit more modified VLIWs or more contemporary VLIWs. So today we're going to, as I said, talk about how to go about getting all the performance that out-of-order superscalars can get, but in the context of a VLIW. So we're going to slowly build up all the different techniques that out-of-order superscalars have and all the ways that they can get instruction-level parallelism, and then apply that inside of VLIW, or how we make small changes to classical VLIWs to get a lot of the performance back. OK, so let's talk about the first trick here. One of the questions that comes up, or the problems that comes up here, is if you have branches and they mispredict, this can limit your instruction-level parallelism in a VLIW. OK, so why is this worse than in a out-of-order superscalar? Well, an out-of-order superscalar can dynamically schedule around branch mispredicts. So if you branch mispredict, you can basically schedule other code or speculatively schedule code depending on your prediction. But on something like a VLIW processor, that's a lot harder to do because you don't have a dynamic scheduling engine behind there. The compiler had to go do all that scheduling statically at compile time. So how do we go about fixing this? Well, one solution is just to eliminate all the hard to predict branches. So you take out the branches that might be hard to predict. So your branch predictor is trying really hard. You could still have a branch predictor in your VLIW processor, but some of these things you don't know. It's like a data-dependent branch. How do you know which way it's going to go? And this is a problem even for superscalars, but at least in a superscalar, you can try to sort of backfill instructions or try to do something or move around, if you will, loads or long latency instructions around branches. So in an out-of-order superscalar, you can potentially move a load beyond a branch. But in a VLIW processor, that's not easy to do because the compiler has to make that decision whether that branch is going to predict taken or not taken. And that may change over the lifetime of the program. And it may also change as the depending on the sort of input sets to the program. So it may not be something that's compiler time even knowable. OK, so our first technique here that we're going to use is called predication. So let's define what predication is. Well, first of all, predication is a technique that allows you to basically change the result of a register based on some other register. And it's going to let us transform hard to predict branches into data flow or data dependencies. So we're going to add something to our instruction set, and it's going to take what looks like a small branch or a short distance branch, and we're going to basically execute both sides of those branches, or the taken and the non-taken code path, and then at the end, decide which one was the right one with something like a select operator from C. So this is like the question mark colon operator, which no one ever uses in C. This is sort of the equivalent of that, but we're going to do it in one instruction, or maybe two instructions. So let's take a look at how this helps with small branch regions or branches which are hard to predict. So we're going to introduce two instructions. And I also want to point out that predication sometimes shows up in superscalars, processors, or sequential instruction sets also. So a good example of this is two instructions very similar to this are actually in x86. They're called cmove, or conditional move. And we're going to introduce conditional move as the most basic form of predication. So let's look at the semantics of these two instructions we add for conditional move. First instruction here, move 0. So what does move 0 do? Well, move 0 tests whether one of these input operands here, RT, is equal to 0. And if it's equal to 0, it's going to move RS into the result register, or the destination register here. So it's going to move RS into RT, or RS into RD if RT is equal to 0. And if RT is not equal to 0, it's just going to leave RD alone. OK, well, on first appearances, that seems like a very simple instruction. It's basically just doing a copy operation. It's a gated copy. It looks a lot simpler than something like add or subtract. We don't have to do any math, at least. There's no compare. I mean, the compare is easy. It's just the equals. It's not a less than equals. So it's a pretty simple instruction. And we're also going to introduce move not 0. So it's kind of the complementary one of this. And we're going to want this because when we go to execute code, we're going to want to, let's say, have an if then else. And we're going to want to execute the then and the else at the same time, or roughly at the same time, or indiscriminately, not dependent on the branch. And at the end, we're going to decide which one was the correct one. And we need sort of two instructions here to choose, well, was Was the positive one the right one, or the one where the conditional value is true or false the right one, or the one where it was true, or vice versa? So move not 0. Move not 0 is going to do the same thing here. It's going to see, except the sense of the condition code is going to be different. It's going to sense if RT is not equal to 0. And if RT is not equal to 0, then RS is going to go into RD. Else, we're just going to leave RD alone with the original value of RD. OK, so let's walk through a quick code example here and see how this helps. So here we have a code example. We have some C code. We have non-predicated MIPS-like assembly code. And then we have a MIPS-like assembly code here with these FANCI2 predication instructions. And all three of these are doing the same thing. So let's look at this piece of code here in the C code. It's probably the easiest to understand. It's going to start off, and it's going to say if A is less than B, so there's a condition, and there's a then and an else. So what does this actually implement? Well, this is a minimization function, or a min function. X gets the minimum of A or B. If A is less than B, it gets A. If A is greater than B, it gets B. So it's going to assign to X the smallest value of A and B. And these sort of if-then-elses, you can see here it's pretty short. We don't have a whole lot of code in either the then case or the else case. And that's going to be important in a second. You'll see why. Mainly it revolves around if you have lots and lots of code, or one of the sides of the branches is long, it may not make sense to actually predicate this, because there's some cost to predication. OK, so here's some assembly code, does a similar sort of thing. Set less than, this is a comparison operation in MIPS. So we're going to do set less than, and these are going to be R2 and R3 are going to have our two A and B values here. If it's less than, we're going to put it into R1. If not, this gets set to 1 or 0. And then we have a branch 0 here, effectively. What is this? This is a branch. OK, so branch equal with 0. It's a little odd. We probably should have just put branch 0 there instead. But it's going to check to see whether this value is 0 or 1. And if it's the one direction, it's going to jump to L1. If it's the other direction, it's going to fall through and then jump over this move. And these two moves here are the two assignment operators, the x equaling A or x equaling B. OK, that's not so bad. Let's analyze how long this takes, how many cycles this will take to execute on a sequential machine. OK, it does a set less than. It's 1. It does this branch. So that's 2. Let's say the branch is not taken or falls through. 3, 4, and then the jump over. So it's going to be 1, 2, 3 instructions in the one. Is that right? 1, 2, 3, 4 instructions in the one case. And the other case, it's going to take the branch and jump to here. So it's going to be 1, 2, jump over all this stuff, 3 instructions. OK, that's not so bad. So the one case is 4 and the other case is 3. They're different. Now, something else that makes this interesting is, let's say this branch is mispredicted. It's a data-dependent branch, A and B. So what's a good thing to predict here? Can our branch predictor do a good job on this? I don't know. Depends on what you know about A and B. If the compiler knows nothing, or the hardware knows nothing, you're not going to be able to do a particularly great job. So let's say it's a data-dependent branch, and it's 50% the one direction and 50% the other direction. Is this going to slow down our execution? Well, sure. It's going to slow down our execution because all of a sudden, when we take a branch, one of the directions, whichever way we predict, the mispredict path is going to add some mispredict penalty. So instead of the one path being 3 and the other path being 4, let's say the branch is predicted I don't know, let's say the branch is predicted not taken. So it predicts the fall through case. So all of a sudden, the fall through case is going to be 1, 2, 3, 4 instructions. And let's say we have a 2-cycle branch mispredict penalty. So let's look at the other case. So the other case is going to be 1, 2, and then 2 cycles of mispredict. So that gets us up to 4. We're to branch over 5. So it's going to be 5 cycles. So all of a sudden, we have our branch mispredict penalty coming into the equation here. And 2-cycle branch mispredict is relatively benign. If that starts to go longer, then you really start to have problems with this. OK, so let's take this code sequence and look about how to predicate it. So if we're going to go predicate this, we're actually going to execute both sides regardless of the value of the if clause or the conditional clause here. So if we look what we do, we actually have restructured the code here a little bit. And this is our compare. This is our if still up here. We have a set less than. And then we say if R1 is 0, move R2 to R4. Else, just leave it alone. And then here, if R1 is not 0, move R3 to R4. And what's important to note here is this non-destructive operation, especially here in this last instruction, is really important. Because if the move 0 was executed and that copied a new value into R4, and then this move not 0 were to somehow change R4, you lose that result from this previous one. So this really depends on these operations being non-destructive if their condition is not true. OK, so let's analyze this from a number of instructions perspective. First question is, does this matter what happens to the branch or what happens to the condition? Is it going to have different numbers of instructions or different numbers of cycles dependent on the direction of the condition? Well, no, there's no branch. Nothing's going to change. So in all cases, this is just going to take 3 cycles. So all of a sudden, we transform something which can take, as I said, if let's say you have a branch mispredict penalty, 4 cycles or 5 cycles. So on average, let's say the branch is taking 50% of the time either direction. We'll split the difference there, and we'll call it 4.5 cycles on average. And we've turned it into something which takes 3. Well, that's a great win. So where else is this useful? Does you always need to have if, then, else clauses to make this work out? So no. This also works good for small code hammocks. So I say a small code hammock is just a if which jumps around a small piece of code. And if you can't predict that if very well, then it makes sense just to go execute effectively what's inside that code hammock, or that small piece of code, always. If, for instance, you have 2 instructions inside of a code hammock, and your mispredict penalty is like 10 cycles, and you don't know whether the branch is being taken 50% of the time either way, all of a sudden, your average mispredict penalty is going to be something like 5 cycles. You could have just executed the code in the middle, and it would have been faster. You could have executed the 2 instructions and then just done a conditional move at the end, and that would have been basically always better. OK, so we bring up some questions here. What if the if, then, else has lots of instructions? So let's say we have if, then, else here, but there's 1,000 instructions here and 1,000 instructions there. Should we predicate this? Let's say the branch mispredict penalty, as I said, it's 10 cycles, and it's 50% either way. But there's 1,000 instructions in the if, the then clause and the else clause. Well, no, that would never make sense to do, because you're basically doubling your code, and if there's a lot of code there, you'd be better served by just doing the branch, because you'd be taking something that was could be 1,000 instructions and turning it into always 2,000 instructions, or doubling the number of instructions executing, versus just adding, let's say, 10 cycles of branch mispredictability, or an average 5 cycles of branch mispredictability to your 1,000 that you have to execute. So all of a sudden, you're adding a little overhead. So where this predication really helps is sort of for small pieces of code where you don't necessarily know the branch outcome, or can't predict the branch outcome very well. OK, what if the code is unbalanced? So you have an if, then, and an else. But the then clause and the else clause are very different in size. So one is 3 instructions, and the other is 1,000 instructions. Does this make sense? Well, it goes back to the same argument we had before with the very large if, then, else clauses. If the code is really unbalanced, you have a lot in the then clause and a little bit in the else clause or something like that. And let's say the branch is taking 50% of the time, it might make sense just to use an actual branch there and deal with the mispredict penalty costs versus trying to somehow predicate it. Because in effect, what's going to happen is, let's say you have 3 instructions and 1,000 instructions on the 2 different sides. You're going to be executing, if you predicate, 1,003 instructions every single execution time, plus maybe some sort of conditional moves at the end, some overhead involved. Versus if you have 50-50, and you have to add a little bit of a branch overhead penalty, your 50-50 chance is going to say, well, I'm taking 1,000 plus 3, and I'm going to add those 2 things together and take the average of them, basically. So it's going to be, what's the average of that? It's going to be like 501 or something like that, or 502 cycles. And that's going to be better than always executing 1,000 cycles. Let's see, anything else we wanted to say here? Yeah, one last thing I wanted to say here before we move off this slide. Move 0 and move not 0, or sometimes called CMove, conditional move instructions, are what are called partial predication. And we're now going to move on to full predication, where we can actually put conditions on every single instruction in our register, every single instruction in our ISA. But this is a little bit easier to do than full predication. This is sort of the first step that people typically implement. And it's called partial predication. And just to hammer this home one more time, predication is really turning what was control flow into a data flow operation or a data operation. OK, so let's take a look at full predication. Full predication, we're actually going to change the instruction set such that all of the instructions can be, or almost all the instructions are executed conditionally based on some predicate. If the predicate is false, the instruction is not going to do anything. It's just not going to have any side effect. So let's look at a code sequence here. So in this code sequence, we have an if, then, and an else, and then some code after we're done. So here we have if. A little bit different. This is not actually in MIPS code. This is something just sort of pseudocode here. But it's going to say, this is our if here. If A is equal to B, then branch to B2, else fall through. Here we're going to execute our else clause. And when we're done, we're going to branch over the then clause. So not anything interesting here. 4 basic blocks. I don't know if we've introduced this term yet in this class, but I wanted to introduce the term basic block. Basic block is a piece of code which has strictly one exit point and one entry point. So you could enter it from other places. You can jump to it from other pieces of code. But once you enter the piece of code, you're going to execute the code all the way to the end, and then there's one place you can leave. So you can either jump to someplace else or branch, and you can fall out to two different places. But the exit point is only one place. So what we're going to make the differentiation here is the piece of code can have, for instance, two branches. That's not called a basic block. That's called a bigger type of block. But this is a compiler term. And it's just good to know. OK, so let's apply full predication here. So these are relatively short code hammocks. 2 instructions here, 2 instructions there, and 2 instructions in the else, 2 instructions in the then clause. This looks like a really great place to think about predicating. OK, so let's take a look at the predication here. And I want, before we do that, I wanted to just say that one of the big reasons that we're trying to predicate on a VLIW in particular is in a VLIW, we have lots of extra, or we could potentially have extra parallel execution slots. So in our instruction sequence, or instruction encoding, we have extra places to put code. So it may not actually hurt us to predicate. Because a lot of times when we go to predicate, we're basically going to execute both sides of the if, then, and else. And it's bad if we have to execute both sides of the if, then, and else, and they're big sequentially. But if you try to sort of slide them up next to each other, if you have extra no-op slots or extra slots in your VLIW, you can actually decrease the critical path through your program. So let's look at this. And we're actually going to do this in this example. So in this example here, we took this piece of code and added full predication. So when we say full predication, we added some extra things to these instructions. They look a little strange at first. So here we have instruction 3, instruction 4, instruction 5, instruction 6. And these are the same ones that were back over here. But instead, we added some extra words in front of them here, or these parentheses with P's in front of it. What that is these are predicate registers. So we're going to add a second register file into our processor where we can store effectively 1-bit values, sort of true or false values, that are going to determine whether this instruction executes or doesn't execute. Excuse me. So what this means is if P1 is 1, execute this. If P1 is 0, nullify this instruction 3 here. And we have a double pipe here. What am I trying to show with this? Well, I'm trying to show that this is parallel. This and this are executing at the same time, because we have a very long instruction word processor. We can execute multiple things at the same time. And what we've done here is we've actually slid this up next to the then up next to the else. And we're going to execute them at the same time, dependent on these predicates. So this is the else block, and this is the then block. We're going to execute concurrently. OK. Sort of stuff before the if, stuff after the if, then, else is all done. That's sort of from that 4-basic block example. What's this instruction? This instruction has very interesting semantics. And this is something that you probably have to add if you're going to try to have full predication. OK, so it's a compare. So this is our comparison. If A is equal to B, and then it writes into 2 outputs. Ooh, that looks broken. That looks wrong somehow. How can we have one instruction write to 2 things? And what is the semantics of it? What does it write to here and here? Well, what this is actually doing is this is writing the positive outcome of this compare to the one, and the inverse, or the negation of that, to the other. And this is useful because then we can go use these predicates down here. We can use the positive one and let's say the negative one, and that can drive whether we execute the sort of else clause or the then clause. So lots of instruction sets that have full predication have either something like this. This is one option. You can actually have sort of 2 outputs, and you load 2 predicate registers. The other option is when you go to actually encode the instructions, you have sort of a not bit. So it denotes the predicate register. But when we denote the predicate register, we also denote whether we take the predicate register being true or the predicate register being false as what drives whether the instruction executes in our full predication scheme. So in effect, this is computing P and P bar at the same time and running them two different registers. And then we can use those separately down here. And interesting result here in ISCA 95, Scott Melke showed that you can, on average, let's say, remove 50% of your branches by using full predication. Now, full predication is not easy to build. Very few instruction sets have actually had full predication. Itanium was probably the closest to a real processor that was built that has almost full predication. It doesn't have quite full predication. The HP Plato instruction set, I think, actually had full predication. I think this is what Scott Melke was working with, or a derivative of that. So you can actually have instruction sets that people have thought about that have had full predication, but not all things are easy. So first thing, you need to add an extra register file for the predicates. You need to bypass those predicates. You need to compute them. There's some overheads involved, and we're going to talk a little bit more about that. OK, so let's take a look at our data path here and see where predicates fit into the data path. And we're going to focus actually just on the conditional move predicate or predication instruction here. We're not going to look at full predication just yet on the data path, but it follows a similar idea. OK, so what do we need to do? What do we need to add to our sort of boring MIPS-style 5-stage pipeline to add this instruction? OK, instruction comes in, moves down the pipe. Oh, this is interesting. I know, this is a really cool trick. Let's just, if this condition is not true, let's just kill the write back to the register file. It's brilliant. We just suppress the write back. We don't have to actually change our data path at all. We just sort of put an AND gate in here. And this AND gate depends on this condition. Simple. It's easy. Maybe this is what we should do. Looks simple. We just add an AND gate where the big X is, and life is done. OK, well, that looks good. Can we bypass this value? So can we have an instruction that directly follows this move 0, or this conditional move 0, and reads RD? Well, where are we changing RD, or not changing RD? Where are we making that decision? Well, in this pipeline, because we did it in the write-back stage, it doesn't happen until down here. Down here in our write-back stage, or this wire, that's the write-back wire, runs all the way back into the write enable on a register file. OK, well, that doesn't really help us a whole lot, especially if we're trying to bypass, and we're trying to bypass out of here, our ALU, back around. Because at this point, we haven't figured out any way to suppress this. So we don't actually we're not able to actually suppress that. So what do we think about this? So how do we go about doing this? So let's think about how to actually bypass out for this conditional move instruction. Because conditional move, it's just a simple comparison with 0. We should be able to do that in one cycle. We don't really have to wait to the end of the pipe to do that. And we want to be able to bypass it into a back-to-back instruction. OK, so how do we do that? Well, our bypassing doesn't work. What if we somehow pipe forward the original value and the new value? OK, so what do I mean by this? So this instruction is very interesting. is much more interesting than your standard like add instruction. So why is it interesting? Well, let's look at the semantics very closely here. Move 0 is going to write RS to RD, or it's going to write RD to RD. Now you say, why do I need to write RD to RD? Well, in the bypass path, when we provide this value around, back to our bypass registers or our forwarding logic here, or bypass muxes or forwarding logic, we need the old value of RD. So the traditional some sort of RISC pipeline here, we're only going to fetch our two sources, and we only write one location. So we're going to fetch RS or RT, and then we're going to write to RD. Now, all of a sudden, in this instruction, we need to read RS. Okay, we need to read that because we need to overwrite RD with RS if the condition's true. And we need to read the condition, RT. But aha! We may also need to read RD here. And this is because when we get to this stage here, and we want to use this bypass path to forward the value of what RD is going to be in the future, we need the original RD. So sort of to draw this a little bit more succinctly, because this is pretty important, we have if the register value of RT equals 0, we have R of RD gets RS. Okay, that's the easy one. We can count the registers here. One source, two sources, one destination. They're like simple. And what everyone always forgets is there's an else case here. And what does this else case say? Well, the else case is going to say register RD gets register RD. And you might say, well, our RD already had RD. That's true, but our bypassing or our forwarding logic didn't have that. So we need to actually read this RD. So that means we need to read 1, 2, 3, and we need to write one location. OK, so that's going to cause us some problems over here. Because all of a sudden, we had our register file, which had 2 read ports. And we need to now have 3 read ports. So we need to add an extra read port on our register file. And this could be expensive. So if we actually want to build predication, it's going to have some cost. We might, if we want to build predication and actually bypass something like a predicated conditional move, we're going to have to add another read port to our register file. And that actually has some costs. And this is especially costly if you look at something like a VLIW. So let's take, for example, a 3-way VLIW, something like the Tilera processor. So it's a 3-wide VLIW. Each of those ways, or each of those pipelines is going to read 2, if you don't have conditional move, we'll say. And it's going to write 1 value. So it's going to have 6 read ports and 3 write ports. So it's a 10-port register file. No, excuse me, it's a 9-port register file to begin with. And if all of a sudden we add something like conditional move here, and we need to add these extra read ports, we're going to go from a 9-port register file to a 12-port register file, where you have, let's think about this. You're going to have 3 write ports and 9 read ports. That's hard to do. It's hard to build these really heavily ported register files. OK, so to sum up here, our problems with full predication is that you need to add another port to the register file. You need to bypass the predicates. So what I mean by that is you're computing predicates, and you want to use it in the next instruction. So if we go back to this instruction sequence here, we compute these predicates, and we want to use it very carefully, or very, very quickly after it. We don't have to wait to the end of the pipeline for those predicates to be computed. So that effectively is going to make it so that we're going to have a predicate register file sitting somewhere here, and we're going to have bypassing around the predicate register file, or forwarding of the predicates to get the predicates there faster, or get the predicates to be used in the next instruction. And you're going to have to add extra pipeline registers to pipe forward the old value, because you might need to keep the old value in the bypass. And in fact, actually, a lot of times when people do these things, they actually always write the register file and just pipe forward both, and at the end make the decision, or along the way they make the decision to go into the bypass or not, but then sort of when the instruction finishes, that's when they make the decision. So we're going to actually have to add more pipeline registers to pipe forward the old value that was in this case, RD. OK, so now let's start talking about how to leverage different more techniques to get a lot of the performance that we received in an out-of-order superscalar, but in a VLIW processor setting. And we're going to break this sort of into two different things. Dynamic events, so things that happen in the processor that you can't necessarily or you can't really do anything about statically. It's really hard to do anything statically about it. You just don't know what's going to happen. Something like a interrupt or an exception happening. How can a compiler know where the exceptions are going to happen? It's just not really possible. And then we'll talk about speculation, which an out-of-order superscalar does. And a lot of the things that fall into this case, actually we can add things to classical VLIWs to get us closer to getting those performance improvements, or the instruction level parallelism improvements that you can get from speculation. And we're going to talk about sort of two different types of speculation today. We're going to talk about how to move or speculatively move instructions over branches. So in particular, this actually gets really interesting with loads moving across branches, because you have a load, and you want to move the load as early as possible. You want to pull the load up early into your program, so that if it misses in the cache, or it has to go out to main memory, you can hide the latency while you're doing other things. We're also going to talk about speculation of speculating that two memory addresses, one of a load, let's say one of a store, or you could also think about this as loads with loads and stores with stores, but we want to reorder those. Similarly, because we want to get sort of loads started early and stores started as late as possible, so we have enough time to do the computation we have when we do the scheduling. And remember, in VLIWs, we're doing all this scheduling statically in the compiler. And as you may recall, from an out-of-order superscalar perspective, when you try to do load-store speculation and try to reorder loads and stores dynamically in an out-of-order superscalar or some sort of superscalar processor, you need an extra structure to figure out when you made a mistake, when you reordered something that was not a valid reordering. And we're going to have to add that same structure into our VLIW processor, or a very similar structure. So let's start off by talking about what the compiler has to do, or how the compiler even starts to think about this speculation. So I wanted to introduce a topic here from compilers. And this is sort of an introduction to how we schedule for VLIW, the nitty-gritty of what the instruction scheduler or the back end of the compiler is going to be doing. So here we have two pieces of code. We have before code motion and after code motion. So what is code motion? Well, code motion is reordering of instructions in order to tolerate the latencies of the instructions or to do something good. So it might not just be tolerating latencies of instructions. It might also be reordering for alignment issues sometimes. Sometimes branches can only happen on certain alignments or the performance is better. So, but roughly, we're trying to reorder the code or do valid reorderings of the code. We can't just move a read after write dependence and move it someplace else. We can't say, instruction A reads the result of instruction B. We can't move A before B because it just wouldn't make any sense. But a lot of times, the compiler has some flexibility in what it can move around. OK, so let's look at this example case here. We have a gobbledygook of code. And what we're going to try to do here, well, two things to note. One, this branch at the end is dependent on register 16. Register 16, where does it get computed? Does it actually get computed anywhere in here? No. We're also saving away register 16. OK, so does register 16 get computed? Maybe not, but we probably want to give it as much time to be computed as possible. Some other things going on here. We have a load. OK, well, the load, what if the load cache misses? Well, this next instruction here is directly dependent on that load. So we probably want to give it as much time as possible to execute. So traditionally in code motion, you want to sort of push the loads up and push the stores down. Well, we're going to do this, if we were to push the loads as high up as possible and the stores down as possible, we're going to move a load and a store past each other. And the question comes up, what if this value and this value, these two addresses, are the same? Well, so let's assume that they're not, and let's assume the compiler can somehow prove they're not. So you should be able to do code motion here where we're going to rejumble all the instructions, and we're going to push the load up and push the store down, leave the branch at the end. So we've done some code motion. The next thing we're going to want to do is we're going to want to bundle or schedule the instructions. So when I say bundle, we're going to take several operations and pack them together into one VLIW instruction or one VLIW bundle. And we denote that here with these braces to say these execute parallel or at the same time. So first, you're going to sort of want to do scheduling. Then you're going to want to somehow bundle non-dependent instructions together. There's been a couple algorithms that have tried to do sort of scheduling, code motion scheduling and everything, and bundling together. Those don't always work out as well. So most of the VLIW compilers now will actually do the code motion and the scheduling first, and then they'll do the bundling at the end. OK, so let's look at our first technique here to get at instruction level parallelism, and our first type of speculation in a VLIW processors. So what's our challenge here? What's our problem? Well, our problem is the branches, or the presence of a branch, rather, is going to restrict the forms of code motion the compiler can do. So we have a branch. We have some code after the branch. If you have, let's say, an add instruction, that's pretty easy to move it before the branch. OK. How about an instruction which can take a fault or take an interrupt? Loads are a good example of one of those sorts of instructions. How is that possible? Well, a load can take a page miss or a page fault. It can try to access some value which is not mapped in by the operating system. So let's say we take this load and we move it above the branch. OK, that's not too bad. Now what happens if that load takes a trap or takes an interrupt that was never supposed to happen? In correct program sequence order, the branch was going to branch around the load. So the load was never going to execute. But all of a sudden, the load got moved up, and the load executes. And it takes an interrupt. Well, your program crashes. It takes either a segenv or a bus error if you're on like something like a Spark system, or you're basically taking a segmentation fault. Even though nothing went wrong, this branch was supposed to protect this load from never executing. So R1 here, let's say, just gets loaded with some bogus value if the branch is taken. And the compiler knew that, and the programmer knew that. But all of a sudden, the compiler decides to reorder things and has moved the load up now that, because it wanted to try to get more performance. This is something that you can do in your out-of-order superscalars also. The out-of-order superscalars are going to pull non-dependent loads up in the program and try to move them across branches. But in out-of-order superscalar, if you pull a load up and it does something wrong, it was speculative state. You just don't care about it. So we need some way to have loads that don't hurt the system. So it's a similar sort of idea, but we can't move this load above the branch because it might cause some sort of exception. So our solution to this is we're going to add special instructions, special versions of the instructions which don't take faults. So if the fault were to happen, it sort of remembers that the fault happened, but it doesn't actually interrupt the process. And this allows us to pull some of these instructions before branches, or reorder, perform code motion statically at compile time. OK, so let's take a look at this example here. How would we go about doing this? OK, so we're going to move the load up. So let's say we move the load as high as possible. We move it above these two instructions, instruction 1, instruction 2 here. And what do we need to do? Well, if you note, we don't have the word load here anymore. We have load.s. So this is a speculative load, which has different semantics. This load.s never causes an exception, even if it has like a page fault or a null pointer exception or unaligned memory reference or anything like that. It's not going to actually take that fault. Instead, it's just going to sort of remember that. And this is typically done if you look at something like Itanium, which is this is a sort of code sequence out of Itanium processors. In Itanium, what they're going to do is they're going to the destination of the load, in this case R1, is going to be set with a poison bit. Itanium, this is actually called not a number. And what that means is the destination register of the load is marked as not there, or that it's not a thing or not a number. And what's important about this is when you go to use that value, that's when you take the exception. So let's take a look at an example of this. What we do is down here, where the load originally was, we put in a check speculative instruction. And it uses R1 here. So what this is going to do is it's going to check the value of R1. And if R1 took a trap or exception, and there was some problem with it, we can jump to fix-up code. So there'll be some other piece of code somewhere else we can branch to. And that fix-up code is going to re-execute the load and make sure everything is OK. And then jump back to the use. So it's speculation. We try to prove and we try to make sure that the common case, when we pull this load up, nothing bad is going to happen. But we put a check in just to make sure that this is the case. One other thing I wanted to point out here is these poison bits, or these not a numbers, they propagate. So why is this important? Well, what that means is, actually, I want to correct something you said a little bit here. If you try to use R1 somewhere else before you do a check, the not a number propagates. It doesn't take a trap. It only takes a trap, or only jumps to fix-up code when you go to actually do the use, or when you have a special check instruction, or there's another load you can put there that'll re-execute the load if the original load didn't work, a non-speculative load to the same value. OK, so why is this propagation of not a numbers important? Well, this allows you to pull code down here up and above this branch also. So we can pull the load up, we can pull dependent instructions up, and then just as long as we do the check at some point, and check to make sure that the load didn't take an exception or not a problem, we can basically speculate that the load is fine. We can speculate that the instructions dependent on the load are going to be fine. But if any of the dependent instructions on the load are not fine, that we've also speculated, when we go to, at some point in our code, we need to introduce this check instruction here, which sees if this value is not a number. So if it propagates all the way through your code, you have a load, a add, a sub, which all reads and writes, let's say, register, or somehow reads from register 1, and there's sort of a dependency tree from register 1 through that code sequence. At some point, you want to check after the branch has actually happened whether everything's OK. And because it all propagates, you can basically do work early and then check later. And when you do the check later, you can say, oh, I get it, everything's OK, and it has a value in it. If it has not a number in it, or it has this poison bit set, and it's propagated all the way through, at that point, and you can jump to fix-up code, which you can re-execute the load and all of the code you've pulled up, all that speculative code. And that's why you need fix-up code and not just re-execution of the load. Because the fix-up code might have to re-execute more than just the load. It might have to execute the load and all the other code you pulled up in front of the branch. OK, so let's move on to another type of speculation. And this is data speculation. So in data speculation, our problem here is we have memory hazards that are going to limit our scheduling, especially if we have to do all this scheduling statically. So if you're conservative in your compiler and you can't prove anything about the different addresses, all of a sudden what you have is every single load is dependent on every single other load, and every single store is dependent on every single other store. Now you might say, why are loads dependent on other loads? Well, though loads and loads you might be able to reorder pretty easily, you have to worry a little bit about if one takes a trap before the other. I guess we could have already talked about how to solve that problem. But once you reorder a load in a store, then you start to have problems. Or reorder a store in a store, or anything with a store, then you start to have problems because all of a sudden you have some state that changed in your memory system that you have to make sure that in original program order, the later instructions actually pick up the result of that. So later loads or stores somehow honor the results of that. So it's really sort of focused on moving loads and past stores. So what's our solution? Well, our solution is to add some hardware check to guarantee that the pointers or the two memory addresses, when you do the reordering of a load in a store or a store in a store, that these addresses are not the same. And this is actually the same thing that we did in our load store queue or our load store memory disambiguation that we talked about in out-of-order processors. So it's the same sort of thing going on here. But we need to actually change the instruction set to handle this in a VLIW setting versus in the superscale where it was all microarchitectural issues, sort of below the instruction set that no one ever had to look at. OK, so let's look at how to do this. We have a code sequence here, some instructions, a store, and then a load. Compiler can't prove anything about these stores and this load. But in an out-of-order superscalar, it could guess or speculate that the load and the store don't share the same address. And if they did, it can basically roll back the code and re-execute the load. And we want to emulate something like this, but doing it all statically with the compiler. OK, so how do we do this? Well, this is something else that Itanium added and was also talked about in previous research VLIW processors or explicitly parallel instruction set processors. What you're going to do here is you're going to move the load up above the store. And this is basically speculating that the load and the stores don't hit the same address. And much the same way that we when we reordered loads above stores in an out-of-order superscalar, added the load address to a load store queue and a memory disambiguation queue, we're going to do the same sort of thing here. That when we move this load up, we're going to have a different instruction here of load and add. So what this is going to do is it's going to add, it's going to do the load and add the address to a special table, which we're going to call the address, what does ALAT stand for? Advanced Load Address Table. The ALAT is what Itanium calls this. So it's a structure that's a associative structure where you can put addresses in it and then check other addresses from other instructions against it. And if you get a hit or something like that, you know that something bad happened. And you can re-execute. So we're going to see here that we're going to have a load, which is going to get the load out in the memory system. We can overlap the time in the memory system with executing other instructions. We have a store here. Now, the store is going to take the address of itself, and we've changed the instruction set here because we added these two new instructions here and changed the semantics of a store. And it's going to check in the ALAT, or the Advanced Load Address Table, to see if the the address the store is happening to is already there. And if it is, it's going to change the table somehow. And we'll talk about that in a second of what exactly happens. But roughly, it's going to take this address out of the table. And then when this load check happens here, this checks to see if the address is still in this table. And if it's been bumped out of the table, it jumps to fix-up code, which is basically going to re-execute the load, or re-execute the load and all the dependent instructions on the load. So we can effectively do data speculation, but all in software. But this is going to require us to have an associative hardware block or some sort of content addressable memory, a CAM, that we need to add that all load addresses and all store addresses are passed across. And this is similar to how we had our memory disambiguation queue in our out-of-order superscalar. OK, so let's look at the ALAT, the Advanced Load Address Table. OK, so what do we have in here? Well, three things. We store the address. We store the size. This is important so we know, is it word, double word, half word, byte, sort of thing when we go to do matching. And when a load.a happens, it adds one into this table. And we denote the register number that is the target of this also. It's kind of useful to know when we go to do the check. This is to match up to make sure that the same load is the same load from before, and we can effectively remove the address from the table when we do the check. OK, so we added an address. OK, we're running along. And no, we execute stores, but the stores don't hit on that address. So when a store executes, what is it going to do? Well, it looks in this table and cams or does a comparison against all of the addresses with size matching and everything against this table. And if it's in the table, it removes it from the table. So by the time that the check or the load check happens, that address is not in the table then. So when the load check happens, it's going to look in here, this table again, and say, oh, I'm not in the table anymore. This address is not in the table anymore. So at that point, you can know, let's go re-execute that load. But if it's still in the table, that means no stores bumped it out of the table. So no stores in the interleaving time bumped it out. So the speculative load was fine. So we've effectively done what out-of-order superscalars can do. We can move now loads above stores. And through a change to our instruction set architecture, by adding these special check and load check and check instructions, and by changing the semantics of load and adding a load add or load a instruction here, we can change. We can have data speculation into our program. OK. couple other things that are fun to add to classical VLIWs to improve performance. I just kind of want to breeze through these next two ones a little bit faster here. First one, multi-way branches. So problem, you have a VLIW architecture or a very long instruction word architecture. And if you have, let's say, 10 things in one instruction or 10 operations in one instruction or 10 operations in one bundle, but you have sort of short branches, or maybe you have multiple branch decisions happening. You want to have sort of a branch every 3 instructions. Well, you have lots of wasted slots. If you can't somehow have one instruction branch multiple directions, now you might say, branching multiple directions, that's a really weird idea. How do you have an instruction go multiple ways? I thought branches could go 1 of 2 places. They could either fall through or go someplace else. Well, we can actually change the instruction set to have a branch that can go multiple directions. So let's look at this with a full predication example here. So we have 2 bundles of code here. This first one here is 3 instructions in it, and these are all executing in parallel. And what this is going to do is it's going to do 3 different compares. So this is similar to this is our full predication example here. It's going to write to these predicate registers with the logical positive and logical negative sort of versions of the predicate comparison. OK, so that sort of stages us to do 3 different branch comparisons. And then down here, we have 3 branches that all branch based on this predicate, or these different predicates that we already staged or set up here. And they can branch to 3 different places, label 1, label 2, and label 3. And there's also could be fall-through code if none of the branches are taken. And one little wriggle here that you have to sort of figure out the semantics. And I should say Itanium actually supports this, so you can buy real chips with this in it. If you have 3 branches together, you need to somehow order these branches. Because let's say they all say taken. Well, or they all resolve to actually being taken. Well, which one do you take? Because you could branch to all 3 different places, and we want deterministic execution. So typically, when you have an instruction set like this of multi-way branching, you define some order. Maybe the first one has priority over the second one, which has priority over the third one, et cetera. OK, so let's talk about some of the other things that were on our list of limiters to instruction level parallelism, and ask ourselves, are these things which we can solve very easily? Well, things start to get harder pretty fast here. Like I said, dynamic events, they're basically things the compiler has no way of reacting to. Now, the instruction set might be able to react to it. You can add things into the instruction set. You can maybe take a branch dependent on a dynamic event. But let's look at some dynamic events. First dynamic event here, cache miss. Well, it's really hard for a compiler, just all things being equal, knowing whether a load is going to take a cache miss or not. It might have some guesses, and that could influence the code. But actually doing something about it. If you think about what an out-of-order superscalar does, if you take a cache miss, it'll reschedule the code around the cache miss. It'll take the non-dependent instructions, the instructions that are not dependent on the load, and pull those up and try to execute those. But if the load hits in the cache, you want a totally different schedule. You want to actually try to start executing the instructions that are dependent on that load as soon as possible. So an out-of-order superscalar has dynamic means to be able to do this. It has dynamic instruction execution. But our VLIW processor, which is statically scheduled, can't really do this. So what's some techniques to go about after this? One thing is something called informing loads. As far as I know, this actually has not been built in any hardware, but it's been proposed, at least in the computer architecture academic circles or in the computer architecture literature. And informing loads was actually come up, the original paper about this is by one of our faculty members, or one of our faculty members here at Princeton, Margaret Maranozzi wrote she's one of the authors of this paper. But the basic idea is that if you have a load that misses in the cache, you can not execute subsequent instructions. Else, you can or there's actually no else there. If the load misses in the cache, you just don't execute some subsequent instructions. You can basically nullify those instructions. And this allows you to change the code sequence dependent on whether the load hits in the cache or whether it misses in the cache. And this was done with Todd Mowry, Margaret Maranozzi, Professor Margaret Maranozzi, and Professor Todd Mowry, I think both when they were graduate students. And Mark Horowitz from Stanford was on this paper. I think a couple, I'm trying to remember who was the last author, the professor on this work. Another option is something that the Elbrus processor people did. So you've probably never heard of this processor. It was something that was built in the, well, I actually don't know if it was ever finished. I think they had a prototype of it. Sort of in the Soviet Russia day, right when the Soviet Union was kind of breaking down. This was the design house in Soviet Russia, which made all of these sort of military processors. They later went off, and that same design team was going to go build some commercial processors after the fall of the Soviet Union. So they went and they went to go build this processor, and it's a VLIW processor. It's some very long instruction word processor, and they had an instruction in there which tried to solve this dynamic event problem around cache misses. So what it said is, if an instruction misses in the cache, go execute a different piece of code with a different schedule than if the instruction, if a load hit in the cache. So you could effectively have two different code sequences. The compiler could actually generate two different code sequences, and you can get back to a lot of the performance and get back to almost exactly what an out-of-order superscalar could do. Now, this processor never really made it commercially, and later the company went under and was bought. I actually don't know if the assets were bought by Intel, but at least all the people who worked at this company now work at Intel effectively. So they still live in Russia. So that's a funny story there that, yeah, it didn't work out from a commercial perspective, but they had some cool ideas in there that you could actually try to schedule around schedule around cache misses. OK, so some other things. Branch mispredicts. Well, we already talked about one technique here. We can talk about you can add predication. But that doesn't help if you have big pieces of code, big code sequences, and big code hammocks. You can't necessarily predicate your entire program. So what do you do instead? Well, one solution that people have come up with for this, and this is a hard one to deal with here, is you can add branch delay slots. So you have a VLIW processor. Let's say it's 3 wide, and you add branch delay slots in your instruction set, and then you use predication in the branch delay slots. And what this allows you to do is it effectively lets you mask some of the branch mispredict penalty and change the code schedule a little bit dependent on the prediction. Or change it actually completely based on what the branch is. And the way this works is in the delay slots, you use the same predicate that the branch is branching on. So the branch is branching on, let's say, if A equals B. Well, you use that same thing in the predication, and effectively you can reschedule the code differently depending on whether the branch is taken or not taken. And because you're putting it in the delay slot, you can sort of get around some of the problems here of whether it's taken the one direction or taken the other direction, no matter which way the mispredict happens, or whether the branches can be predicted correctly or not. And what we're doing is basically putting code in the delay slots that will always execute, but it can be predicated, and you can effectively pull code up from the two destinations of the two branches. So it's sort of a way to get around branch mispredict penalties here. This is actually done in a research processor that was built at MIT. And I think this is probably also done in some of the other HP processors. But the MIT processor, at least, was called the M machine out of Bill Daly's group. He's now at Stanford, but I think the M machine was sort of built right when he was moving from MIT to Stanford. But they had, I think, 3 delay slots, and they were 3 wide, and they could predicate the instructions in the delay slots. So last thing is exceptions. So you take an exception, and you want to schedule different code. And these are like impossible to predict. The compiler has no way to try to predict this. But this is hard on a superscalar also. When you have a traditional superscalar and an exception happens, they usually end up flushing the pipe anyway. So, and it doesn't happen that often. It probably doesn't hurt your performance that much. So no one's going to lose too much sleep over this one. So I briefly wanted to say something about how to build really wide VLIWs. As we start to go to wider and wider VLIWs, lots of instructions execute at the same time, you have to start thinking about what does the register file in the bypass network look like. So in this drawing here, we actually have a figure of the C64000 series processors. So these are TI DSPs, this is sort of the flagship DSP processors. And this is a sort of block level diagram of what they have. And what they actually have is they've divided the machine into local register files when they bypass inside of what's called a cluster. So it's a clustered VLIW. It's similar to how we have clustered superscalars, which also divide the register file. But this is an architectural, a big A architectural or ISA level architecture splitting or dividing going on here. So in something like the C64000, they actually have 4 instructions per cluster, so they're executing 8 instructions at the same time. And you can bypass values between these 4 ALUs within them, or you can bypass within these. But if you want to sort of take a value from here and move it to there, you have a very low bandwidth sort of bypass path here, and it takes an instruction. You effectively have to have a move instruction to move between the 2 different clusters. So there's a lower bandwidth between the clusters and a higher latency between the clusters, but inside of a cluster it's very fast. And what's important to know here is these are not 2 processors. These are all executing 1 instruction at the same time. So it's an 8 wide instruction executing on these 8 different ALUs. And this is used in as I said, the TI high-end DSPs. Also it's used in HP's and ST Micro's LX processor. And this is probably a processor you never heard about, but this was actually what Josh Fisher went on to go do at HP Labs after Multiflow. So this is after sort of a lot of the original VLIW work. Same person went and built this LX processor. And this is sort of a joint collaboration between ST Micro and HP, and this shows up in printers today. So it's not something you're going to really have. The LX processor is probably something you're not going to have in your desktop machine. OK, so I wanted to just briefly give a case study here of one of the more interesting modern-day VLIW architectures, or probably the most famous and possibly also the most infamous VLIW processor out there. This is the Intel Itanium, also known as the Intel IA64, or what's known as an EPIC processor, explicitly parallel instruction computing architecture. And a lot of this work actually was done in collaboration between Intel and HP. HTP uses these a lot in their big servers. They're sort of big mainframe, well, not quite mainframes, but big, heavy, big iron computers. And Intel was trying to use this to effectively kill all of the other workstation vendors. And this was going to be their 64-bit solution to computing. So it's a modern, non-classical VLIW. And this was going to be Intel's chosen ISA. They were going to deprecate x86 and choose IA64 as the 64-bit ISA. And as we now know, going a few years forward after the creation of all this stuff, that didn't really happen. Intel went and did this. It built a bunch of processors with this instruction set. You can still buy processors with this instruction set, but it never got as good of acceptance as the competitor. The competitor is what at the time was called AMD 64, which is a 64-bit extension to what people already had. And that's what people ended up wanting. It's just a 64-bit extension to what we already had versus something totally different. OK, so a couple features here. It's an object code compatible VLIW. So it's not quite a VLIW in a classical sense. It's object code compatible, which means different generations, different microarchitectures of this VLIW can have the same instruction code and the same binaries, and you don't have to recompile. And how they did this is effectively, as I alluded to before, they had the ability to have parallelism straddle across instruction bundles. And they had this notion of groups, which we'll talk about in a second. So first few implementations of this, Merced was the first Intel Itanium implementation. It's kind of like the 8086 for x86. But Merced, as lots of things, you'll realize if you look at Intel code words and Intel code names, named after a river. Intel likes to name their things after either rivers or places. I think this has something to do with you can't trademark a place name, so they just sort of get around that and make sure they don't have any trademark issues by choosing place names for all their code names. One of the big problems here, it was supposed to ship in 1997. First customer shipment, not until 2001. It's a 4-year miss. And superscalars and other things had sort of had caught up on it at that time. And it was supposed to be faster and better than everything else. And the first one was not very good. It had low clock rates and was not as high performance as it was supposed to be. And sort of the x86 side of Intel's business line actually had almost the same performance as the first Itanium, and then very quickly surpassed the first Itanium. So their high-end processor wasn't actually very high-end. Couple other things here. So McKinley was the second implementation, shipped pretty quickly after that. This was much better implementation, but it's still hard to do. But we're still building these things. So in 2011 at ISSCC, Intel introduced the Polson processor. Big machine here. 8 cores and 32 nanometer. Lots and lots of RAM. We'll look at that. Yeah, so 32 megabytes of shared L3 cache. Big processor. 544 square millimeters in 32 nanometer. So at the time this came out, this was the biggest processor ever built. Most number of transistors, so over 3 billion transistors, or at least the biggest commercial thing. Intel might have had a research prototype, I think, that might have had more transistors than this. I think their multi-core processor, or their, what do they call it, the SCC, their single-chip cloud computer might have had more, but I don't actually know the transistor count. But from a commercial processor perspective, huge chip. But they're selling it into extremely expensive sort of sockets. They're selling this chip for a premium. It's going into big mainframes. That was not where this was originally destined for. It was destined for both big mainframes and workstations. But now this is sort of the, in 2012, standing here now, this is not used in lots of other places except for sort of bigger hardware mainframe sort of things. So a few interesting things here is the cores are multi-threaded, and you can execute 6 instructions, or you can fetch 6 instructions per cycle, and you can execute up to 12 instructions per cycle per core, and then there's 8 cores. So this is a beast of a machine, very high performance computer. Okay, so let's dive into some of the details here of Itanium. Itanium has a 128-bit instruction bundle. And inside of there, you can fit the 3 operations. And then there's some what are called template bits, which sort of says what is in the instruction bundle. So it's not actually a fixed format bundle. These instruction boundaries can move around a little bit. And they did that so you can sort of mix in something like a immediate instruction with an instruction which doesn't have immediate and get more space in the bundle for the immediate bits. So you can have, or branch offset or something like that. These template bits also describe how a particular bundle relates to other bundles around it. So sometimes these are called begin and end bits or start and stop bits. So it says the number of instructions which can execute explicitly in parallel. And the machine doesn't necessarily have to execute these in parallel. So for instance, if you say 20 instructions can execute, or 20 operations can execute in parallel, but your machine's only 2 wide, or they build a 2 wide implementation of Itanium or IA64, you just are going to execute 2 wide for 10 cycles or something like that. But what's really cool here is the compiler is able, just like all the other VLIWs, to express the parallelism to the machine explicitly. Some interesting things about the registers. Because this is a VLIW processor, and because you're going to have to do code scheduling like what we saw in last class, and that increases the general purpose register pressure. You don't have a register renamer. So you can't go and use different names for things, and the hardware is not going to rename things for you. So instead, the compiler and the software is going to have to do the renaming. So they had 128 general purpose registers and another 128 floating point registers. And they also had these predicate registers. So they're not quite full predication, but they're pretty close to full predication. So you can have bits that say whether later instructions are going to execute or not, and you have to compute that into a little register file. So they had a predicate register file that you have to bypass. So that's sort of interesting to see. And then they had a really interesting feature here, which is called rotating register file. And let's talk about what a rotating register file is. So the problem this is trying to solve is in a code sequence as we saw in last lecture. If you have a very long instruction word scheduled piece of code, and you want to get good performance, you're going to have to unroll the loop, and then you have to software pipeline the loop. But when you do this, this is going to increase your register pressure or increase your register names, how many register names you need to use. And as we saw, you're going to have to add extra special code in the prologue and the epilogue, which are different than the main loop body. So how do you solve this in one fell swoop? Well, you add a subset of your register space, which will sort of statically rename itself every loop iteration. So it'll slightly change the loop iteration or change the naming of the registers. And what this looks like is if you go to access, let's say, register R1, there's a register, sort of a architectural enabled register called the rotating register base, or RRB here, which has a value that gets added to this. And it's modulo arithmetic, so it rolls around at the end. And that points to different locations in the physical register file. Oh, this is pretty cool. So what we're going to do is every single time we come to a new loop iteration, we are going to change the RRB, and it's going to point to a different set of registers. And we can actually effectively software pipeline just by using this one feature. So here we have the same code sequence we had from last lecture. So it was the previous code example. And if we recall, when we unrolled all of this, what we ended up with was a load, an add, a store. We'll talk about this in a second. This was kind of the key thing we were trying to execute. And if we have to unroll this, we basically had to unroll the code and then look at the dependencies. So let's look at the dependencies here. Well, dependencies that we're going to have is this load writes F1, or the floating point register F1 here. And we know that this is actually going to want to get read let's say the latency on this is 1, 2, 3 cycles, and it doesn't get read till here. Likewise, this add here computes P10, and the add, let's say, is a floating point add. It has some long latency. And down here is when it's ready into the store. So on something like a Itanium with a rotating register file, we don't actually generate all this code. Instead, we generate one instruction, this, which is going to take care of our epilogue, our prologue, our epilogue, and the main loop. And what we're going to do is we encode the distance in register numbers between these two values here. So what this means is if this writes F1 and 1, 2, 3 loop iterations in the future want to read that value, we encode that here with a register number that is that number off. And then likewise here, so this would be F1 to F4 because it's off by 3. And here, this writes F5. And we know this wants to be read 1, 2, 3, 4 later. So we encode it with a register number that's 4 into the future. And now we're going to talk about this instruction here. So what this is going to do is it's going to change the rotating register base number, or the RRB, and it's going to bump it by 1. So we can basically just keep branching to itself here. And each time we do it, all the registers are going to change names. So by the time this is ready, or by the time the load is ready here, these other values will have sort of caught up with it, where the physical register that they're actually going to look at will now point to the correct location. So we can effectively encode into one instruction here all of this, including the prologue and the epilogue, using this rotating register file. OK, so last slide of today. Why do I think Itanium, I think we can pretty confidently say, failed? I actually don't think it was a lot of the ideas. I think a lot of it had to do with the implementation. So first off, if you tie the hands of the microarchitect, they're going to scream. So IA64 added a lot of architectural, big A architecture, or ISA level features in order to get a lot of the speculative parallelism. And a lot of that stuff was implemented and talked about, but never actually built in real processor. So people didn't go through the effort until basically the first Itanium to try to implement some of these things. And they didn't all mix well together. And they added a lot of state, and they added a lot of complexity to the processor. So we have ALAT, full predication, or almost full predication, rotating register files, to name a few. This really complex bundling sequence, that's probably one of the hardest to decode instruction sets in the world. Very, very challenging. And this was a big challenge. And it tied the hands of the microarchitect. And the microarchitect couldn't make decisions. So a good example of this, and a funny story here, is that after the DEC Alpha employees, Digital Equipment Corporation employees, left DEC and were sort of assumed into a part of Intel, that same team that used to build out-of-order alpha processors went on to go build sort of the next generation of an Itanium processor. And what they said is they went in to go look at the Itanium processor, and they're like, wow, this is really complicated. It took them much more complicated than alpha. And then they said, oh, well, we could probably do better if we just built an out-of-order superscalar, took apart all of the instructions, took apart all the dependencies, poured that data into what was effectively an alpha out-of-order superscalar core, and then execute it. And what was funny is if you go look at this is like all the people, you can sit there and just bang your head because you did all of this work and added all of this architectural state to allow the compiler to do all this work. And then they just wanted to undo it all. I mean, they did this because they wanted performance, but then they wanted to undo all of the sort of state and all of this hard work the compiler did and just redo it all dynamically because they thought they could get better performance. They probably could have. It probably was a good idea, but what's kind of funny there is you built an instruction set that had one microarchitecture in mind, basically an in-order architecture, and then all of a sudden people are thinking about building out-of-order variants of it. And it sort of throws everything you had before away, or all these notions sort of went away. So it's just a funny story there that people tried to build out-of-order versions. They ultimately did not end up doing that. That same team decided it was basically too hard, mostly due to predicate registers and sort of how to bypass predicate registers of out-of-order things. And I think they ultimately ended up not doing that, or they definitely ended up not doing that. And that's what's sort of known now as the Wachusett or excuse me, not the Wachusett. It's known as the Tukwila processor from Intel. Other couple of problems here. First implementation at a very low clock rate, so your first one out the gate just was not very good. This sort of hurt, and it's hard to build these things. They're wide. The speed demons versus the sort of brainiacs. This is this question of, do you want to go wide or do you want to go long and narrow? Long and narrow was doing okay at the time. Big code size bloat. Fundamentally did not solve all of the dynamic scheduling problems that out-of-order superscalar could get at. So for instance, branching or changing your instruction schedule based on whether a load hit or missed in the cache, they couldn't do. Big compiler complexity, you needed profiling and not everyone wanted to profile. There was also just not that much in static instruction level parallelism in all programs, so the compiler couldn't necessarily find all the parallelism or it wasn't there statically. And if you're going for a compiler-only approach, you need to be able to do that. And then this is what really killed it here is the people did go build these more complex out-of-order superscalars. So at the time, there was this big discussion, can we build more complex out-of-order superscalars? And people said, no, those are too hard. They're too hard to build. They cost too much. We don't know how to solve all these problems. So instead, we'll try to build something simpler and push a lot of complexity into the compiler. Well, there was money behind this question. So people went and did build these complex out-of-order superscalars. And that's what we're basically still using today in our sort of desktop processors. We have out-of-order superscalars today. And then finally, the last big one here, AMD 64 happened. What is AMD 64? Well, it's a 64-bit extension to x86. AMD originally did this. Intel, after sort of dragging their feet for a couple years on this, finally decided, oh, we're gonna use that because people wanted this. People wanted code compatibility with the ability to do 64-bit sort of wider, both arithmetic operations and wider addressing, so more amounts of memory. And 64 bits is a lot of memory. So AMD originally came up with this. This is now known as, I believe, EMT64 or Intel 64, not to be confused with IA64. That's what Intel calls now the 64-bit extension to x86. And now Intel's building those processors too. So everyone has sort of jumped on that. And Intel's kind of de-emphasized Itanium now in the Itanium instruction set. And instead, we're basically sticking with IA64 in this instruction, or IA32, the 32-bit x86 with extensions to 64-bit, and that's taken over the workstation market. And what's kind of funny here is this processor was really designed to kill or unify all of the workstation vendors together under one processor that was going to beat them all. And it did its goal to some extent. Because this processor was coming around, either companies went out of business or they jumped on the IA64 bandwagon and decided they were going to take that on. But what replaced all of the different little variants of processors that were in workstations. So SPARC, PA RISC for HP, SGI's sort of MIPS processors, I already say SPARC, yeah, all these sort of other different things, and Power by IBM. Power's still around, but a lot of the other ones sort of died through attrition or moved on to were supposed to move on to IA64, but IA64 did not end up winning this. Instead, we replaced it with 64-bit x86 processors. So it sort of did its job. It killed the workstation processors, but replaced it with not itself. It ended up replacing it with something else. Anyway, we're gonna stop here for today, and we'll talk more next lecture. Why is branch prediction important? So let's talk a little bit about motivation. Then we're going to move on and start talking about branch prediction and the two things we need to predict when we're predicting branches. And the top thing that jumps to mind is the branch taken or not, the outcome of the branch. But that's only half of the story. And today we're also going to talk about figuring out where you actually go when you take a branch. And when I say branch, we're going to loosely put all forms of control flow into this. So it's not just a branch, it's a branch, a jump. You might even think about trying to put something like a interrupt, because that changes your control flow of your program, but most people try not to predict their interrupts. It's hypothetically possible. But let's start off by talking about why branch prediction and what is the big motivation for branch prediction. So as I said, longer pipelines and more complex pipelines require us to have relatively good accuracy trying to figure out when we take a branch or when we don't take a branch. So here we have our in order fetch, out of order issue, out of order execute, in order commit pipeline. And a couple things you should note here is, we added this extra stage out here. We added this issue stage. But we also added this issue queue or instruction buffer here, or issue window, depending on what book you read, in the front here. Well, instructions pile up into this. And if you don't actually figure out if the branch is taken or not, let's say until somewhere here in the execute stage, then you're going to have more basically instructions you need to kill when you take a branch mispredict. So when you start to go to these out-of-order processors, when you sort of have this seemingly short pipeline, seemingly easy pipeline, more instructions can get sort of queued up into some of these structures, especially if you have a queue. So this effectively lengthens the front of your pipeline and makes it such that if you mispredict or you fetch the wrong instructions relatively often, you're just going to be out in the weeds. You're going to be killing lots of instructions and having done a lot of extra work that you didn't really want to do. So also, if you wait all the way to the end of the pipe in sort of these out-of-order processors to resolve your branch, that's also going to make life even worse here, because that makes your mispredict penalty even longer. Most people don't actually do that. I mean, you might say, oh, I don't want to actually kill instructions until I know the branch commits. And that was sort of our simplistic example we had when we were talking about these out-of-order processors, is we waited all the way to the end of the pipe and then sort of cleaned out things. You can wait for it to go to the end of the pipe to actually fully clean out things, but you're going to want to redirect the front of the pipe, or redirect the fetch or the PC in the front of the pipe as quickly as possible, because you just don't want to be fetching off into the weeds, because then you're just wasting cycles. Here we have, going back to our super pipelining lecture that we had before, and we look at for some real processors, the Pentium 3 and the Pentium 4, what their branch mispredict penalty is. And in this Pentium 4 here, you have 20 odd cycles here of branch mispredict penalty. That can be pretty painful if you take branch mispredicts quite often, because you're going to be taking branches, and the branch penalty is going to be quite high if you don't have the correct subsequent instructions after you. Now, we talked about some techniques. You can just stall and wait, so you don't actually predict the branch. But then, if you have to wait for every branch to get to, let's say, the 20th stage of the pipe before you go and fetch the subsequent instruction, that's pretty painful. So we had talked about speculating the next PC, or the PC plus 4, we'll say in a MIPS-style architecture, or an architecture where each instruction is 32 bits long. But that doesn't really help you when you're trying to predict, or when it doesn't really help you if you have high probability you think the branch is going to be taken, or you think the control flow is going to be taken. So you need to start thinking about how to actually deal with that in a pipeline. And up to this point, we've only talked about speculating the fall-through case. We talked briefly about speculating the non-fall-through case, but we didn't say how you could possibly do that. And today we're going to talk about what the hardware is to do that. Also making life worse is if you start to go wide, this hurts also. So if we start to go wide here, let's say we have a dual issue processor, but if you go wide here, when you go to kill instructions, you're killing twice as many instructions in flight in the pipe if you take a branch the wrong direction or mispredict a branch. So showing that from our pipeline diagram perspective here. This is just recapping. We had seen this in a previous lecture. But here we have a fetch for this branch. And we're fetching 2 instructions per cycle here. So even if a relatively short pipeline, you end up with 1, 2, 3, 4, 5, 6, 7 dead instructions on a mispredict. So what this really comes down to here is you have the pipeline width, or approximately how much stuff you end up getting killed is the pipeline width multiplied by the branch penalty. So it's width times length before you can resolve the branch. And if you can shorten the time it takes you to resolve the branch, that's good. Or if you can make the processor narrower, that may be good. It's good from fewer instructions being killed, but we like to execute multiple instructions at a time because that improves our performance. So this is really the motivation for thinking about trying to put something useful in this time here, and also trying to reduce the probability that we start fetching incorrect instructions at all. So this brings us to some techniques. So we're going to start off by talking about prediction and how we can use branch prediction to determine 2 things, the outcome and the target address. So branch prediction. Everyone always thinks that it means this first thing. That's not what it means. It encompasses both things. You have to predict the outcome. So that's whether the branch is taken or not taken. And you also want to predict the target address. Now, if you think about that, the first one sounds relatively trivial. I can just sort of pull numbers out, or I could pull something out of a hat. Taken, not taken, just sort of choose randomly. It's going to do OK, probably. I could probably try to correlate it somehow, use some heuristics. The second part here, I have to get the number exact. So if I choose at random for my branch prediction outcome, I'm going to get it 50% right. Or if I just always choose, I don't know, we'll say we just always choose not taken or something like that, we're probably going to do pretty good. But getting the actual destination correct, you have to be exact. You have to choose a number out of, let's say if you have a 32-bit instruction pointer, you have to choose some random number out of 2 to the 32 locations and get it right all the time with high accuracy. So we'll spend some time about this, talking about this and some strategies to getting the prediction target and predicting our branch target and our jump target correct. But you have to think about both of them is all I really wanted to get across here. OK, so this is something is a little bit more review from something we had talked about in lecture, I think, 2. We talked a little bit about figuring out where we can resolve a branch. So here's a little bit longer pipe. 1, 2, 3, 4, 5, 6 stages. It's not quite our 5-stage pipe. I put a issue stage in here. And let's look to see where everything gets known. So we know that our target address for branches, jumps, and jump and link will likely be known here. But that's not really helpful unless we know which way the branch is, or rather, unless we know which way the branch is going or the branch outcome. Because even if we know, at least for jumps and jump and links, we know the outcome. It's taken. But for conditional branches, we may not know that until somewhere over here. So we can't necessarily use that information until later in the pipe for branches to do something useful in the naive approach. In the execute stage, we know the branch outcome. We talked about a trick in MIPS, at least, where we could try to pull that forward a stage into our decode stage by having some sort of special comparator on the output of a register file, comparing it with 0. But that doesn't work for all branch types. So if you have something like a branch equals, where you're actually trying to compare two real registers, you have to wait for the full bypass. Doing a 32-bit compare is sort of the equivalent of doing a full 32-bit subtract. You're not really going to know that until the end of the execute stage. That trick doesn't really hold water. It holds water for comparing with 0. You might even be able to do it if you have lots of extra time in your decode stage. But let's assume that you don't. Also, target addresses for jump registers and jump and link register. Jump registers, jump and link register, you need to read the actual address that you're going to out of a register somewhere. So this, you can't even have a chance of trying to predict it out here or the destination. It's pretty hard because, I don't know, it's somewhere in the bypass. You just compute some value, then you jump through it. So we don't, at least out in here, by the time we're done here, we have one of two addresses. We have both of the addresses that the branch could potentially go to. It could go to either the fall-through address or the branch target. And we know that's sort of at the end of the decode stage. For jump and link registers and jump registers, we don't even have that information. It's not encoded in the instruction anywhere. It's encoded in a register. So we need to go fetch something from the register. We might have to go through the bypass network. So we're going to have to wait. So let's look at some techniques to deal with outcome prediction for branches. And we're going to look at this mostly, first of all, in the static domain. So things that are not trying to watch the dynamic instruction sequence, but instead can basically statically analyze the instruction sequence and with some high probability, we'll say, try to predict the location. The first technique is actually not a prediction at all. The first technique, we had talked about this a few lectures ago, or we talked about this in lecture 2, adding delay slots. So instead of, I don't know, having that time just be dead cycles when we're trying to resolve the branch, let's say we put if we don't resolve the branch till here, we have, let's say, 1 delay slot, 2 delay slots, 3 delay slots, and we have 3 instructions, we'll say. Or maybe you can redirect at this point out of X and you have 2 branch delay slots, depending on how you sort of wire that in, if you can make the cycle time. Let's say you have 2 branch delay slots. What ends up happening is you have instruction BEQZ here. Let's say that is at address 100. And then you have 2 instructions which execute no matter whether the branch is taken or not taken, that follow it. So these instructions are in the delay slots of the branch. And you can have architectures which have things like load delay slots and other things like that. But for right now, we'll talk about branches. And we can force these instructions always to execute. Unfortunately, if you go look at the sort of percentages of probability you can actually fill these delay slots, it's pretty low. It's always not easy to find work to shove down here, because you're basically taking work that was above the branch and in the compiler reordering the code to put the instructions that were before the branch after the branch. OK, well, this is good. I mean, if you could actually make this work out, this is great. One of the problems with this, though, is the probability of filling 1 branch delay slot, let's say, is 70%. And the probability of filling 2 branch delay slots is even lower than that. It's maybe 50-ish to 40-ish%. As we said before, if you have a monkey pulling out of a hat, or just some random process pulling out of a hat, you're going to do 50%. Correct. So, and as we'll see today, if you use some more fancy branch prediction or the outcome prediction techniques, you can get the prediction accuracy of a branch all the way up into the sort of 95, 96, 97% probability, and all the way. And people have built. If you look at your sort of, I out of order superscalar. It's on your desktop, your Core i7 these days from Intel. That's probably somewhere in the neighborhood of 98 to 99% correct. So being able to fill these delay slots with some probability, which is less than 98%, is not a good trade-off. You would have better been served possibly by allowing some fancier prediction mechanism trying to fill it if you care about performance. Now, if you care about complexity or reducing complexity in area, a static prediction might be a good way to go. So let's look at some basic rules of thumb here about static prediction. So the overall probability of branches taken, let's say, out of something like SpecInt is 60 to 70%. But it's not equally distributed. Backwards branches have a much higher probability of being taken than forward branches. OK, so we got a question coming up here. Why is this? Yes, so loops with high probability, or by definition, to be a loop, you're going to have to jump backwards. If you jump forwards, it's pretty hard to loop. So if you jump backwards, it's a loop. And in fact, people like to execute loops and stay in loops for a while, because that's where a lot of work is done. So if you're sitting in a loop and you're just spinning in this is increasing the probability that the backwards branch is taken, and that has a high probability. So that's this half. Forward branches, 50%. Can we, what's going on there? Forward branch, 50% going forward. These are usually some form of data-dependent branches, like an if-then-else clause. So that's why the probability of this is much, much lower. You sit in loops for long periods of time. Forward branches typically sort of are if-then-elses, and there's you're checking some data value, and then you're either executing it or not. Now this gets a little trickier with some more advanced compiler techniques. Because sometimes with advanced compiler techniques, you will actually effectively convert a loop with an if-then-else into it, or a condition check at the end, into a unconditional backwards branch, and then a little sort of branch that goes around the piece of code which checks the loop sentinel, or checks whether the loop is completing or not. But even that's actually not a horrible thing, because at least that backwards branch will always be predicted taken 100%, because it's turned into a jump. So that's not bad for performance. It's just might change these percentages a little bit. But things do like to sit in loops, is what you should take away from this slide. OK, so let's think about a technique to try to take advantage of this. So one technique that you can take advantage of this with is actually to add extra bits to your instruction set and allow the compiler to hint to the architecture whether the branch is taken or not taken. Now this is still a hint. If it gets it wrong, we still want the correct execution. So if it takes a branch, we still want to go correct. We still want to execute the right piece of code, but the performance might just be worse. So let's take a look at two branches here. We have branch.t and branch.nt. Branch.t is a branch which is taken, or predicted taken, and branch.nt is a branch that's predicted not taken. So what do I want to say about this? Well, architectures do have this. I was going to say the Itanium architecture actually has static branch prediction completely. Some things have sort of intermediary things with this. For instance, the Motorola 68K kind of has something like this, but not. You can't do it with all branches. So this does exist in real architectures. And one of the things is that this can actually be very accurate, especially if you profile your code. So if you run the code once and you allow the compiler to see which way the branch was taken, it can do quite good. And some of the insight here is there's a lot of branches in a program which are there just to check error cases. and the probability that they actually are taken or not taken one way or the other is one that can basically almost be statically determined at compile time. And definitely if you have feedback information of execution of the program once, that's a very good indicator. So for instance, if you had a loop, the compiler would denote that the backwards branch is taken. So it would put a br.t. And if it's, let's say, some piece of code which just jumps over an error case and checks an error condition, and 99% of the time that it never falls into that, it would predict that taken, because it would just jump over that little piece of code. So you can actually have very high prediction accuracy. Now we're not up into the 99% here yet, or something like that. This isn't great. We're still doing static things here, and at this point it might actually make sense still to have a delay slot, because we're still not over our 70th percent. We're sort of a close trade-off here. You have to get the static prediction correct, and your delay slot might actually still be a better approach at this, depending on sort of how this accuracy compares up to how many times you can fill the delay slot. But let's take a look at what happens in the pipeline here. So here we have a branch taken, and it's predicted taken to this target. We still end up with a dead cycle here because we do not know where that target is until we've effectively decoded the instruction. So that in this sort of intermediate time here, we just have to fetch, let's say, the fall-through case or something like that. But because we predicted it taken, we can do better here. We don't have to have 2 delay slots or 2 dead cycles. We can fill it. We can actually get the correct next instruction in here for the target. This branch not taken, let's say we speculatively execute the fall through, we don't actually have any penalty for a correctly predicted branch here. So if we predict this branch not taken, that's the fall through case. We can just fetch PC plus 4, PC plus 8, and just keep executing, and we have no penalty there. OK, so if we get the hint wrong, what are we going to do? Well, we've effectively taken a mispredict penalty here. And if you look at the branch taking case and you take a mispredict penalty, what's going to happen here is you're actually going to end up having two dead cycles, because we don't actually determine whether we took the mispredict or not until this execute stage. And that's the soonest we can go redirect the front of the pipe. Now, if you look at this and squint really hard, you can see that we actually fetched op-A twice here. This was the fall-through instruction. It is hypothetically possible that you might be able to not hold off killing this instruction, if you will, and in this case, sort of have the pipe do something special and actually end up getting the instruction after op-A or op-B here, if you will. But that's pretty hard to do. So for the base case, we'll just say that you end up with an extra cycle of mispredict penalty when you mispredict. Yeah, so just to reiterate that, what I was trying to say here is that with a branch taken, we fetch the subsequent instruction, the fall-through case. We fetch the target of the branch. We try to kill this, but lo and behold, we actually end up fetching the exact same instruction again. So you could, if you really wanted to, try to optimize around that and not fetch this twice, but then you're kind of having things out of order in the pipe here, because you'd have this instruction's dead, and you have to figure out how to kill sort of sub-portions of your pipe or things out of order in your pipe, and that gets pretty hard to do. But this does really quite well if we do static software-based branch prediction. OK, so let's look at hardware branch prediction. Now, when we say hardware branch prediction, that does not necessarily mean dynamic hardware branch prediction. This could just mean that you have the hardware doing the prediction without any hints from the software. And we have a couple different cases we can try to implement, heuristics, if you will, in hardware. The first one here, always predict not taken. This is what we've done so far in all of our pipelines that we've designed. we predict fall through effectively, and we just fetch PC plus 4. We didn't put a name on it, but this is actually what we were doing. We were doing speculative execution with a static hardware branch prediction of PC plus 4. It's pretty simple to implement. It's what you guys have done in your labs so far. You know the fall through early. Accuracy is not very good. You get all your loops wrong. All your backward branches of your loops just are always predicted wrong. OK, let's do the inverse here. Predict taken. Let's have that be our static strategy in hardware. Well, kind of hard to do here because we don't really know the target of this branch in decode. So it's like going back to here. If we predict everything taken, what do we fetch in this cycle? Well, I don't know. It's a big question mark there. It doesn't do super well on if-then-else's, because a lot of times those are sort of forward branches over things. Or some depends on how you structure it. Some architectures which have things like these static prediction techniques will actually restructure their code such that the compiler will figure out the probability of a branch being taken or not taken, and then work the code around it to make it work out. That's actually pretty common. The Motorola 68K had something similar to that, and the compilers there actually try to work around it. So, well, this is definitely a bummer here. Maybe we can fix that. Like we said, this is the second part of today's lecture, is trying to fix this problem. OK, how about we use a heuristic that all backwards branches are taken, and the forward branches are not taken. OK, so this does a lot better. This is our heuristic of what we were saying before, that loops and things like that will get caught up in this. So a forward branch is not part of a loop. We'll predict that not taken. We'll predict the fall through. Backwards branch will predict taken. This does pretty good. It's better accuracy. It's still nowhere near the sort of 80% accuracy that we had if the compiler could get involved. Because that's effectively the compiler case that we were talking about before could actually implement this entire algorithm in software. Or something much more sophisticated. And that's usually what ends up happening. OK, so that was one way to figure out the outcome. Let's look at a little bit more dynamic way. OK, so we can try to build pieces of hardware which determine the outcome of a branch dynamically. And this is by adding extra little pieces of hardware somewhere in the front of the pipe. So somewhere in our PC plus 4 calculation, there's going to be this multiplexer here in the PC plus 4 calculation. And effectively, we're going to use some piece of hardware to feed into that. And this is our taken and not taken prediction values. And we'll talk about this in a second. But one of the questions here is, what things feed into this PC plus 4 hardware? Well, one of them is going to be PC plus 4. One of them should be your branch target. Unfortunately, as we said, we don't know the branch target till here. So we can't have that come around in one cycle. So we need to hold off. That's this target address question. But first thing is, how do we swing this multiplexer here of our next PC? OK, so some solutions to this that are dynamic in hardware that try to increase the prediction accuracy is we can think about having something which exploits the nature of programs. So what we're going to try to exploit, first of all, is temporal correlation of a branch outcome with previous outcomes of that same branch. So if you're in a loop, and you fall into a loop, and you have a branch that's predicted taken, or let's say you have a branch that is taken, you can use that in the future to predict the outcome of that same branch. So here we're actually going to have a 1-bit predictor, as denoted by this finite state machine. And what's going to happen is, let's say we start in the not taken state. If the outcome of a particular branch is not taken, we just stay here and we continually predict not taken. If we then take a branch, if we then end up taking a branch, we transition over to this other predict taken state, and we sit in there if we're not taken. And if we have alternating branches, taken and not taken, we're basically going to be predicting the wrong one. Or, well, we might have been predicting the wrong one every single time. But we can implement this with 1 bit, 1 extra bit to our control logic. It's not a lot of logic here. It's literally 1 extra bit. And it just says which of these 2 states you're in. Let's take a look at the performance of this. Does this help? So let's say we have a loop here that iterates 4 times. So we're going to graph the iteration number. And then we're going to show the prediction that's coming out of the predictor, this 1-bit predictor. And then we're going to look at what actually happened. And we're going to see if we predicted right or wrong. OK, so in the first iteration, let's say we train up the predictor. It says not taken. It starts off as not taken. That's the start state. We're going to predict not taken. It was actually taken because we're going to loop 4 times in this loop. So we mispredicted. That wasn't great. But then it transitions from the not taken or predict not taken state to the predict taken state. So the next few times we iterate the loop, we're going to get it right. Now this is a relatively short loop. We only run it 4 times. But if you have a loop that executes 100 times, this might actually do OK. OK, but then we look at the end here. And well, the fall through case at the end of the loop, we're going to predict taken, but we actually fall through. This is the last little bit of our loop. That's not great. So here, if you look at prediction accuracy, this is 50%. This was not very good. Let's try to execute the loop again. And I just kind of wanted to show here, the reason that I show a second execution of the exact same loop is to show why the start prediction was not taken. The second time we come back to the same loop, we left this predictor trained up to be not taken. So now when we go to execute again, we come in not taken, and we mispredict the first time, correctly predict the second time, correctly predict the third time, and mispredict the fall through case. So that's why you need to sort of execute this loop twice here to see what the common case is with sort of the loop back to back. Otherwise, if we were to change the start state, you might end up thinking that this predictor does better than it actually does. So that's not a whole lot of magic there. It's simple. It does OK. Can we do better? Well, we're nowhere near 99%. So the answer is going to be yes. OK, so what happens if we start to have more bits to do prediction? So here, instead of having 1 extra flip-flop added to our computer architecture or our processor pipeline, we add 2 bits to our processor architecture. We add a 2-bit saturating predictor. So what do I mean by saturating? Well, what this means is we start off, let's say, in the strong not taken state. And then if you have a predict taken, it moves here. If you have another predict taken, it moves here. If you have another predict taken, it moves here. So we slowly can we have a range here, if you will, of taken. So we have weak taken, strong taken, weakly not taken, strong not taken. And we can sort of move across the spectrum as we reinforce the taken or not takenness of a branch. So still not quite rocket science. There is some subtleties here. Effectively, we're introducing hysteresis into the prediction that we're trying to do here, or our prediction algorithm. And that can help. So let's see how that helps. So let's execute the same loop here. Another time here, let's start off with strong not taken. Strong not taken predicts not taken. And the first time we execute this loop, well, it was actually taken, because loops like to be taken. Well, that's a mispredict. But we transition from strong not taken over here into the weak not taken state. So something actually happens. That mispredict was not in vain. The second iteration happens, and we still are predicting not taken, because we're in this weak not taken state. And we did take it, so we mispredict again. But now we actually transition to the weak taken state. This time, things get a little bit better here. We're actually going to have a prediction of taken. The actual thing is taken. We predicted it correctly. And then finally, 4 here, prediction of taken. It was actually not taken. Sorry, this is actually a mispredict here. This is incorrect. So if you go, this should be yes. But you can see that this is actually doing worse, or appears to be doing worse than our 1-bit predictor. Well, does life get better? Well, we trained this up a little bit at this point. So let's take a look at now. Let's execute the loop another time, given that we started off in this strong taken state. So now we're going to execute again, and we see that we actually predict taken, taken, taken. It actually was taken, taken, taken. And we just mispredicted the last one. And what's nice about this is now when we go to execute it again, we're going to start off, because we mispredicted the end state here, we're actually going to start off in the weak taken state. Sorry, so this probably should be weak taken. Is that what you were going to say? Yeah. So this is another bug in the slide here. I'll fix this in what I upload. This should actually say weak taken, because that's where we left off at the end of this one here. But the prediction accuracy is the same. We're still going to predict taken. So you can see that this does not get tricked, if you will. It does not get untrained by this one not taken case here at the end. But what's nice about this is you can train up, basically, and the hysteresis will not get fooled by one branch at the end of a loop sort of falling through. And that's positive. You can even think about this as actually being helpful, that the fall-through case might even signal you to do something. People could actually have you can even use that to sort of trigger something in your finite state machine. If you see lots and lots of takens, and then one not taken on the exact same branch, that might mean something to you. And people, in fact, have done things like that. So you start to get, even with 2 bits, you can think about having different state machines for the same thing. So here we have something which jumps directly to strong from weak. So instead here, when we had strong, weak not taken, and we have a taken here, we actually jump to strong. So we train effectively very fast. So still hysteresis, but sort of faster acting hysteresis. So this looks pretty similar to what you had before, but now this weak not taken state will jump straight to strong taken if you have one mispredict or something like that. But this is only one example. If you go look in actually the Shen Lepaste book, in the chapter that talks about this, they give like 3 other examples that look similar to this and are different heuristics to sort of try to get different chances or different behaviors that are common with programs. But none of these are going to be super, super great, because they're only 2 bits. As you actually start to think about having a table of these predictors, so you have local predictions. So it's not predicted globally, but instead we're predicting based on each different branch. And how we do this is we take bits out of the program counter, and we index that into this big table. And then we can store, let's say, 2 bits in this table, and then we can train each of these things separately. And Now, we're not going to want to have an entry in this table equivalent to the number of branches in the program, because it would be huge. But you want to somehow have some number of bits, k bits in fact, maybe just take the low or the medium order bits of the program counter and we use that as an index, similar to how we use indexes into caches. You could also think about having multi-way associative versions of these. So instead of having, this is a direct mapped version, but you have a multi-way associative version of this. And if you look at, let's say, something which is a 4 kilo entry version of this, that's pretty big, actually. But a 4 kilo entry branch history table with 2 bits per entry, now we're starting to get somewhere. We can get sort of 80 to 90% prediction accuracy. So that's starting to get us there. But we had to build, I don't know, 8 kilobits worth of storage. And we had to somehow pipe it into our next PC logic, which is kind of a sensitive path on our processor. But, you know, this can be helpful in performance. So let's, actually, before I move off this, I want to make one point. There are other ways to organize this table. So what we're really doing here is we're indexing into a table, and we're, let's say, running through some sort of finite state machine decoder here, which tells us taken or not taken, and then we're individually updating sub-entries of this table for a particular branch. You could think about having other things to index into this table. So either more complex hash functions, or maybe some other history information, or maybe previous states, or just some other bits up here. So this is just a base case. We're going to show some more complicated examples for spatial correlating predictors. But a lot of the ideas that we're going to talk about in spatial correlating predictors, you could apply that to these temporal correlating predictors. But I just wanted to make that point that these things do, what we're going to talk about, we're going to show much more sophisticated versions in our spatial correlation predictors. But you could apply a lot of those ideas back to these temporal ones. OK, so let's look at spatial correlation. We talked about temporal correlation. So in time, one branch and the direction that one branch goes has a high probability that it's going to influence, or it's going to predict, rather, whether that branch in the future is going to be taken or not taken. That's what a temporal prediction is. A spatial prediction, what it's trying to get at, this piece of code here, is that if you have, let's say, one branch do something, the future branch that's, let's say, right below it is going to somehow be correlated. So a good example case, and this is kind of the canonical example here, is if you check this value and it's less than 7, it's also less than 5. And you get code like this relatively often. So these branches are correlated. But they're not the same branch. They are different branches. This branch and this branch. So we're having some sort of spatial correlation here. And we wanted to try to exploit this somehow. And this was Yale Pat and one of his students came up with this not that long ago, surprisingly, in the 90s. And the idea here is that, I don't know, we're going to have an extra register we'll call a branch history register, which will store whether previous branches that we've executed were taken or not taken, and then use that to index into some tables, or use that somehow to predict what's going on. So this is actually going to be a shift register, where we're going to shift in what the branch did. So it's not based on just the address. OK, so here's our picture of our branch history register. the branch outcome, either whether taken or not taken, goes into here. And every time we take a branch, we're going to shift a new value in and let the old one sort of fall off the end. So what can we do with this? Well, we can use it to index a table. So if we have a pattern history table, what the pattern history table is it will be indexed by previous branches. And then based on this pattern, we're going to look in this table, and that'll output either some bits that go into our state machine, or it might just output one bit which says taken or not taken. But in a general sense, it's going to output n bits, maybe 2 bits, which will feed into a state machine which updates itself, like what we had before. What's cool about this is, let's say you have a loop which always has 4 iterations. So we're going to have taken, 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 not taken. Well, what's going to happen is we're going to shift in these 4 taken, 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 not takens into this register. And then let's say we execute the loop. We execute that whole loop multiple times. We can train up this history table here, and it'll detect if we've seen the loop, let's say, have taken, taken, taken. What do we think the next thing is going to be? It's going to be not taken. And this predictor can detect that. And that can do that actually with only one bit here, just a 1-bit state machine. Because if it sees taken, 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 not, or excuse me, if it sees taken, 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 that's going to index into this table, and the output of here is going to be not taken. So it's going to be able to predict sort of short runs, loops which have short runs. And if this, as this gets longer, this branch history register gets longer, you could actually predict loops which have longer runs. So if this is 100 bits long, now you're never going to have 100 bits long because a pattern history table of 2 to the 100 is a very large number. But as this gets longer, let's say it's 10, that's very reasonable. You could predict a loop, let's say that loops 10 times, and it'll get the fall through case correct, it'll get the start case correct, and you will have 100% accuracy in that loop for your branch prediction. Wow, that's pretty cool. So this is where we're starting to actually get some traction here. And this is where branch prediction really started taking off. This is where we started to get sort of above 80%. We start to get to higher numbers. If we want to go even if we want to even have better prediction, we can start to think about having a branch history register which indexes into multiple tables and then chooses based on some bits in the program counter between these different pattern history tables. Now, why do we want to do this? Well, we want to know, based on our PC here, which one to choose. So this is trying to sort of get the mixing here of temporal and spatial correlation here. Because if a certain branch gets executed, you want to use that prediction for that particular branch. And here, you use some hash of some bits in the program counter. We'll choose between some number of these history tables. So this is mixing our spatial correlation with our temporal correlation together here. And this is called 2-level branch prediction, because we have multiple levels here. We have the history register indexing in here and the program counter. And this can do quite well. And if we want to have a sort of generalized 2-level branch predictor, and you want to make this even go better or even go faster, you can start to add multiple branch history registers and have them be per branch effectively. Now, you're never going to have it per branch. You're going to have it be somehow aliased into here. So you have multiple shift registers. And only when that branch is indexed is when you actually shift that shift register. So for relatively small numbers of m coming into this index into this branch history register table and k indexing between different pattern history tables, you actually can get very high accuracy. You can get like sort of 97% accuracy. Now we're still not at 99. Now you might say, why do I care? 97 sounds pretty darn good. Not good enough, unfortunately. You actually need to go higher if you have a 22-stage pipe and you actually want to have decent performance, because 22-cycle mispredict or 20-cycle mispredict is really quite bad. Is pretty damaging when you go sort of work through the iron law math. So before I go on, this is kind of one of the more complex slides that we're going to see today. Does anyone have any questions about this, of what's happening in the mechanics? So let's talk about training this. So as you're executing, you're going to be shifting, when a branch occurs, you're going to be shifting the old outcome into this register, one of these registers here, based on the PC of that branch. And then you're also transitioning based on the outcome, the prediction, or the state machine, which is embodied in the prediction. So this is actually a pretty complex machine here. And you don't probably want to be updating that, we'll say, right in the fetch stage or right in the decode stage. So typically how this works is you go to do this update later down the pipe, sort of at the end of the pipe somewhere. You go and you actually feed back the true outcome of all the branches, and that feeds back into the branch history register and the pattern history tables. And the downside to this is, by waiting to the end of the pipe, is, well, first we'll go for the upsides. The upside is you know that the branch was actually executed. You know the actual outcome. You know that it wasn't squashed by something else. If you were an out-of-order pipeline, you know it was actually committed, because you don't really want to train your predictor on bogus data. So you don't want to like sort of train your data on incorrectly predicted branches themselves. So if you, let's say, have a mispredicted branch, and in the shadow of the mispredicted branch you have something else, and that would to go and try to corrupt your prediction state, that's not good. So usually you sort of wait to the end of the pipe. The downside of waiting to the end of the pipe is there's more feedback, and it takes longer to train up. It doesn't necessarily take longer time, but if you have a branch followed by a branch that wants to use that prediction, you can't actually use that, let's say, until it gets to the end of the pipe. So you're going to be using sort of old, stale data for a little bit of time, or as long as your pipe length is. Not the ends of the world, but something to be aware of. OK, so now we're going to start talking about getting into our higher 90, well, higher than 97%. We're going to talk about sort of getting into our 99% accurate branch predictors. And this brings us to tournament predictors. It's a great name. Came up first in the Alpha 21.264. And what they did is they actually had predictors to predict which predictor to use. So one of the interesting things, going back to this two-level branch predictor, is sometimes you want per branch information or per branch history, and sometimes you want global branch history. The per branch history, you're only basically training this up based on that previous branch. But in this example here, you're training it upon other branches. So sort of going back here, this is a different branch than that branch. So you might actually want global history. But there are times, for instance, in a loop, you actually want local history. So tournament predictors, actually, they end up with things where you're using a predictor, we'll call it a choice predictor, that predicts which predictor to use. I show two examples here, one which is choosing from a global predictor and a local predictor. That's kind of the canonical usage of this. Actually, in 21.264, they had something more complicated. I think they had, I think anecdotally I heard they have about 10 predictors in there, and they're trying to choose between 10 different predictors. And they train the choice predictor based on which predictor was correct. So you can use, basically, because you run loops and you run code a lot, you can train up the choice predictor to choose between other predictors based on the accuracy of the other predictors. So for a particular branch, one of the predictors is always wrong. The choice predictor can say, just don't use that one. Just exit out. So this does quite a bit well here. And you're starting to get into the 90, I don't actually know the full numbers here, but it's probably 98 to 99% accuracy for large individual predictors hooked up to this. The book Shen-Lapasi that you have talks about sort of some other things you might want to try to stick into here. But for right now, we'll leave it at this, that we have sort of global predictors, local predictors, things that use a branch history register for both of these, and then something which predicts between the two. But I'll just restate it one more time. You train up your predictor to determine which one to use, and it has lots of training data. But this is all heuristics. If you go look in the book, actually, there's they even joke, it's actually not a joke, it's something someone actually has proposed. They call it the perceptron predictor, and they basically have like a neural net hooked into the prediction strategy. So these things can get pretty sophisticated. I don't know if anyone has actually ever built the perceptron predictor for real, but at least has been proposed. OK, so that gets us out of the outcome part of today's lecture. Let's start talking about how to figure out where we're going. So this brings us back to this picture. And I took some stuff off this picture now. But now what we need to do is we need to know the targets, the relative targets. And as I said, we don't know the target for a branch, a jump, and a jump and link until we actually do PCE plus the offset calculation, sort of somewhere in the decode stage, until we at least get the instruction. For jump registers and jump and link registers, we don't know that until later. But this is baking out. This is not looking at the outcome. This is just looking at when do we know the value. But this is important because even though we have the prediction of where whether it's taken or not taken, and we can do that, let's say, with 99% accuracy, this is the harder one. We're trying to pick from 2 to the 32 possible numbers. Can we actually do a good job here? So something not on the slides, but something I wanted to talk about very briefly here is we can use a static algorithm similar to what we had seen with the other predictors to do this calculation through the compiler, if you will. So there's been a few architectures. One example actually is the Hitachi or now Renesas SH5 architecture, which is sort of a media processor, we'll say. And they actually have an instruction which loads the target of a future branch. So they decouple the branch into two instructions, the actual branch and a prepare to branch, which they have to execute earlier in their instruction sequence and says, I'm planning to do a branch, and it's to address something. It's actually called prepare target is the name of this instruction, or PTA, on their architecture. And because of this, they don't have this problem. All they need to do is actually do the branch. So they know the target of a branch in the fetch stage. They can actually just go, because they have this instruction which says, load up this special register with my target of the branch, and then we'll decouple the actual taking of the branch sometime in the future. So this is an interesting idea. I thought I'm pretty sure there was actually one of the CDC machines, the Control Data Corp machines, did this a long time ago also, but I couldn't find the reference in time for today's lecture. But I know the Hitachi SH5 definitely has this instruction. So all I'm trying to get at here is that there are static software ways to go about doing this. In addition, now let's talk about some dynamic ways. OK, so the most common way to go do this is to implement something called a branch target buffer. And the branch target buffer you actually do in parallel with both the branch prediction outcome, or the branch outcome prediction, and the PC+4. So you put into it the current PC, and it's going to tell you somehow 1 out of 2 to the 32 possible targets. How does it do this? Well, what it does is it actually just keeps a table of where that branch has gone in the past. So the first time it executes, it just gets it wrong. But then the second time it executes, but given that first time it executes, it's actually going to load a table with a predicted target. So we're going to load the predicted target based on where this branch went in the past. We're going to index into this table based on our current program counter. And then we're going to check to see that we actually match. So we're going to take the whole PC. We're going to do a tag check, very similar to our cache. This is effectively a cache. And if we hit in this small cache here of targets, we have the new program counter if we predict it taken. If we predict it not taken, we just want to use PC+4. So in effect here, we can actually predict the target of the branch based on where this branch has gone in the past. Well, that made this a lot easier. I thought it was going to be really hard. Well, it's actually not that bad. One thing I should say is the size of this table kind of matters. If you alias too many places into here, you may end up just pulling out wrong data, or you might having a miss quite often. So you want to size this table appropriately. But you don't want to make it too big because you're carrying the entire program counter in here. And that can get big. So the data in here is quite large. So one way to solve this actually is typically people try to make these things set associative. So you'll actually have multiple PCs and predicted targets, because that actually has a little bit better performance if you can check multiple in parallel versus making it larger. I mean, you can just make it larger, but typically having a little bit of associativity helps with this. But you're really executing this in parallel with the PC+4 logic. One thing that also makes this a little bit better here is the branch target buffer does not hold every instruction. If it's not a branch or a jump, don't put it in this table. So you really only put in instructions that are branches into this table, which helps save a lot of space. OK, so we have a question here. How do we achieve this effect without decoding the instruction? So we have a branch target buffer. We don't want to decode the instruction. Can we just look in the branch target buffer? Is this good enough? Is all the information we need in that table? Because we're executing it in parallel with the PC+4. We haven't fetched the current instruction. Is that good enough? Or are we missing something? Yeah, this is kind of what I was trying to get at, is that because we check the program counter here and do a full bit width match, this is good enough. We don't actually need to look at anything else. One thing this comment was here to make a point about something called a line predictor. Sometimes you want to get rid of this valid bit and this PC from before. And then you just have coming out of here, instead of predicting the program counter, you don't really need to know the program counter. You just need to know where to go get it from your cache, sort of which entry in the cache to go fetch. And this is called a line predictor. So a full branch target buffer will give you an actual PC. At some point, you actually do need to know the PC, but you can wait to actually know the PC until later down the pipe. All we really need to know is which line in the cache we want to go fetch the next cycle. And we can do that actually by just sort of removing this check and just ad hoc, just having it fetch whatever it gets pointed to from here, which might be wrong, but we have to check that. So anyway, this is a trick question. We can achieve this with a full BTB, a full branch target buffer. If we don't have this check, it turns into something called line predictor. So we're predicting which line in the instruction memory or which line in the instruction cache to go fetch from. Oops. OK, so this brings us to jump register. So jump register. This one gets harder to train. We can try to train it the same way. We can try to use the BTB. So let's look at these different cases. So what is a jump register used for? It's used for switch statements. It's used for C++ virtual function pointers or dynamic function calls. So if you're doing a jump through a function pointer. And it's used for returns from subroutines. So how well does a BTB work in these different cases? So for switch statements, if you use the same switch statement and the same case gets lit up, this works pretty well. It's kind of like training any other predictor. If the probability that you're actually choosing something out of that switch statement is data dependent or highly data dependent, you're probably not going to predict it very well. And you're not going to do there's probably no great solution to this. There's some people who do sort of data prediction and try to look at the register values to try to do this a little bit better, but it gets very hard. Dynamic function calls. Well, this works very well. So if you ever ran a C++ function, in C++, they have function pointers all over the place. And this is to implement polymorphism. And this is how, when you, in C++, you sort of do a method access on some sort of function, you're actually indexing through a jump table inside the data structure. And it just so happens that this is basically always correct, unless you actually reassign that object to something else, or if that object actually changes to a different type. So an example of that is that you have class animals, and you have dogs and cats, which subclass from animals. And you have a pointer to an animal, and you have a cat and a dog. And let's say you assign a cat to this function, or excuse me, this object pointer, which is an animal, and you call some method on it, like run. Well, that's going to train up very well. But all of a sudden, if you change that cat to a dog, the virtual function pointer, because what you actually execute on a cat, when you run the function run on a cat versus running the function run on a dog, they do different things. Cats like to sleep a lot, and dogs like to run around a lot and bark. So the code in the middle of the run function of the cat and the dog are different. So we no longer jump to the same location. So our BTB will be wrong, but it will train up pretty fast, because you're probably not changing the object pointer very often. So that's decent. OK, so subroutine return calls. Jump registers are used there a lot. So you call into a function. You do it with a jump and link. To come back out, you come out with a jump register. Well, BTBs are OK if the place that you are returning, or excuse me, the place that you call from, you're calling from that location a lot. But if you're calling a function from different locations quite often, effectively what's going to happen here is one function is going to be called from lots of different locations, and you're not going to be able to predict the return location very accurately. So if one leaf function gets called from lots of different locations, that's not particularly very good for a BTB. One interesting thing about this subroutine return case is that the jump register at the end of a leaf function, the program counter for that jump register is not correlated to the function which called into it. So effectively, when you go to index the BTB, you're using the address of the jump register, and it might point to some other function that had called it in the past. And that may have no correlation to something calls in the future. And that's why this is really hard to do. So can we do better for jump registers? Yes. So there's an idea of a subroutine return call stack, or a subroutine return stack. And the idea here is you have a small predictor, specifically just for jump register subroutine returns. And what you do is you track function calls, and you push the return address onto a stack. And then when you do a return, you use that prediction. So let's say we have these three functions here. We have function A, which calls function B, which calls function C calls function D, as denoted here. We have some stack that we're going to push entries onto when we do jump and links. So we know that there's something to load this predictor with. So when the function call gets executed or the jump and link gets executed, we're going to push the address of what is after effectively the function call site. So I'll denote it here by the address of FB. So that's for when FA calls into FB. In reality, it's probably like, well, the instruction right after that is where we're going to return to. Likewise, when FB then calls FC, we're going to push the return location after FC. And when FC calls FD, we're going to push that. And these come off in the inverse order, because it's a stack. So when we try to pull off this, we're actually going to pop return addresses boop, 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 like that. So we're going to pop off the FD, FC, and FB, or the address after FD, FC, and FB, and we're actually going to predict the return for this function, or the leaf function, correctly every single time. Where it gets a little hard is if we have our call depth be deeper, or recursion depth, if you will, be deeper than how many entries we have in a return stack predictor, then we're going to start predicting wrong. But otherwise, we can do pretty well with this. In fact, some architectures make this a little bit easier on the hardware, and they'll actually have a special instruction for the jump and link, or the call instruction. So for instance, in x86, they have the call instruction, and that tells the code, basically, or tells the hardware to load this predictor. Because otherwise, a jump and link, there's too many other uses for a jump and link. It's not always a function call. It's almost always a function call, but it's not always a function call. But for a call instruction on x86, that's basically always a call. So you know to load this. And then on x86, there's a return instruction, which is always a return from a function. That's the semantics of it are tied very well. OK, so there's actually one other topic I wanted to talk about today that's not in the notes. And this correlates to line prediction. We talked about line prediction. The one other thing I wanted to talk about was way prediction. We haven't talked about this yet, but if you have a, let's say, two-way instruction cache, we talked about where to go look, of which line to go look at in the instruction cache. But one of the things that's just as hard is if you have two-way instruction cache, and you're trying to fetch the next instruction, which way do you go and shove into the decode stage of your pipe? Way 0 or way 1? It's tough. You don't know. So this is one of the reasons a lot of times people will build direct map instruction caches, because it's very hard to know which way is the correct way. But our predictors, just like our branch predictors, helps with this. We can build a way predictor. So we can have the same prediction architecture we've talked about today in today's lecture, dynamic, multi-level predictors, sometimes even baked into the branch predictor. And then that can be used to predict whether we choose from, let's say, way 0 or way 1, or if we have a 4-way set associative cache, way 0, 1, 2, or 3. Anyway, that's what I wanted to talk about today, and let's wrap up here for today.